All right, welcome back. And where did we leave off? We were just talking about the Simonduino and kind of going over the high-level design and looking at all the subsystems. And now what we're going to do is we're going to start drilling in and we're going to start looking at the actual design of things and the IC selection that we're going to use. All right, so so one thing, let's come back here. So what I've done was we have the work copy that we created, which is just a copy, a forked copy of my original, right? So we've got this work copy, and the work copy is complete. And this is kind of what you want to do. You want to create a fork of the original, the color match game, and call it work copy or whatever you want. That way you can mess with the final complete project, right? But also I decided, I can't remember if I said I was going to or not, but we're going to create a final version, and we're just going to do a lot of copying and pasting. So we've got a final version here, and the final version is just blank. So this is going to allow us just to copy and paste pieces of the working copy as we look at the ICs, all right? So, so let's just get right into this. All right, let's get back to the design here. So here's the Arduino Nano. So this document, this PDF, which of course I'll provide, but you can get it as well online. So what is this? This is the Nano design, and if you go to the Arduino page here, let's see, the Arduino Nano, so Arduino CC or org, and again we had that whole discussion about CC and org and the company splitting up and being remerged, but there should be technical specs and documentation. So if we go to the documentation, then here are the Eagle files, so the actual schematic Eagle file projects, and then here's the schematic in PDF. So if we just click this, then it pops that open. All right, so that's all I did, was I just have a copy of that so I can work with it. All right, I don't like using PDF viewers inside of the browser. It just seems to have trouble, so I always make a local copy and bring it here. That way I can mark it up and do things. Okay. All right, so now this is actually a massive project depending on how deep you dive into it. So if you were going to design something with a microcontroller, you would have to read the data sheet inside and out. You'd read the reference manuals inside and out. You'd read the application notes inside and out. You would know everything about it. Or you can just copy a reference design and not know what you're doing. All right, or something in the middle. We don't have time to go reading the data sheets and the reference manuals. I would like you to, so at some point you should do that. But we're going to basically take the point of view as we have a reference design, and we're not going to follow it exactly. We're going to maybe improve things a little bit here and there electronically. You know, just that when we look at something, we see say a regulator that we don't like, we'll change the regulator. But as far as the IOs go and all that, where things connect, we have to maintain that because that's part of the Arduino design, and the firmware expects that. So we got to keep that in mind. All right, so first thing is we're going to do a little bit of this. So if we go back here and we look, we see that the Arduino Nano uses this surface mount QFP. So that's good. So we're going to use that exact same surface mount QFP because we want to do everything in surface mount. Now, another thing we want to do is we want to use surface mount components for all our passives, for our resistors, capacitors, etc. So we need to pick a size. Now, if you look up the sizes again of surface mount components, right? Let me back up here and let me see. I think images doesn't really, and we've seen all this before, right? So here's what these surface mount components kind of look like, right? And they have different sizes and so forth, right? And then if we go here to the size chart and let this, there we go. So here is the standard sizes: 1812, 1206, 805, 603, 402, 201, and there's also smaller sizes. How these dimensions work is over here you see dimensions in inches. So the 0805 is simply 8 thousandths and 5 thousandths. 8 thousandths wide, 5 thousandths tall. 603, 6 thousandths wide, 3 thousandths tall, and so on. So the 805 is pretty good. That's what I prefer to tell beginners to start working with because you can get your hands on it. And it's about 2 by 1.3 millimeters as well if you think more in millimeters. Either way, that's what we're going to use for the parts. We're going to use surface mount 805 parts. So now, once we have a footprint of an 805 footprint. Here's the cool thing. An 805 footprint, just a little rectangle. You can put an 805 resistor, an 805 capacitor, an 805 LED, an 805 anything. So once we have that footprint, we don't really need to care about the specific part number. So if I have a 1K resistor, a 300 ohm resistor, a 220 ohm resistor, a 100K resistor, I don't need to find the exact part number from an exact vendor. I just need to find one vendor that makes an 805, say 1K resistor. Then I know that everything would fit on that footprint. Okay, so keep that in the back of your head. You don't have to, drill down and pick every single part exactly, and you're going to change it anyway. And this is a big problem. Whenever you're doing your part sourcing, that's why you have to, have some parts companies that you like, some manufacturers, like maybe like Vishay, you like Comet, you like Microchip, you like Fairchild, you like TI, for whatever parts, and you just kind of stick to them. That way you don't have to go all over the place. All right, keep that in mind. Now, let's go and let's look up our processor. All right, so let's get DigiKey here, DigiKey or Mouser, both good search engines to do this and has all the information, or Octopart, but I just kind of keep using DigiKey here since it's up. Let's get our design back up. Okay, and we'll go here to the working copy here. All right, and then you can see the working copy uses this part number right here. So apparently this is inside of Circuit Maker. So I'll double click on that and let's go ahead, oops, and let's copy it. Let's not delete it. All right, let's go back here and let's pop it in here. All right, let me tell you a couple things. First, I think we've mentioned this before, but Microchip purchased Atmel a little while ago. So if we go to atmel.com, and they still have their own web domain as part of Microchip's entire system. So you can go on Atmel here and you can search, and then we can find, here's the data sheet, and documents, data sheet summary, probably go here. And I just want the actual page. So this is the summary. So that's not what I want. So let's go to 8-bit microcontrollers. All right. So here, let's go to product search. All right, and cross our fingers. All right. So now this is all of them, which we don't want this either. So this has got 8 and 32, and this is one of the problems. It's just trying to figure out, you just want the page, and a lot of times on these sites this is not easy to do. All right, so what we're going to do is we're going to move the flash here, and I know that the flash is 16K. All right, it's an 8-bit CPU, and let me see if that kind of narrows it down to what I want. And not so much. It's got too many pages. Let's see, is there anything else we can knock out here? SRAM, 128. I know that the SRAM is, I think it's 2K. So on this chip, 2K, and we'll push it up here, and we'll put it to 1K. All right, between there and there should put up what we want here. All right, and let's see. No, it's going to be on page 2. And no, of course not. That would be too easy. All right, so we did something wrong here. So let's try again. And now this, this search is very frustrating. And you're going to find that a lot of these things are very frustrating on these websites. They don't do what they're supposed to do. All right, so I should be able to Mega AVR. Let me see. Let's try this. All right, the Mega AVR, and let's see here if we can do this. All right, so here's a better place. We want the 328. Okay, so now let me tell you a couple things. So see, here's this 328. The Arduino originally used the 328. The only difference with the 328P, now we're talking about the original Arduino Uno, the very first one, which I believe is called the Uno also. Very first one 10 years ago used the 328, and then they changed it to the 328P. The only difference is this is Pico Power. It's just got much better power modeling, all right, and power control. All right, so we click on that. Okay, and now I'm making a mistake. Now I'm starting to remember. I think the very first Arduino used the 168. Used the 168, which had 16K, and then they switched to the 328, and that's been the way it's been for a long time. So a little bit of a mistake. So this has actually 32K of flash, yeah, 32K of flash, and then it has 2K of RAM. All right. So, all right. Anyway, so here's the actual product page that I've been trying to find. for the AT Mega 328. So what you would do here is you would sit here and you look through here, right? And then you would go, check this out. You look at the products, pricing and all that. 5,000, it's $1.50. At 100, it's $1.75. It goes, 20 megahertz is the speed that we can run it at. Here's what the features are. And then we go down to the documentation. And now you can see there's a lot of documents here. Now, if you're going to actually design things with these processors, you would read all of this. The data sheet, the summary data sheet, I'd read all of this information, right? And I have read all this information. I've read every single one of these data sheets, I bet. All right, just to get an idea of everything. And then, of course, you forget it, right? Because you play with 100 different microcontrollers, maybe hundreds in your lifetime. You'll play with them. And then all these quick start guides and all this stuff, instructions say you got to read all this. All right, but since we're doing electrical engineering and embedded engineering mode right now, we'd probably stick with the data sheet, and then what we might want to find is a hardware reference manual. So if you look through here, all right, and I can't find it right now, but if I type in hardware, and if I can spell right, hardware, yeah, so there's hardware, okay. So see this right here, hardware design considerations, it's an app note. So I pop that open, okay, and okay, so now hardware considerations, okay, and what's going on here is there's a version of it for all these different processors, okay. So we're going to look at the 328P, here it is here, and this is just updated a year ago, so that's cool. And it went right back to this page here, which is not what I wanted it to do, so it's a cycle. All right, so then I'm not sure. Again, you're seeing us do this in real time. Okay, so this, not sure what this list is supposed to be here. That's just links back. So this is the document right here. Okay. And you're going to have a lot of fun on Atmel Microchip site with these kind of problems, cycles in the site, going back to things. The sites are so big, they just can't maintain it all. And a lot of times you get confused where you're supposed to go or click, and it's very frustrating. So be patient. Okay, so hardware design considerations. And so what this is, so you're a hardware engineer, embedded engineer, and I want to build something with this chip. So I've got the data sheet, and I'm reading the data sheet, which we're going to get also. But this kind of tells you, what you should hook up, talks about things, what goes here, the clocking, the reset module, here's the reset, external reset switch, the programming port to program the thing, the JTAG interface, all these different things. And let's scroll down here, how to hook up different external crystals, resonators, some calculations for computing capacitors, a little reference design, basic schematic. So here's the basic schematic. So if we look at this, what do we got? We have a 16 megahertz crystal here. Okay, so, and we could make this, we can do different things with this, all right, if we want, but 16 megahertz is the reference. Then there's two 22 picofarad capacitors, right? Then here's the main power, the 3.3 power. And then they're saying, hey, separate this reference right here. This is the analog power with a ferrite bead. Remember, we've talked about that and we've done that. That creates a nice little interface. And then we've got a little bypass capacitor. There we go. And then over here, we've got our V sub CC and ground. And here's our 3.3. We got another 0.1 microfarad or 100 nanofarad capacitor. Very light. They're showing minimal bypassing. To me, this is nowhere near enough. I would do more. And then another one over here on this pin. Okay, and then another one over here on this pin, and that's the basic design right there. That's why people like this processor. It's fairly simple to get up and running. And then here's some basic PCB layouts. Just hey, put the thing down, put your capacitors down. That's it. And here's again what this thing looks like. Okay, so not complicated, but that's what this is for. This gives you a reference of where to start. So when you go to design a board based on a microcontroller, you want to read this and read the data sheet. Okay, so let's go get the data sheet. So let's go back up and get the data sheet here. All right, and we'll go to 328P, and that should take us back to the page, I think. And again, I'm not clipping this or whatever. Here's the data sheet right here. And a lot of times you're scrolling around and you're like, okay, here's the documentation, here's the complete data sheet, but it's also up there. So it's 5 megabytes. Let's grab that. Okay, let's zoom in a couple times here. All right, so here's the data sheet, and it's no joke. This is a baby microcontroller. This is like newbie level technology. If you start messing with ARM technology, very advanced ARMs, you're looking at a 2,000, 3,000 page data sheet. This is only 400 pages. This is nothing. This is very easy. So you could actually read this, right? You could actually read this thing end to end, and I have read this thing end to end, the entire thing, every single word of it. Again, you forget most of it, but it's like you read it, you at least see it, and so that's another thing you would do when you're designing a computer. So here's a 328p complete data sheet. Okay, so we got the data sheet, we got a hardware reference manual. Now, the whole idea is we want to copy this Arduino Nano design. So we go look at the Nano design, and right off the bat, we can see, hey, he's got his 16 megahertz here, right? He's got his two capacitors. They're not labeled out here in the design, okay? He's got his power here. Here's his two V sub CCs, which he's combined together, and he's showing a 1 microfarad, a 1 microfarad, and a 4.7 microfarad. All right, and that just tells him I'm going to put these close to these pins. All right, now and what our design may do is we may put a 1 microfarad or a 10 microfarad in parallel with a 0.1, another 1 or 10 in parallel with a 0.1, and then put each one of those pairs next to each V sub CC. Then you see he's got his analog V reference here line, all right, pin 20 here, and so he's got that just connected through a capacitor to ground, and I can't remember why that is. So this is the analog reference, and so this should be to whatever you want as the reference voltage, and we'll take a look at our design to figure out what I did there. I read something about this, and this, I can't remember if this is incorrect or if you're not going to use it, then you can put it to ground through a 100 nanofarad or a small capacitor. All right, but again, that's a little bit funny right there. All right, so here's analog V sub CC. This is what's powering analog V sub CC. Now look what he's done. He's tied all three, analog V sub CC, V sub CC, V sub CC, all to the same thing. So that analog line is going to get noisy potentially. We want that to be cleaner. And in the reference design, it showed two different power domains. They separated them by a ferrite bead and their own bypass capacitors. All right, so again, not liking that so much. Here's reset. This is fine. So there's looks like it's a 1K pull up to reset, and then he's got a little switch there. That's fine. All right, and that goes to the reset line. Then what else do we have going on here? So this is important probably. So this is a D13, this specific pin right here, which is also, this is the SPI interface. This is S clock. This is a MISO, master in, serial out, master out, serial in. Again, you don't know anything about, I'm not assuming that you do. You don't know anything about microcontrollers, I'm assuming, or different protocols, but if you do, obviously this is a SPI interface, serial peripheral interface, and it has 4 signals, a clock signal, a data out, a data in, and a chip select typically. So here are 3 of those signals. But he specifically got this one connected to this LED. So this is probably part of the Arduino design, and it's some kind of indicator. So we're going to copy that in our design. Then there's going to be firmware loaded on this, right? And we load the firmware on there that gives it its Arduino personality. And to get that in and out, it uses, then after the firmware is loaded, then to communicate to the bootloader, right? And so the microcontroller, after it boots with this Arduino personality, it's going to have a bootloader. And what a bootloader does, it's a piece of software that when the processor boots up, it sits and it waits for a program. And that program can come in, say, over USB, SPI, I2C, wireless, who knows, right? In this case, it's coming in over simple digital serial over this TX and RX line. So specifically, he's using TX PD1 and PD0, which is TX and RX. So we have to use those same pins, or otherwise we'd have to modify the firmware because it's expecting traffic on these 2 pins. Now, really, really, really want you to make sure that you remember this your entire life if this is, you're just starting off doing microcontroller stuff and communication stuff. You are going to make about 1 million mistakes with TX and RX. You have to keep in mind TX means transmit, but sometimes it might be labeled as put the transmitter here, so it's really a receiver. So now on this microcontroller, TX means transmit. Data is going out. Data is going out. RX means data is going in. But you got to be careful because so we have this TX and we have this RX, right? And depending on whose point of view it is, we might connect this to the wrong thing. So now over here on this USB chip, this is a USB to serial bridge, it's called, by FTDI, all right? And we're going to take a look at that also. It's got a TX and an RX. Now take a look at this. So here's TX, pin 1 in this case. We're going to change this chip, by the way, because this chip is expensive and old. TXD, and we've got RXD, but it says connect TX to RX. So this is the transmitter of the USB chip. So it's going to transmit to the receiver of the processor. Likewise, the transmitter on the processor, the transmit pin, is going to go to the receiver. So here's TX. It goes to the receiver of the USB chip. But depending on, you know, the manufacturer, whatever, this could be wrong. So see, this is TX saying it's TX out, but it could be labeled like RX, meaning connect it to the RX on another chip because it's the TX. So the bottom line is, I always make mistakes doing this. I read the data sheet, I check it, I double check it, and somehow you invert it. So a lot of times I'll actually put jumpers on the first design so I can flip TX and RX, right? It happens all the time. It's almost funny, all right? Anyway, so forget this USB for now. Let's come back here. All right, so we got our bypass capacitor. We've got something funny going on here in AREF, which we'll see if in my copy of it we did that. If so, we'll just copy it and assume that I read something. And then we've got TX and RX. Now notice he's got these 1K resistors right here. And the reason for these 1K resistors is this. This TX and RX is going to go to this USB, but he's also going to export these pins out. He may, and I'm trying to remember. Yeah, so see D1, D0, TX, and RX, these pins are exported out as the Arduino interface. Here they are right here. And so, but be careful because he exports them out right here before the resistor. And then he's got these resistors going to the USB. So what this does is this helps if there's a contingency. So if you drag on these lines over here and force it to 0 or 1, if we had this shorted straight across to the USB, you could cause some damage. So the resistor minimizes the current flow, right? So if you've got a 1K resistor and a 5-volt signal, obviously you're going to have very little current, right? You're going to have 5 milliamps is the most that can flow through here. Nothing's going to get damaged, all right, if there's a short. So if you put a 1 here and a 0 here, nothing's going to get damaged, all right? So these get exported out, so that's important also in the design. Okay, so let's go ahead and let's grab this entire piece. Oh, one more little thing. So this 328p AU. So let's make sure, let's go back to here. And here it is here, 328p AU. So this is the last digits here in letters talk about what the packaging is. Let's make sure. 32K, yep, 2K RAM, looks good. These are the TQFPs, okay? So that's, I believe the T stands for thin, quad flat pack. Thin quad flat pack, all right? And it's 7 by 7 millimeter, very nice, very small. All right, so let's go to the page. That's what the IC looks like. And notice it says microchip technology. Don't get confused. They just own Atmel, so that's what that's all about. And then we see some pricing here, so everything's good. Of course, we can get the data sheet and a lot of things here. That's why DigiKey is really nice. Mouser is really nice because you can get all this information right here because it's sometimes hard to find on the own manufacturer's website. All right, so that's the chip that we're going to use, so that's good. So we're all happy. We want to use the surface mount version, which is this QFP. A lot of work we just did. We didn't even do anything. We didn't read the data sheet. We didn't go through the reference manual. We didn't go, we're just talking here. And I'm just kind of letting you know all the things. There's a lot to this, and that's what this is all about. All right. Okay. So here it is right here. And what I'm going to do is I'm going to try and snag, collect, select this entire thing carefully. There we go. And I'm going to get this programming port also. Okay. Talk about that in a minute. All right, so now I'm going to grab this and I'm going to say copy. All right, and I believe if I click out into space now and I go here, and then if I say paste, I right click and I say place, or I say paste, Control V. If I'm lucky, and I'm lucky, good. All right, so this is working. We got the whole thing. Okay, now we can see that this this document's not going to be big enough, right? So what do? We right-click on it. That's one thing. We can also go, and again, there's many ways to do everything here. I think it's project. We can go up to document options, or we can go to templates here, and we'll change it to. Let's try. I think A2 is bigger. Am I right? Yeah. There we go. Okay, so A2 is bigger. We'll just stuff this right here. Okay, so we literally just copied the entire thing from the previous working design. So let's take a look at what I've got here, all right? Okay, so so we've got the V sub C 5 volts, so we got a power supply. We're going to copy in a second and see what we did with that. All right, uh, we've got our crystal here. All right, and now of course we had to find this IC. So this 18 mega IC right there. So if I were to go and say place component, luckily this thing is, because it's an Arduino, it's very, very popular. And we just go to Octopart and we type it in and give it a second to populate. All right, and then we want this AU version. I'm not sure what the difference is between these two. We'd have to look it up. I'll give it a second here, but I didn't use that when I used this one. And just a slightly different version. But anyway, this is the version we use. And here's the chip down here. And again, we can zoom in and then rotate it around. So that's definitely a QFP. It's got a nice little pin 1 marking there. So we like that. And that's the pin. That's the IC, and that's the proper pin out. Again, don't assume anything's right. Copy that, put it on your schematic, then crack open the data sheet and verify that all these pins are in the correct place. All right. So the first thing that you're going to do after you get done doing this is you're going to go back here. You're going to go to your data sheet here, right? And make sure it's right, because wouldn't you hate to spend all the time doing a big design and then the darn thing is wrong? There's a nice block diagram. Here's the DIP package. Here is the MLF. That's not what we want. We want the TQFP. There it is right there. So here is the exact pin out. So we go here and we say, you know, pin 7 is PB6 and this stuff, PB6 and that stuff, right? So we go here, and pin 7 is PB6 and that stuff, right? Pin 13 is PB1, pin 13 is PB1, 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 PB1. Anyone help me out? There it is, pin 13 right there, and it's output compare 1, and so on. You go through this and make sure this is correct. I did, but you know, I'm human. I may have made a mistake also. All right, so always double check, triple check, quadruple check, because money is going in here in time. Okay, so let's look at our design. So here's our design right here. We remember we looked at the reference design. So we need a crystal across pin 7 and pin 8. There's an oscillator inside of the IC. And to finish the oscillator off, you need a crystal, and then you need a couple capacitors to get the phase margin that you need to get the oscillation to happen. And then depending on the manufacturer of the crystal and this and that, you can kind of do a calculation. And these capacitors are going to be roughly from like 18 to 22 picofarads. So we've got 18 picofarads should work. Now, on the crystal, you can do any kind of crystal you want. There's many kinds of forms of crystals, meaning mechanically what they look like. And we looked at this. We did all this crystal stuff. There's surface mount ones, there's through hole, there's different packaging. So this particular crystal right here is this package right here. See this? And the reason I like this is what you can do is you can solder it directly into the PCB, or you can put little teeny tiny pins and you can pull the crystal in and out. And I like doing that so I can overclock the thing, so I can change the crystal and do that. So you can put little pins in there, which is really nice. So anyway, that's what the crystal is going to look like. All right. And let's see, what else here? Look at these capacitors. Okay, so here we go, right? Little capacitor. See, they're surface mount. Same thing here. Surface mount. All right, and let's grab a resistor. There's a resistor. What does it look like? Same thing, surface mount. So again, and we look at the size here someplace, we can find it, 805 right there. Okay, and same thing with these capacitors. If we look here at the size someplace, there it is, 805. Okay, all right, so all I did was I went through and found some components that I liked over in DigiKey maybe, and then made sure it was over in Circuit Maker, and then used those components. And then I'm using the same part, you know, 10 microfarad, 0.1, 22, 0.1 for all of these, using the same footprint and just changing the value. However, be careful. Like, see this 22 microfarad? This is an 805. That's about as big as you're going to get. An 805 size, 22 microfarad is pushing it. You can find a 22 microfarad 805, but they're a little bit expensive. If you wanted a 47, probably could still find it, but you might need a bigger surface mount component, all right, like a 1210. So for example, if we say 22 microfarad, you know, let's look at it. Let's go look at it. Look, say 22 microfarad 0805 cap. All right, so we want, what do we want here? We want a ceramic capacitor, 1951 items. All right, let's just say bulk cut tape. We're going to say in stock. I want RoHS compliant. Okay, and we want 22 microfarad. All right, and the voltage rating, so let's say we're working with this 5-volt system, so let's double it, right, minimum, and any of these will be fine. Okay, so bigger is better, higher voltage is always safer. Okay, let's go there. All right, and then let's see here. Now, these are the temperature coefficients, so you can look all of these things up. Uh, Typically, we want the best temperature coefficient so the capacitor stays the same, and we talked about all this, right? So out of these right here, X5R, I believe, is the best. All right, and then there's also some, these are heights, thickness, right? So I don't really care if it's tall, but it might be important to you. All right, so we got all our parts here. Now let's go ahead and let's do a sort on price. And it looks like about the cheapest we're going to get is about a quarter each, 25 cents each. This is 16 volt X5R. This is a 20% though. That's a little bit sloppy, but we're using these for bypass capacitors, so we don't really care that much. But we might want to go to this one. This little bit more expensive if we want a little bit more accuracy, but I think we would be fine just with this guy right here. So we might select that, right? And we look at what the pricing is for 1,000. Give DigiKey a second here to think. There we go, and it's 6 cents. So the thing doesn't cost anything. So it's 6 cents 1,000. Buy a whole reel of them. Now, if we go to this one, right? How much is that per 1,000? Okay, it's 8 cents. Who cares, right? Buy the better one. All right. So anyway, that's it. We would pick one of these and then go to a circuit maker and see if it had it, and then maybe try another and another until it did. And then if it doesn't have it at all, then we just don't care. We just want something that has the same footprint, and we might say we're going to use this part because we like this part, all right? And we would buy it. Okay, let's get back to the circuit here. All right, so that's how we got all of the components, right? So I went through and did this. Now let's look at the design. So we have our reset line right here, and then in the tool we're using, up here we're using this port. See, that's that port thing, so you can put nice ports, all right, instead of just labeling the wires, right? We can label the wires with a net label, but I like putting ports on things. It just looks neater and it looks nicer. Okay, so then what I did was I went through and copied the Arduino Nano, right? The Arduino Nano, and I looked at the reference design, and I looked at the data sheet all simultaneously to make sure I was kind of doing things right. Now, all right, so if you look here, we've got our V sub C and our V sub C line here. So we've got V sub CC, and what's it going to? It's going to a 22 and a 0.1 microfarad, right? So we've got a large capacitor and a small capacitor is what I decided to do in this case, because I'm going to tie, they're so close, pin 4 and pin 6, they're so close together, I said, hey, I'm going to tie these together, and then we'll have a large and a small bypass rather than two pairs of bypasses. All right. Then on the analog V sub CC, we actually do have a ferrite bead, and then we've got a 10 microfarad and a 0.1. We don't need to put, this 10 is probably overkill, and remember, these numbers are placeholders. I can change them. Maybe 1 microfarad would probably be fine because we're not going to pull a lot of current from the analog power rail, right? But from V sub CC, we are going to pull a lot, and that's what that 22 is for, all right? Now, this ferrite bead, we've talked about these for noise again. You know, that's kind of what it looks like. And then this particular one is an actual part here, part number, which I actually did look up, and it's something I like, I believe. And if we look at it right here, it looks just like a resistor or capacitor, and we look at its specs, it can handle up to half an amp, and it's 1 kilo ohm at 100 megahertz. That's what we want. Remember when I talked about this with ferrite beads? If it's not at least a kilo ohm at 100 megahertz, the thing's kind of useless for noise. Make sure that, and then the current rating is important depending on how much current you want to push through this. So let's say if you had to buy these and you needed an amp, right, you could go ahead and put 2 of these in parallel, not in series, but in parallel. Put 2 of these in parallel. Okay. Now, when you put the 2 in parallel, one thing that you're going to do is the overall impedance is going to cut in half also, right? So you're going to kill the impedance, but you're going to get the current. So you might have to just find one that can handle the higher current, all right? But anyway, it's an option. Okay, let's get back here. So we've got clean power, V sub CC 5 volts coming in here during our analog. And then we got our reset line, which is going to go to our reset switch. Here's our reset switch. So there's basically a little switch, which is, again, a component that I looked up that I liked, right? And if we look this component up right here, this Panasonic part number, let's go take a look. Where'd we get it from? And let's go to DigiKey. And again, this is, hey, this is the process. It's slow. All right, and this is it. So it's a little 11-cent switch, and that's it, little red switch, right? Reset switch. Again, you could do anything you want, you know, put it whatever you want. It's just an off and momentary switch. It's got a certain amount of plunge depth, right? It's got a tactile feel here. You could make it blue, you can make it black, make it green, whatever, all right? But just the switch, all right? Lots of switches will fit in there. All right, what else we got? And then we just got the schematic, the standard design stuff, ground all the grounds, ground the analog ground to the same ground. All right, then we have all our ports. Now, where do I get these names from? I looked at the Arduino design, right? This is what's important. So the Arduino design, we look at what did they name all these things. So they name it D10, D9, D8, A5. This stands for analog. These are analog ports. D7, etc., etc., etc. So we name all these things the same name because we want to export them out to the header, these headers, because the Arduino Nano has these headers. Let's look at it, right? Where to go? It went right here. See this header on top and this header on bottom? Those are all these IOs, and you can see the little labels here. Let me zoom in just a little bit. You can see all the labels here. So we want to kind of mimic that as much as we can and kind of put them on our board. If you look at our board, our final version, where is it here? Here's those headers. Right? And here's where these pins are, 1 to 15 on each side. So that's kind of that little, so it's like an Arduino. So you could actually add things to it. So if you had some Arduino code that said on D6, I'm going to do this, you can just connect a wire to D6 wherever it is on these headers. Okay, we want to keep it as compatible because it's an Arduino. It's a Simonduino, right? Okay, what else do we have? Okay, we've got our programming port here. So these need to, so this is a very certain format. It goes in a very certain order. And this is another place to make mistakes. So you got to visually look at it. So you go to the data sheet, where are the pins? Because when you see 1, 2, 3, 4 here, maybe the labeling of the pins is wrong. Maybe 1, 2, 3, 4, 5, 6, maybe it's labeled like that instead of staggered. So be careful. And I checked this, but maybe I made a mistake. It's easy to make mistakes, so you got to look at the programming port. And remember when we were scrolling down the reference, hardware reference, it showed this. And just make sure when you look at the thing, the pins are in the right place. Okay, so we're assuming that these pins are like this, and then we go look at it. Pin 1, pin 2, pin 3, pin 4, pin 5, pin 6. So then when we get the final version, where is that thing? Where is that programming? Here it is, right here. There is the programming port right there. So MISO, 5, clock, and MOSI. Okay. So MISO, here's 5, clock, MOSI, reset, and ground. So it's the same. All right. So it's the same. Let's go back to it. So that's exactly how it is. So then you need to make sure that the cable on the programmer for the Arduino looks like that. All right. Let's take a little break and look at that. So what are we talking about? Programmer. So after you have the Arduino firmware on the processor, it becomes an Arduino, then over the serial connection, you can program it. But to get the firmware on it, we have to somehow program it directly over that programming port. So we need a programmer. So what we need is this thing. All right, so what we need is AVR MK2, and this is a programmer, which this one I believe is now no longer being manufactured. All right, but here it is here, and yeah, obsolete, whatever. Oh, wait, let me back up. Here it is. You know what, let me show you this. So here's the programmer, and here's what it looks like. It's a little programmer. I've got one over here. Now notice it's got a cable for the computer. It's got all these adapters. And so see like this adapter here. So you can plug stuff in and then fly wire this stuff out. So if you got your connections in different places are wrong, you can program the thing, right? So that's important. So it's not the end of the world if you wire something wrong. You can just fly wire it out and convert it. And here's this right here. And again, this is quantity is 0. So what are you supposed to program these things with? Well, this is fairly old. You can find these things still if you want to look around, but now they have this new Atmel ICE, which stands for in-circuit emulator. So here's the new version that they want to push. The other one was only $19. This one is $100 and it has more features. But if you don't want to spend that much money, you can just type in AVR ISP2, and then let's see here. Well, of course, you can always go on eBay and find something, but we can say replacement, and there's a company who makes one, and I'm trying to find it, Anyway, there's a company who makes a copy of this, or clone. So if you type in this, maybe you type in clone, you can find it. The bottom line is this is going to be used, let's see, this is going to be used, a compatible Atmel and system programmer. This might be it. The whole idea is this would be used to program uh, your processor at a direct level. Oh, and see, and that's exactly what I was talking about right there. Look at that, look at that. So it's showing the 6-pin in-circuit programming connector. So it's MISO, power, clock, MOSI, reset, and ground, right? Did we do that right? And we look here, yep, MISO, power, clock, MOSI, reset, and ground. All right. So anyway, the point is that you can get one of these programmers. Then this programmer communicates with, what does it communicate with? It communicates with Atmel Studio, or something that's compliant with Atmel Studio, which is their big tool. So you would use Atmel Studio or a standalone programmer just to download the initial firmware that makes this thing into an Arduino. But it has to be done through this magical port. Okay? All right. So we need that programming port on there. It needs to be correct, bottom line. Once we have the firmware on there that makes it into an Arduino, then you could remove this if you wanted to, because now the communication goes through the UART. Because the bootloader now, when you power this thing up, it turns into an Arduino. It says, I'm an Arduino, and I'm looking for a program on the UART. And here's the UART. So let's talk about the UART. Okay. So here's our design right here. Now, if you look, I labeled it D0RX and D1TX, just like in the Nano, right? If we can get back over here. D1TX, D0RX, all right? And then after the resistors, the protection resistors, it's just TX and RX, okay? Okay, so so we have the labels there, D0RX, D1TX, all right? Now, then we have the output, same two pins, going through the resistors. Now, if we look at the design here, back here, all right, so they go through the resistors, then we have the same TX and we have the RX, and then the TX line. So this is the TX from the processor and the RX to the processor. So TX from the processor, so TX here, and then it's going to end up going into the RX line of the USB. This is the receiver, and then the transmitter here is going to go out to the receiver here, all right? Now, so let's go back here. Let's see if this is correct, all right? So, so the first thing is we have our receiver line here, RX, that's good. Here's the pin right here, and it goes through here. And then, look, this is labeled TX, all right? So I just noticed this, and I must have changed it doing some dragging and dropping and copying and pasting. But again, this is why you got to check this over and over and over. It's a very easy mistake to make when you start labeling things. So this TX here, right, is really RX, and this RX is TX. So let's just go in there and change that, all right? RX, and go in here and change this. This is TX. All right. So that means that if we go look at our working copies here, this is the working copy, and inside of this working copy right here, this is wrong. So that means the copy we made of it is wrong. So we're just gonna save that right there. All right. And then now what's going to happen is over here in the design, we'll mess with this later. These couple traces are going to have to be ripped and routed again, unless I fixed it in here, which I'm not sure. So we'll check on that in a minute. But let's go to our copy here. So now this is correct right here in this working copy. Now let's go to our final one. All right. So if we look here, we've got TX and it's going to D0RX. This should be RX. All right. And again, when you're doing copying and pasting, and when you're doing your design, it's very easy when I drag this down here to flip these little things and get this. We just have to be very, very careful that things are in the correct place. All right. Now the other thing that the design had was it had this LED right here coming off of D13, the clock line. And if you look here, I've got an LED coming from, let's make sure, from D13, the clock line, which is also on PB5. So it's over here PB5. So that's correct. Look at the orientation of it. So cathode is down to ground. That's correct. Cathode is down to ground. And it's a green reference here, and I'll probably put a green one because it just looks cooler. All right. So that is our entire processor. So that looks correct. Everything looks like it's there. Going back here, that looks like we've got everything that we need except for the power, all right, and some of the stuff over here. There's the it's ICSP in-circuit programming. and all the pins here are the same as ours. All right. So now the next big part would be this USB, but I think what I want to do is I want to go to the 5-volt regulator. All right. So in this case, if we look at this particular design, what does it look like? So let's get back to its design. So it has the 5 volts coming from the USB, or you can directly connect it right here. See this V inline? So you could power the board with that V inline. So if we go back here, here's that V inline. So there's a regulator, gives me a final output of 5 volts here, and then this right here is just a resistor to power for current limiting for this little green LED. All right. And on our design, we have something similar. If we go back to the original, right here, we have, here's our circuit, we've got our voltage regulator, and then we've got our LED here like that. So we got something similar. So the bottom line is we want to power this thing and get 5 volts, and we want to get the power from the USB and from some kind of input. Now, first things first. Okay, so if you look here, he's got VIN coming from here, which is coming from power externally on the board. So first he's making the assumption that this VIN is very, very clean. Now, so you've got this Arduino plugged into your board, you've got 5 volts from someplace. I don't know how clean that, I don't know where it's been, right? Think of it like that. I don't know where you've been. Let's clean you up. So there should be bypass capacitors on this input, and probably a ferrite bead is what I would do to clean that up, because I don't know where this has been. All right, and I wouldn't just put it right in here. Next, he's using an LM1117, which is a fairly primitive voltage regulator, so we're not going to use that either. And then he's got very little bypass, only 1 microfarad on the output. That's bare minimum. This should be a 10 microfarad, and there should be a 0.01 for noise. Again, just very bare minimum. All right. So we're going to do something a little bit more. But at the end of the day, you get an output of 5 volts, which I like calling V sub CC. I don't like calling it just plus 5. Now, there's something else interesting going on here. And so it can be powered by this, but it also can be powered by the USB. So when you have the USB connector connected in, you can power things from USB. That's what's going on here. So we've got all these pins. We're going to talk about this more. But this pin right here is called V-Bus. This can give you up to 500 milliamps. It's on pin 5, and then he puts it through a fuse, and then he calls it VUSB. This is a very common practice that you would do on anything, right? It's not Arduino. Just whenever you connect a USB, you can grab power from it and power your board. So he takes that VUSB, and then he bypasses it right here. So here's the bypass capacitors for that VUSB. All right, and then what he does is he runs it through a diode, a Schottky diode, a protection diode, so the current can only flow this one way. So if you've got 5 volts right here, he doesn't want that 5 volts coming back this way. He just wants this current flowing this way. All right, so that's standard. It's called a power OR, right? So you put a diode there to make sure the current only flows in one direction. So we're going to do that kind of thing also, and then it sums everything up at the 5 volts. So the power comes from the USB, or it comes from over here. So this is, and you might have multiple different ways of getting power, and there might also be a 2.1 millimeter barrel connector, all kinds of things. So we're going to do something just like that. All right. Okay. So in our case, here's what we got. So we have our handy dandy 1294 Keystone connector. This is the 9-volt battery connector. So we're going to use a 9-volt battery, right? Lithium ion, so it has a lot of power and it'll last forever. And then we're going to put a label here, VBAT. We're going to put a protection diode here. Then we're going to call this VIN. Then we're going to put one of our switches, one of our little on-off switches. Then we're going to call this VN switch. Now we're going to have a nice 22 microfarad capacitor here, right? So that battery doesn't have a lot of load on it. We're not constantly going back to the battery. And then we're going to have this regulator here. Then we're going to have 10 microfarad and a 0.1 on the output. Okay. And then what we're going to do is we're going to have this V sub CC 5 volts here. And this is going to be our final power. Now, over here on the USB connector, which we're going to talk about this whole USB situation in a bit. But briefly, we have power coming in from VBus, same kind of thing. Then we have a fuse. We've got a ferrite bead so that noise doesn't get injected in either direction. We've got some bypass capacitors. We've got another diode. So we got a diode here, just like in the Nano's design, to protect the V sub CC. And then we're going to take V sub CC and it sums right here. Okay, so that's our design. So our design can take battery power or lithium ion battery power. Now in ours, we do not have VIN on our header here, right? We don't do that. So this is an output. So this is going to output 5 volts, and this V sub CC 3.3, this one is going to come from over here. It's going to come from the USB. It actually generates a low current V sub CC 3.3 if you wanted to use it. All right, so that's what we're going to use. So we're using this part right here from Microchip, and there are thousands of regulators, thousands of regulators. You don't have to use anything particular, but this is just something that I like. And I'm going to go back here, go to DigiKey, take out the microchip, and it should be able to find it here. All right, here it is. It's a very little small, nice little cute. It's an SOT235. It's called 235 because 2 pins here, 3 pins here, total of 5 pins, right? That's that. And then let's look at some of its specifications. The thing is, it's $1, and it'll take a maximum of 12 volt input. All right, it has only a 0.6 volt dropout at half an amp. All right, which is really, really nice, and it can output half an amp. Okay, so this is a regulator that we're going to use. Now, if we look at the other regulator, so let's look at the regulator from the Nano design. All right, it's this regulator right here. Let me see, can I select this? Let me see if I can select this text. And of course not. LM1117 IMP-X. LM1117 IMP-X. Let's take a quick look at that. LM1117 IMP-X, and we're going to look for the 5 volt version. So we're going to look at the 5 volt version, we'll apply filters. All right, we want the active one. Okay, so here it is here. And okay, so what's the difference here? So it's about the same price, $1 for one, positive fixed. It takes a little bit higher input voltage. All right, it can put out a little bit more current, and at 1.2 volts at 600, it needs a 1.2 volt dropout. So you have to have 1.2 volts above to put out this current. So the dropout is going to be a little bit higher in this one. So I wanted the other one because its dropout's a little bit lower. So we can drop that battery down even lower with that particular IC. But this is it's not bad. It's just kind of an older part, but nothing wrong with it. You could use it also. And because it's a higher current, it's got that little heat sink on it. Okay, so anyway, nothing wrong with it, but I just prefer to use the other one. All right, so there's our design. So let's go ahead, and we're not going to take the USB part yet. We're just going to take this. So let's take all of this piece here, and let's try and copy that. And then I think if we click here, that's kind of what it likes. And then we'll go here, and then we'll paste it. Good, there it is. And now we have it in there. So now we have our entire power supply. All right, we have our entire power supply. We've got our processor, we've got our programming port, we've got our reset switch. So we're doing good. So now what we're going to do is let's go ahead and save all this. Make sure, and you should have been doing that anyway. And then let's come back and let's do the USB stuff. So okay, so let's go here and this work copy. I'm going to commit that since I made that change to TX and RX. We'll double check that later and just make sure that's correct. I don't know how that got flipped around, and this is exactly what happens when you're designing something. Now, of course, I'm doing this for you, and I've designed this for you, and maybe I thought to myself, I'll flip it around and find a bug. I don't remember. But I may have just dragged and copied this as I was designing it and put TX and RX, and I type so fast sometimes. Maybe I put TX, maybe I put RX, maybe I messed it up. And even though I sat there and went through it a bunch of times, I still made the mistake of the mistake I said not to make. But at least I know to look at that. And it's, you gotta be careful. All right, so anyway, let's stop here. And then let's come back and let's work on the USB, and that's a whole another little project unto itself. All right, so I'll see you in the next video. Bye. All right, welcome back. We just took a quick break there, and of course all videos are potentially broken up into multiple parts just for a time constraint. So anyway, now what we're going to do is we're going to go over the USB to serial UART. All right, so let's talk about this just in general, if you have no idea what I'm talking about, so you have some context. All right, so years ago, back in the the 80s and the 90s, all PCs had serial ports, and these are based on, RS-232 is a standard, RS-232A, a very simple protocol. It's got a TX and an RX line and a ground, and then the serial data would clock out on TX and RX. It was an unclocked protocol, so basically it would run at a certain speed, and it was analog in nature, so it was plus and minus 12 volt. And then there's digital TTL, serial, where it's a plus 5 volts and 0 volts represent the ones and the zeros, so it's a little bit easier because the original RS-232 goes 12 volts plus and then minus 12 volts. Okay, now, so that was a really easy interface. So with 3 lines, TX, RX, and ground, you could hook things up to your computer and get things done. When USB came out, Universal Serial Bus, they got rid of this simple interface. Now you can still get PCs and you can surely buy serial ports. For example, you can just go here, go to Google and say serial port card PC. All right, and or you can just go to Amazon and search. So you can see just a bunch of things come up here. Dell. Not a big fan of that, but Newegg. And so here's a little card that has 2 little serial ports on it. Real simple, just plugs into a slot in your PC. This is a PCI, and it's $19, and then now you can do serial, all right? Okay, but if you've got a laptop or a newer PC, you're not going to have that. All right, so what's happened over the past few years here, I don't know, maybe 10 years, companies have come out with USB devices that create a standard digital TTL version of serial. So you can take a USB port, you can connect it to your device, and then the device then gives you out serial, TX and RX and ground. To make that work, though, you need a driver on the computer, whether it's a PC, a Windows PC, or a Mac, or Linux, or whatever. You need a driver that can do that for you, so that you can basically, from some kind of API built into the operating system, say create a serial port, send serial data, and then out of this magical device that's connected to a USB port, which has no serial, which has no standard, RS-232 serial, you get this TX and you get this RX. All right. So again, let's just kind of draw this a little bit. And this is important if you probably know this, but if you don't, it's not going to kill you to review it. All right. So here's the problem. We used to have our PC, all right, and on the PC we used to have a port, and this port was an RS-232 serial port. All right, so this is a serial port, and on this port it had a couple lines that you needed and ground, and then it has other lines because a lot of times this was for modems, right? So it had modem-related things. But TX, RX, and ground, that's basically all you need. So with these 3 wires, you could basically take this over here, take these 3 wires, right? And then, come over here, and then you could build something that understood serial. It could be another PC, could be another PC, could be a microcontroller, could be a computer, some other small computer, could be whatever, could be this other device right here. All right. And that was really easy because it was a really easy protocol and standard. It was just ones and zeros, and that was that. Now the problem is once a USB came out, there's no more serial ports. Now there's a USB port. So now there's a USB port. All right, we're all familiar with USB. So now the problem is you can connect USB ports from computer to computer as long as they have a USB port on the other end. That's great, that's fine, or computer to device, whatever, that's great. But what if you have some little device like a microcontroller based device that has no USB, but what it does have is a serial UART. It's got TX, it's got RX, and of course it's got a ground. How can I get these signals? Well, what you can do is you can take this USB and we can come down here. And then what's been developed is a device, and this is called a USB to serial bridge. And a few companies make this. And what this does is it takes the USB, and then there is a serial device as part of the USB device suite that the bottom line output is you get TX, RX, and then of course there's ground here. So from the microcontroller's point of view, it just sees TX and RX. So then you can basically connect this like this, right? And then you cross connect these things, right? Like that. So TX goes to RX. That's just horrible. I'm just not going to, you know what? That's horrible too. Let's do this. Here we go. There's that. Oops. We want TX to RX, and let's use this color. We want this to this. They have to be cross-connected. Okay. And then grounds are tied together. So here's this ground here, and then these are tied together. All right, so the microcontroller can communicate with TX-RX in serial packets and send, ASCII characters, whatever it wants, and then this thing receives it, and then it puts it into a USB packet and sends it back to the computer. Now, here's the problem. On the computer, we need some kind of driver that understands this. So there's got to be a driver, a USB serial driver plugged into the computer. So here's this driver here. And then here's your application here, and it talks to the driver. And we want that driver to be so that it's transparent. So from your point of view, if you just create a COM port, that driver will give you a USB COM port. So it's completely transparent. So from your programming point of view, you don't have to change your code. So let's say you used an API call in Windows or Linux or Mac that said open up a COM port, and you gave it a number. That API will still work completely untouched because it's the driver's problem to go install itself and announce itself as a COM port so that the computer doesn't know the difference. All right. So when you have one of these USB drivers, one of these USB to serial bridges, and now lots of things have it, and you're probably familiar with this, all right? But if you were to go to your control panel over here, and let me get it over here so we can see it. Here we go, here's my device manager. All right, and if you look inside your control panel here, and we go down here to, it's in different places. Okay, that's not what we want. System devices, keyboards, and of course it's not showing the way I want. All right, so maybe I don't have anything plugged right now that has an FTDI driver. Let me see here. As a matter of fact, here we go. So let me plug something in. So right here, this is got a teeny tiny FTDI, and I'm going to show you this company. So this is a USB to serial bridge. This is a tiny little product. This one's made by Parallax, I believe. Yeah, this is a USB to serial. All right, so now if I plug this in, what's going to happen is the computer is going to detect it. So we got our USB cable here, if you can see this, and I'm going to plug it in. And sometimes this works and sometimes it doesn't because it's got to detect it, the driver's got to get installed properly, and a few things have to happen. All right, so you can see here down at the bottom, driver software, it's installing, so we can click on this. All right, and now the FTDI drivers are part of Windows Update, and they're mostly part of everything now. Mac, Linux, all of these come with these FTDI drivers, which at first you had to manually install, but now they just kind of come with the standard driver install, so it should be able to recognize it. So, all right, so there it goes, and installing driver software was able to find it, ready for use, USB to serial converter. Now, it's still kind of working a little, but what's happened is if you look over here, in ports COM, now I've got a USB serial port COM6. Okay, so now, and there it goes, so now it's got that, and then this little question mark should get off there in a second once it figures this out. Now, what's cool is, let's say that you have a terminal program that you like. Okay, terminal program, and let's see what I have here in this particular installation. So we got those terminals right there. Let me see. Do I have PuTTY here? And I've got PuTTY. All right, so PuTTY's a terminal program that I like. So, so here's PuTTY, which is just a standard terminal program. Then we would go down to serial, and then see here we could say connect to whatever line, and we would just say COM6, and then we say whatever speed we want this at. All right, and then what's going to happen is it's going to negotiate this, and then we're going to be able to get that. And then flow control, we want none. So we could actually communicate like this, or we could go through and we could say Microsoft's hyperterminal. Hyper Terminal, is it still called that? I never use it. I never use it anymore. So lots of different terminal programs, and depending on your, here's Zoc. This is another one. This may not even work because this is a free version of it. Let's see, cancel, create new, set. See if that pops it up. That's not doing what I want to do. Anyway, the whole point is, now if you look at this, it's just COM6. Doesn't know the difference. So you could use this and communicate however you want. So that is what you need. We need something like that to be able to talk to the PC, because the Arduino software communicates to the Arduinos over serial. So it needs this serial port, and so we need this whole bridging system here, transparent, and then the Arduino tool itself communicates through a COM port. Okay, so we need this USB to serial bridge. All right, so we know we need that. All right, now we go, and I'm going to show you this in 1 second. So there's a couple companies, Silicon Labs makes one, FTDI, so we could say USB, and this is going to be something hard to search for, serial bridge, I don't know. Let's see, or maybe we just put USB serial, might be a wiser, less is more, right? USB serial when you're doing searching. Let's see. Okay, interface, here we go. Interface controllers, RF transceivers. All right, let's try interface controllers here. Okay, and let's see. All right, so we'd look through here and see what all these things are doing. So see these interfaces over here? So these are showing different interfaces, all right? So if we put serial interface, for example, all right, I just want serial interface, and well, that only gave us one remaining, and who's this coming from? So this is Microchip, not sure what that does. But anyway, the point is you could search, and there are other companies that make these things, but the primary company that does this is this FTDI. Okay, so FTDI is the primary company that makes these devices. All right, now, so let's go to FTDI. So if we go to FTDI, and not to be confused with the flower company, if you go to ftdi.com, you're going to get confused. Go ftdi.com, unless you're sending flowers to your girlfriend or boyfriend, right? Wrong website. Okay, so this is the website right here, and we go look at their products, and they've got a bunch of products here, all right? So we'll look at ICs, all right, and they've got this line of ICs here, and we go down here to the USV stuff, and they've got this whole series. Before they only had a couple, now they've just got many, too many, a lot of confusing stuff. They make graphics chips now and stuff, all kinds of stuff. But the common chip that you'll see for the FTDI USB to serial bridge chips are these guys down here, this FT232R, and these chips down in this range right here. These are USB to serial bridges. So see, take a look at this 232R here. All right. Now if we go to the design here, so this says FT232R L. I can't remember what the L is, if it's just the package. I'm not sure. We will have to check on that. Discontinued ICs, let's check on that real quick. No, so we're good. So I think the L is just the packaging. All right, so anyway, we go here, and so what is this thing? So this is, we'll go here to this data sheet. All right, and look at this. Again, we want to know what we're hooking up here, right? So I've used this chip many times for many years, and now newer versions of it. So the FT232R is a USB to serial UART interface with the following advanced features and a bunch of stuff, right? And it's got a driver which they wrote royalty-free, so that from the PCs or the Linux or Mac, it just looks like a serial port, which is exactly what you want. It's very advanced, and it supports all these different things, operating systems and versions, all right? And then it shows you kind of a block diagram here. So over here we've got the USB connection, power, and things like that. And then over here we've got basically these are the outputs that give us our digital outputs, right? And these can be programmed, so that they're generically called D-bus and C-bus, all right? But come down here a little bit, and you can kind of read through all the pins here and what they do and so forth and figure this out. And it's just like anything. You got to read the data sheet. And I want you to read this data sheet. You're going to use this chip so much as you get more advanced, you need to know how this thing works. And like I said, there's a couple other companies that make good ones, so you can pick whichever one you want. But what I want to show you is, scroll down here, scroll down. Here is one little reference design. So this is showing USB powered configuration. So this is showing the chip is powered from the USB, right? Showing some bypass. Again, showing something else here, different reference designs. Here's a little bit more of a reference design showing with power switching with a FET, all right? And then another little thing. But what I want to show you is, yeah, and then so here's a simple, so this is, say you want to just make an USB to RS-232 converter. This is kind of, what you do. You've got your USB connector here, which you got to figure out and get one yourself. Here's your power. Here's, how this thing is all set up. And then here's your signals here. All right, now in this case, what this is talking about is if you want true RS-232 plus and minus voltages, that would be this. But if you don't, here's the signals right here, TX and RX, and that's that. And then all these signals, this is request to send, clear to send, data terminal ready, data set ready, data carrier detect, ring detect. This is if you're making a modem. Don't need all those. We just need TX and RX. Okay, then when there's traffic on the thing, in default mode, CBus 0 and CBus 1 will flicker. CBus 0 is TX and CBus 1 is RX. So when there's a TX or RX event, these LEDs, these signals would go on and off, ones and zeros, and then you connect up LEDs, you can see traffic. So this is basically what every one of these little devices has in it, this kind of thing here. With this chip, this has just got one USB port on, one serial port on it. And then here's something else here if you want to do RS-485. They basically give you all these reference designs, okay? Okay, so you have all these reference designs and it's telling you where things can connect and all this. You got to read all this. Here's exactly to a microcontroller, all right? So the RxD goes to the TXT, the microcontroller. The transmit out goes to the receive. The transmit out here goes to the receive here. And then if you want this request to send and clear to send, you could add those hardware handshakes also. All right. Again, if you don't know anything about serial, you got to read about it, right? You need to know how this works. Okay. All right. And then again, like I said, go through this whole thing. Okay. We are going to look at something different than this though. So this is the FT232R. Okay, if we go look at the reference design, it uses an FT232R or RL. Let's see what the whole story is there. All right, so let's go here and check it out. And again, it's a process. This whole thing is a process, not something you're going to do in an hour. This takes hours and hours, hundreds of hours, thousands of hours, sometimes thousands of hours to develop a product. Okay, so here's the product right here. And so this is $4.50 for one of them. It's the FT232RL. And like I said, I believe the L just stands for the package version, but it's the FT232R, which we just looked at the data sheet, which we pop this up. That's it, okay? So there's our data sheet. Okay, so now, and we've got a bunch of snaps here. We'll have to fix that. Let's go back here. Okay, so the browser got a little destabilized. Okay, so we're back here on the FT232 page here, kind of searching. And then what we saw is that the FT232, and we'll FT232RL, and let's go back here and look here. All right, so it's $4.50. Now, if we look at the design, all he requires to hook up this up to an Arduino, we just need TX and RX. Here's RX and here's TX, right? So the TX out goes to the RX of the processor and vice versa. That's all we need, all right? And then one other thing, there's DTR here, data terminal ready. Now, how the Arduino does resets is it needs something to reset it. So what they did originally many years ago is they said, well, how can we talk with serial and do a reset kind of with a trick? And one of those tricks is in the modem interface, there's a bunch of modem lines, data terminal ready, request to send, ring indicator, data set ready, data carrier detect, clear to send. You can read what all those actually mean. but one of them is data terminal ready. And what you can do is if you, in the API, say, take that signal low or high, you can control it from your serial API. Usually they let you talk to the data terminal ready line, okay? Because of that, the designers of the Arduino said, well, what we can do is in the API to reset the Arduino, you can pulse the DTR line, pulse it, and then we'll put a capacitor there, maybe a transistor, something, and then we'll connect that to the reset line. So see, there's a capacitor here, 0.1 microfarad. It goes directly to the reset line right here, okay, right to the reset, and that's it. And now you can also notice there's this pull-up resistor pulling this high. This is a little bit too stiff for my taste, so I'd make that like a 10K. But anyway, so that goes right to the reset line. So all we need is TX, RX, and data terminal ready. We don't need all these other features, right? So this chip is $4.50. Are you kidding me? It's more than the processor costs, right? It's too expensive. It's $4.50, all right? And then at 1,000, it's $265. Can we do better? So if you look through the portfolio on FTDI of all their serial chips, you can find a better chip. Okay, the better chip is right here. So it's the FT231XSR. So let's take this, and I just want to grab the text here. Let's go look at it. All right, so $450 for one of the chip in the reference design. Can we do better? Okay, one is $2. Look at that. All right, so right here. And then at 500, it's $1.60. Anyway, it's half as much. Will it work? All right. Now the cool thing is all the FTDI chips, from the driver's point of view that's running on your PC, it's no different from the driver's point of view. It's just you open up a COM port and you don't know the difference. So that's okay. The question is at the electronics point, down at the other end, at the microcontroller point, do we have all the signals? Are they the right signal levels and all that? I don't know, let's find out. So let's go to the 231X here. Here's its data sheet. Okay, all right. So here's what we're talking about here. So it's a serial UART with full modem and following advanced features. It looks similar. Okay, all right. And you'd have to read through this, right? And I did. I read through this whole thing at one point and looked at it and made sure it was all compatible. All right, and then so if we look at it here, it's got our signals. So it's got our TX, our RX, and there's our data terminal ready. So it's got what we need. All right, so the question is, what's the difference? I can't remember, other than this is newer, all right, and it's cheaper. So I can't remember what the difference is, and the other chip just may be older, or maybe it has one feature this doesn't that no one uses. So anyway, now on TX and RX, let's make sure that those are correct. So TX is the output and RX is the input. All right. So when we were looking at the design and we found that mistake, labeled on the chip, TX is TX, RX is RX. It's not the opposite. So you got to be careful. So somehow I flip those, and we'll talk about that more when we get to it in a second. All right. So here's the chip, and then we have to go look at its reference design, make sure we're doing everything the same. So scroll, scroll, scroll until we can find our reference design. Okay, so here's a reference design. It says, okay, here's your USB port, put your ferrite bead for noise, put some 27 ohm resistors in here for reflections, and then you might want to pull these down with some capacitors also for noise on those lines. Here's your bypass, and then here's this whole situation right here. Take reset, which is active low, pull it high, so this VCCIO, pull it high always, and then this VCCIO, this is the I/O voltage of the chip. So do you want it to be 3.3 volts or do you want it to be 5 volts? That's important. All right. If it's 5 volts, then the outputs, which are not shown in this block, are going to be at that voltage. So you got to be careful of that. So all right, so that's showing us that. All right. And then here is just another little variant here. All right, there's that same switched variant for mixing power supplies. Very similar to the other one, very similar. And then where's the one going to the processor? There was one going directly to processor, and I'm just looking. The LED interface here, you got to look at that so you hook up the LEDs correctly. And these can be reprogrammed, and we don't see it. So I'm just looking for if it shows it here, or if I just looked at all of them and like I said, I've used this many times, so I guess maybe there wasn't just a single nice microcontroller interface version. Okay, doesn't matter. So I read the data sheet. You need to read the data sheet. It's 44 pages. Read it. Okay, so now what I did was from that, I built this. So let's copy this whole thing. All right, so we're going to do that. We're going to say copy. We're going to go to our final design here. And we're going to put it in here, right over here someplace. So we'll say Control V and hope that it fits. Yep. Okay, looks good. Okay. Okay, so here we go. So now let's talk about this thing. All right, so now let's talk about this thing. All right, so we've got our USB to serial chip. We've got our FT231. Again, this is going to be a surface mount chip, obviously. So I had to make sure that Circuit Maker had the footprint of this, and it did, so that was good, so I didn't have to make it. All right, so now let's look at the design, and let's see what's going on here. So the first thing is, we've got V sub CC, and that's what's powering this thing. It's going to V sub CC 5 volts, all right? So one way or another, this is going to get powered either by the V-bus itself or by the regulator power system. So one way or another, that's going to get powered. Okay, this is bypassed right here. Now, look at VCC IO. That's also hooked up to V sub CC, which is hooked up to the 5 volts, which means my IO is going to be at 5 volts, not 3.3 volts, but 5 volts, because the Atmel chip is a 5 volt chip, so we have to make sure that the IO voltages match each other. Otherwise, we need translators. So that's important. And by translators, I don't mean language translators. I mean 3.3 gets converted to 5, 5 gets converted to 3.3, so you don't damage anything. Okay. Next, we've got this 3.3 volt out. The chip has a built-in regulator which can generate this 3.3 volt out, and I think it puts out maybe 50 milliamperes. We'd have to look at the data sheet, right? We could say 3v3, 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 3v3. 3v3, yeah, 50 milliamperes. So it can put out 50 milliamperes, so it's not going to power a bus, but that would power, you know, a microcontroller and some other things that were low power. Okay, next we have the reset line. It's active low, so we just tie that because we don't ever care about resetting the chip itself, right, in this case. Next, what else? We have our grounds, all right. Let's see, anything else? Okay, so here's USB data minus and USB data plus. Those go to the USB port plus and minus pins respectively. Okay, and here they go wrapping around here, and hopefully I did this right. So data minus, data minus, data minus, data minus, data minus goes to data minus, data plus goes to data plus. Another really easy thing to flip around, right? Very easy. There's our 27 ohm like in the spec. Now, we need a USB connector. So the question is, what do I want to use? A micro, a mini, a this, a that? You could put any connector you want. So I like using mini connectors. Micros are just too small and flimsy. So I picked this EDAC. Two reasons why. There was a model in Circuit Maker, and it's cheap and it's good. So if we go here to DigiKey, let's take a look at it. Here it is here. And oops, 6 should be able to find it, or Mouser will have it. There it is right there. So I did some searching, right? It's got board guide, solder retention. It's a nice little connector, and it's unshielded, can handle an amp. So we go here, you know, at 500, it's only 34 cents. Nice little connector, USB mini V, right? Okay, so I could click on it, and I can also see here's its 3D model, right? And flip it around. That's exactly what we want. There's our 5 little, if I can remember, there's each one of these interfaces is slightly different. Yeah, so there's our little pins right there. And again, a really common place to make a mistake is figure out what pins is what on these USB connectors. All right, then we've got a fuse here. Let's talk about this real quick. So the fuse is simply if there's an overcurrent event, a short, something, right? We don't want to blow anything out, so this fuse will open up. So this is a fuse, that polyfuse, that after it opens, it recloses. So heat causes it to open up, and then it resolidifies. So it's you know, resettable. It's called a PTC. And let's see if we can find its part number. Here we go. So it's Borns, which is a common company that I like to get fuses from, and Little Fuse. We've talked about this before. Here it is here. Fuses tend to be a little bit big. So here it is here. So it can handle up to 15 volts, so that's okay. Current max is 100 amps before it just explodes and it's no good. The trip current is 1 amp. So if more than 1 amp flows through this thing for more than 150 milliseconds, it's going to pop. All right, and it'll open up and then it'll reclose. That probably means there was a short. Otherwise, you can maintain 500 milliamps, no problem. Of course, you can change this. So this has got a certain size, and if you scroll over here, the size is an 1812. So that's a pretty big surface mount device, 1812. There's what it looks like. That's what these fuses look like. Very nice and very safe, okay? All right, so we've got our fuse there. We've got a Schottky diode, and all the Schottky diode is just making sure that current only flows in one direction. We've got our bypass capacitors, all right? So everything is as it should be. And then the only other thing is we've got TX going out, and so this TX here, this is an output, goes to RX, and this RX, TX from the processor connects here, right? So each one is opposite, but we got to make sure we got these labeled right now. So here's RX going to RX, and here's TX going to TX. Okay, so I'm happy. Okay, so there is our entire USB to serial bridge. We don't know anything about USB, have no idea how it works, right? We didn't write the driver for it, we didn't do anything, but if you hook this circuit up, at the end of the day, you're going to get TX and RX from the PC. And then on the PC side, some other smart guy took care of writing the driver for you, a virtual COM driver it's called, right? So that when you write an application in C, C++, C#, JavaScript, Python, you name it, and you open a COM port and you grab a COM port, the COM port can be a physical COM port or it can be a virtual COM port via the USB, and you won't know the difference. You won't have to change your coding, which is awesome. Okay, let's come back here. All right, and why do we need this again? Because after we program the bootloader onto the Arduino through the programming port and put the bootloader on there that makes it an Arduino, then we don't use this anymore. When this thing powers up, it says, I want traffic through here. So on the PC, we run the Arduino software, and the Arduino software sends the traffic through the RS-232 through the COM port, which ends up here. But to start the whole process off, it has to reset the processor. How does it do that? It does that through the DTR line, the data terminal ready. It pulses it. And there's a little tiny capacitor because it's an AC pulse, right? Pulse. It goes through the capacitor, hits the reset line, reset N, which just means reset active low. Put an N means active low. Or you can put a bar over things, whatever. And then that'll reset the processor, and the processor will start the bootloader, and that'll be that. Okay, so there is the entire USB section, right? Isn't that cool? So we got our USB, we got TX, we got RX, we got our data terminal ready for reset. One last thing. The traffic here. So CBus 0 is TX and CBus 1 is RX, I hope. So the way it is in default, I believe that's correct. CBus 0 is TX and CBus 1 is RX. Worst comes to worst, the label would be wrong on the silk screen, or you can actually reprogram these chips over USB with a tool from FTDI, and we could actually change that. But I think that's correct. I'm pretty sure it's correct. I looked at the data sheet, but again, I'm not perfect, so I could be wrong. But it's pretty consistent through the different versions. And if we look over here, CBus 0 is going to the RX. So CBus 0 is RX, and then CBus 1 is TX. We go over here. CBus 0 is TX, CBus 0 is RX, and CBus 1 is TX. So these are backward relative to that one. Again, it's so easy to make mistakes. And again, I'm using a different chip here. So this TX and RX also can be flipped around, right? So that's another thing. You can flip the TX and the RX around, which is nice. So if you do put it in backwards, you can program it and flip it around. So maybe I read something, and again, I did this a while ago, so maybe I read something that says something different. But let's take a quick look here. And remember, this is all about this is all about schematic design and PCB layout, and then the other engineering parts of this. This is a much bigger process, right? You have to read these things, you got to go through it, you got to take notes, you got to take engineering notes. I've got countless books here full of notes as I do this stuff, and you need to do that too and keep your engineering notes, right? But anyway, if we look at the pins here, the CBus 0 configurable CBus pin, like I said, it can be what you want, but the default configuration is transmit enable, and CBus 1, the default configuration is, so let's see here. So we got to be careful. Got to be careful here. So this is RX led and this is TX led. So CBus 1 and 2. All right. So we got to be careful here. So we may have made another little mistake. So, and again, I'm copying this so many different times. All right, so we need to make sure we're using the right package first. So what package are we using? Let's make sure of this. So let's go here, back to our design. All right, so we're using this XSR package. Let's double click into here. And let's see here. So this, I believe this is this, they call this SSOP20. SSOP20 package is the package, SSOP20. Okay, so it's the SSOP20 package. And again, let's go through this. This is really good. So here's the SSOP20 package. All right, now here's the QFN package. All right, so we're using the SSOP20 package. All right, so let's be careful. SSOP20 package. This is the package we're using. All right, and on this particular package, we got CBus 0 and CBus 1, CBus 2, CBus 3. Did we do something wrong here? Let's find out. So this is the SSOP pinout descriptions, all right? So let's scroll down here. Now it says that CBus 0 is TXT enable, all right? The configured device default configuration, all right. In table 3.7, we're going to take a look at that. But CBus 1 is RX and CBus 2 is TX. CBus 1 is RX, CBus 2 is TX. So that concerns me. So if we look here, we've got this to 0 and 1. Now we could reprogram this, but I don't like that. So CBus 1 is RX. So CBus 1 is RX. So that's correct. So CBus 1 is RX. But CBus 2 is TX. Here's TX. So this is actually wrong. So let's go here, and we're going to go down here, and we're going to connect this to 2 like that, and close that. And then, so now we don't want to delete this whole wire. So remember what we can do. We can right-click on this. We can say break wire, and we can go here, and we can break the little wire there. All right, and then we can select it and delete it. All right, and then we can just shrink this down. Hopefully it'll cooperate with us. Okay, so that's potentially wrong. So we got TX here, now we got RX, all right? And so now that would be right because the way that this default is, the CBus 0 is this TX enable, all right? So we got to kind of look at that also. So we'll look at that a little bit. And we want to look at table 3.7 also, all right? So let's see, let's go to table 3.7, 3.7, 3.7, 3.7, and this is the process. You got to sit here and go through this stuff and figure it out. Here it is right here, and let's see, configuration control. This isn't really helping us any. All right, so anyway, it looks like we want those pins the way that we had them. That we just made a change for TX and RX. And if we go back down here and go to this SSOP version, CBus, and that's why you got to read this because there's little tidbits here. And here, so see this TX LED can be on any of these pins, RX LED can be on any of these pins, all right? And then enable transmit data for RS-485 mode, all right? So we don't need to worry about that. Now, so we had it on 0 and 1. So we had it on 0 and 1. If we look at his reference design, see he's got his on 0 and 1. Let's see if the default for the FT232RL is 0 and 1, and I bet you it is, and I may have just copied that. So let's go here. And this is the whole thing. We're talking about very, very lots of tiny little minutia details that we got to be careful of. All right, so let's go down. We're going to find the pin out here. All right, so here we go. Yeah, so look at this. So CBus 0 default on this version of the chip is a little bit different. So CBus 0 is TX, CBus 1 is RX. See that? And then CBus 2 is this TX enable. So anyway, I tend to believe that the data sheets are correct, but hey, it's possible they could be wrong. I've seen it before. I can't remember if it's incorrect in a bug in the data sheet, but we're going to assume that it's correct, and we're going to assume that this is right, so that on CBus 1 and 2 is RX and TX respectively, and we're going to design it like that. The good news is if we're wrong, we can go into the chip over USB and actually reprogram this stuff, and that's why this is nice, because anything here that's on the C bus, you can reprogram. All right, and I even believe you can flip TX and RX, and you can flip the polarity of them as well. Okay, so the guys who made this know that this is a problem, and they know that this happens. Okay, so we're going to leave this like this. All right, and then we're going to have to go back and we're going to fix that. I'll go do it inside of here in the work copy. So we'll go back here to the work copy real quick. All right, we're going to go to the work copy and let's go and fix this right here to reflect what we just read. And this is good because what's happening here is we're going through this and we're figuring things out. And you got to do this to make sure that you got everything right, and that's just all there is to it. And so by me going over this design with you, we're finding little errors, and that's great because I want to find errors because it's pretty suspect that I'm perfect, right? I'm not. And so if I don't find any errors, that means I probably made some and I didn't find them. So we're finding some errors, which is good. Okay, so this is now the same here. Okay, so now we're going to go back to our final. Okay. All right, so let's see, we've got our USB, we've got our processor, we've got our power, we've got our LED indicator, we've got our reset switch, we've got our programming port. What else do we need? All right, what else do we need here to copy over? All right, so we've got our audio amplifier, and then we've got our whole input interface here, and we've got our LED bank, okay? So why don't let's stop the video here, and then we're going to come back and let's deal with these three elements, okay? And of course, make sure if you probably are not following along, you're just watching because it'd be too hard to follow along right now. But let's make sure we save everything, commit everything, make sure everything is all synchronized to the cloud. Always keep doing that. I hit Control S constantly at least. Okay, so anyway, all right, so I'll see you in the next video and we'll go add those other three elements. All right, bye. Okay, welcome back, and we're just going through the different subsystems of the Simonduino. So we just finished off, we did the USB, and we found a couple bugs in the design, which the TX and RX were switched here, and then over here, the C-bus lines, the TX and RX were switched. Again, they're just LEDs with labels on it, so obviously when the TX traffic went, we would have seen the other LED blink, but no need to not fix it. Again, that's why you really have to go through this stuff over and over and over and make sure you've got it all correct because it's like you stare at it and it looks right and then something's wrong. Okay, so now right here we're in the working copy, of course, the complete design. So now what I'm going to do is copy over another couple blocks. So let's copy over a couple things here. Why don't we copy the I/O expansion? So this area right here, so what this basically is, these are two headers, 0.1 inch pitch headers. Each one has 15 pins, and the pins are labeled 1 through 15, 1 through 15, and then the associated signals have been attached, connected to each one of those to mimic the Arduino Nano. All right, so let's just do a copy here, and then we're going to go here and paste this in here. We're just going to paste it right above or to the left or something. So let's try putting it right here. Okay, looks good. And then now one thing that we want to do, so we've got this right here, and if you look at this, again, you really want to go through everything to make sure everything is correct. But if we look at this right here, and then we go to the Arduino Nano in our PDF, and we look at the headers, so we can see here that now, of course, J1 and J2 don't mean anything. This is kind of showing the DIP package, kind of the DIP. If you look at the Arduino Nano here, if we can find it, it's kind of in this DIP version, this dual inline package with the chips mounted on here. So it's like a big, a big IC that can plug into a solderless a solderless breadboard. And the signals, the way that they go, one of these is J1 and one of these is J2, and then they're in a certain order. So we're just trying to maintain that order more or less. All right. So basically, we've got D1, D0, reset, then D2. So it's not D0, D1. So it's D1, D0, reset, D2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 on one of the headers. Okay, so let's see what we have here. So we've got D1, D0, reset, and then ground. That's correct on pin 4. Then D2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12. So that's correct. And then on the other one here, starting from pin 1, now here's where we get things a little bit different. So pin 1 is V in. Our pin 1 is, this is V bat. So for example, if we did not plug in a battery here, right, we could plug power into this header, and then it would end up coming in right here. So we could basically do this same kind of thing. So VBAT goes on this side of this diode. So that's what we're calling that. All right. Then we have pin 2 is ground. Pin 2 is ground. Pin 3 is reset. Pin 3 is reset. Pin 4 is V sub CC 5 volts. Then we've got A7654321, 0 and A ref. We've got A7654321, 0 and A ref. There's our analog reference. All right, then on pin 14, we've got 3.3 volts, and pin 15, we've got D13 S clock. There we go, which is the serial clock for the SPI, serial peripheral interface. So that looks good. So that's exactly what we want. All right. And so we copy that in there, so that's good. So that header is basically, that's it, it's done. So if you look at the model of the header, the 3D model, all right, there it is right there, and it looks like one of these things. Now this is a male version. We could just as well use a female version, right? It doesn't matter. So you just get a female, but the footprint will be the same, which is simply, and again we have to play around with, there we go. The footprint is the same, which is just the holes here are 0.1 inch, and they have a certain diameter, which is, I don't know, 30 thousandths or maybe 40 thousandths of an inch in diameter. And you could put a female header in here if you wanted to, no problem. All right. So, but we're just going to start off using this as the model. That's fine. Okay. So now we have our headers. All right. So that's good. Let's go ahead and let's save this. All right. What else do we want to copy over here? Oh, and there was a little bit, we'll swing back to some of this when we kind of do final review. But yeah, here was AREF. So we've got our AREF going to this capacitor to ground. That's actually in the data sheet, so that's correct. And then you can assign a reference voltage for this analog reference from the interface here. So that's actually correct. So that's good. Okay, let's see here. What else do we want to do? Let's go to the working copy. Let's back out here a little bit. All right. I want to do this whole switch in one sitting. We can grab these display LEDs, I think. Yeah. And then here's the amplifier. Let's grab the display LEDs. Okay. So let's grab this section here. All right. Let's go ahead and copy this. Control C doesn't seem to work like it should. Huh. So that's interesting. Now let's see here if I paste it. Will it work? All right, so that worked, so that's good. All right, so again, now here we've got some resistors here. Again, these are all 805 surface mount resistors. And then the LEDs themselves are through-hole LEDs. Now the reason for that is just so they're big and brighter and just, you know, more prevalent. If we use surface mount, they're just not going to be big enough, and we would have to use a larger package to get enough light out of it. And then this can be pushed through some plastic that you design or something like that. Now, they're all, if you look at the models here of all of them, they're all green, and the part number is probably the green one, but one of them exists, which is, these are all Cree parts. So the actual part number, which is here someplace, maybe, hopefully, a unique ID, that's not it. If we go to the Octopart part, that'll do it. So if we were to go to the Octopart part here, so all the LEDs are just copies of each other, and we know that we can find them in all the colors that we need. So if we go here, and we just go to Octopart, all right, so there's the LED. So the whole idea is it's a 5mm round through-hole LED made by Cree, which is a great LED company, optics company. So then what we're going to do later is the footprint is the same. So we'll just get a red one, we'll get a yellow one, we'll get a blue one, and get the proper colors for the Simon itself, which is red, green, blue, and yellow. Okay, so That's all we needed to do was just find one that the tool had, and it did. Now, what's this funny business here? So remember we said we're going to drive these from GPIOs. So here are 4 GPIOs. They happen to be the analog GPIOs, meaning they have analog support on the ATmega IC. So these actually go to A2, A3, A6, and A7. And then if we look at A2, A3, A6, and A7. Okay, so that's on this header. Okay, great. So we can also get to them from there. And then if we go look at the processor, A2, A3, A6, and A7. So A2, A3, A6, and A7. So you might say A6 and A7. Andre, why didn't you just use A2, A3, A4, A5? You know, why'd you skip? Well, the reason I skipped was that on this processor, you notice that each one of these pins has an alternate function. So this is PC0, it's also analog digital C0, right? This is PD0, it's also receive for receive data for a UART. So on these 2 pins right here, A4, A5, this is SDA and SCL. This is the I2C data and clock lines respectively for the I2C support. I2C stands for Integrated Circuit Communications. And we may have briefly talked about it. It's just another serial protocol invented by Bosch, the car company, in the, I don't know, late 70s, early 80s. Anyway, it's a two-wire communication schemes, very similar to SPI, very similar to standard serial. That's annoying, isn't it, the way it keeps popping that up? So I didn't want to put the signals for the LEDs on here because I may want to use this functionality on the header interface and interface something. So that's why I skipped it. So I said, well, I don't want to use A0 and A1 because I like to have those available, right? So let's do A2, A3, A6, and A7. That's like the best of the worst, all right? So kind of like the least amount of damage and impact on the IOs there, okay? All right, so to turn on your LEDs, you'd have to turn those to outputs in your firmware that you would write for your video game, right? And then these would turn on, and that's it. And remember, we're just assuming that the 20 milliampere IO current of the outputs of the GPIOs is sufficient to light these, which it is. And I believe it's 20 milliampere, and how we would figure that out is we would go to the data sheet. Right here, here's the data sheet, the 442-page data sheet. And we would look in the GPIO section. Unfortunately, unless I download this briefly and look in the GPIO section. Let's do that. So we'll just sit here for a second and we will download this. This is okay. And give it a second. Okay, great. And then I'm going to show in folder here. And then what we're going to do is we will drag it over here. And I don't believe I've got a copy of it in here now. So, okay, we'll put it over here. Cross your fingers it doesn't crash. Okay, there it is. So here's the data sheet and a little bit more searchable. So now what we're looking for is the DC characteristics for the GPIOs. So we could go down here to electrical characteristics. We could jump down here and we could say common DC characteristics. Usually is in here. It'll say what the current is. So here we go. So VIL, VIH, remember these things, right? These are voltages though. We want currents. Okay, so V output low. These are voltages. Okay, now these are leakage currents right here. We don't care about that. What we want is the drive. So now here's some interesting things. Even if one of the IOs can support 10 or 20 milliamperes, here's a couple notes. It says the sum of IOH for all ports C0 through C5, D0 through D4, et cetera, should not exceed 100 milliamperes. So the sum of it at any time cannot exceed 100 milliamperes. So that's another constraint. So here's some more notes right here. Although each IO port can sink more than the test conditions, 20 milliamperes or 10 milliamperes at V sub CC 3 volts under steady state conditions, the sum of all should not exceed 100. Okay, so you'd have to read that to know that, which we did, and I know that this is in here, and that's why I showed it to you. Otherwise, you'd blow something up. So the point is that if we're running this IC at 5 volts, and we have this 200 ohm resistor in here, just say 200. We're just going to say we actually left it. 5 volts divided by 200, right? V divided by R. We're going to figure out what the current is. And the current is 25 milliamperes. So these 4 alone, out those GPIO ports, would result in 100 milliamps of current, right? So there's 4 times the 25. There's 100, right there. And we'd have to look to see if those are the same ports that were mentioned inside of this note right here, right? We'd have to look here. So D5 through D7. So anyway, the point is it's probably a little bit much. All right, we don't need that much current. 25 milliamps, you don't need it. So what we're going to do is maybe we just bring this up to, we'll just say 330 ohm. All right, just 330 ohm. And then what you might do is you just might make a note here, 330 ohm, make a note to yourself using the little note tool, right? And say, do not exceed, you know, and right here, if this is 100 milliamps, then we have no current on any of the other GPIO pins noted in this note that the sums can't be greater than that. So you got to be careful, okay? So now, if we do the same calculation, 5 volts divided by 330, we get 15 milliamps, of course, times 4 is 60. And so 60 milliamps is now we've used up a little bit more than half of what our budget is, and that's okay. So I think we'd be okay just putting those resistors inside of there. But again, just be cognizant of it and be aware of it. All right. Okay. Let's see here. So that's the LED bank, and that's all there is to that. So basically, I did a search on DigiKey. I found some LEDs I liked. I looked at their price. I looked at this. I looked at that. I use a lot of Cree LEDs. I also use a lot of King Bright and Light On. Osram, but Cree is real good, real bright. And so that is how we're going to do the LEDs for the Simon, okay, for the lighting. Now, the next big problem is the I/O. Let's get into here. So the next big problem is this whole I/O thing. And then remember I said the whole point was we don't want to use up 8 different lines and hook it up because we'll just run out of GPIO. We just use 4 up for those LEDs, all right? Now, I could have also multiplexed the LEDs, right? But I want to be able to turn them all on simultaneously to do effects, like blink them all or doing a pattern or 2 at a time. And that the game actually has that support where you can press 2 things at once. So we really do need 4 separate GPIOs to do that. All right. Of course, we could still multiplex it and serialize it and do things like that and use less, but 4 GPIOs kind of gets it done, and it's only wastes 1 GPIO really even if you multiplex it. So we'll keep the 4 for that, but this would use too many. So we're going to multiplex this by using this demultiplexer, and since only 1 button can be pressed at once, this method will do the trick here, okay? So this method will do the trick. Now, of course, if we light 2 lights at once, like red and green, and you're supposed to simultaneously press them, this won't work, right? Because we can only detect 1 of these at a time. So that's a constraint we have to put on our firmware. We can't do something where you can light both at once and you have to press them both simultaneously. It's always got to be just 1 at a time. But we can do effects where just maybe for lighting or fun, where they all turn on. All right, so the next thing that I want to do is let's copy this over, and then we're going to actually stop the video real quick, and then we'll do another video where we're going to talk about this design. So let's see if we can grab this thing. All right, so what I'm going to do is I'm going to grab here, and unfortunately, we're going to end up grabbing some other stuff here, but that's okay. We'll just delete it. All right, so we're going to go here. We're going to say copy. Click out there, and we're going to go to our final, and then we need to be able to fit this. Now, so one thing here is I'm already seeing is let's go here. Let me see if I can move this up a little bit, move it up a little bit more. Okay, and why don't we move this up a little bit? We just ran out of room here. All right, and I think this will be okay. Now let's see what happens if we try and place this thing here. All right, so if we place this right here very carefully, now I'm not happy with that. Let's take this and let's just move this over here for a minute. All right, and let's take this whole thing and we'll just move it just a little bit here, maybe move it a little bit up. Okay, and let's take this. We could have just used a bigger sheet, but a bigger sheet's getting a little bit big. Okay, now let's try and place it. Okay, there we go. So just going to place it right here. Okay, now we'll zoom in. This is garbage here. This reset, this is all copies. We want to be careful there. This is a copy. We're going to remove that. All right, and then here's our display stuff. Let's just move this back over here. Okay. Okay, so now let's back out. We got everything on here, so that looks good. All right, so now what we're going to do is we are going to talk about this whole thing here and how this thing works. Okay, so I'll see you in the next video. All right, so we're just moving on with the analysis of the design here. So we just copied the input buttons here and the difficulty switch. So let's talk about how this works. Now, if you recall back a few lectures ago, I discussed the whole point of we want to have, a bunch of different buttons, one for red, green, yellow, blue, and then start, last, longest, and then we've got one extra one since there's 8 here, so this is called OGS. And then we have a difficulty switch, which we can use 1 bit for. If we use 1 GPIO for each one of these, there's going to be like 9 bits total used. So we have to encode them somehow. Now, they're more or less mutually exclusive. So if you press red, you're not going to be pressing start. If you're pressing longest, you're not pressing green, and so forth. So we can kind of get away with a mutually exclusive design. There's lots of ways to encode them. One way would be to serialize them. We could put a serial parallel to serial shift register. That's one way. Another way is to use this kind of encoder, a priority encoder. And how this works is like this. We pull every one of these lines up high here with this 10K pull up. So each one's pulled up high. All right. Then there's a class of ICs. They're called priority encoders. And let's go here. And one of them is the 74HC148. You can go take a look at it here. It's a TTL kind of chip, or in this case, it's a CMOS chip. And at 1,000, it's 13 cents. So very cheap, very cheap. All right. So the cool thing about this is we go to its data sheet here. And in a nutshell, it takes 8 lines and encodes them into 3 lines. Now, how it does that is like this. Here's the truth table. So let's take a look at this. All right, so first thing here, we have some inputs. We've got this EI input here, all right, which if it's high, it doesn't matter what these inputs are doing. If it's low, then we've got this situation here, and then we've got high, 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 if none of the inputs are low. Now, if one of the inputs are low, then we get all lows out. So basically what this does is the first time it sees a low, all right, a low assertion, that's the priority, and it encodes that as a 3-bit pattern. All right, so if none of the inputs are low, so if they're all high, that's this case right here. If they're all high, then the output is high, high, high. All right, high, high, high. All right, now if just one of them is low, let's say the 7th, right, then the output is low, low, low. All right. Now if the 6th bit is low and the 7th bit is high, and all the other ones could be high also, or they could be low, but let's just assume they're all high, that we're only pressing one button. Then we'll get out this pattern, low, low, high. All right, and then and so forth, and so on and so forth. If the 5-bit here is low and the others are high, doesn't matter what these are. So wherever this low is, that's kind of what it's encoding as the priority, and then you get this bit pattern out. So if you look at these bit patterns and look at them in positive logic, this bit pattern right here, when you have no input whatsoever, so you have no input whatsoever, no lows, then we get high, high, high. We get 1, 1, 1 out. All right. If we have the 7th bit low, then we get out 0, 0, 0. Then we get out 1, 2, 3, 4, 5, 6, and then we get out 7 here again. So if you have this case here where you put a low down in the 0 bit, you'll also get this case of high, high, high. Okay. All right. So that's how this is working. Now, if we look over in the design here, we've got the inputs going into each one of these so that we can tell which one of these events is happening. All right. So now looking at this, right, so this is, wired up. So now let's take a look and let's make sure that we've kind of done this correctly. So is there maybe a better way to do it? So if we look at this, we say that, and we look at the data sheet. Let's go back to that data sheet. All right, so we go back to the data sheet here. And so there's 2 cases where we're going to get these highs. So in the case that the input, this EI is high, so if this, If this EI is high, then no matter what, we're always going to get highs out here. Okay, now in the case that EI is low, right, which it stands for enable or something like that, we can look it up, and we have all highs here, so everything is high, we're going to get a high, high, high out. All right. So now the problem with this is we can't differentiate this case here to this case here. So if we have a low in this 0, we're also going to get high, high, high out. So we really want the case, because of these inputs, the way that they're labeled, we care about these cases. So one of these cases, we got to make sure we can discern here, right? So the problem is, since the case where we've got all highs, we get high, 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 and when we've got a low down here also, we're getting high, high, high. We need to be careful about that. So what we kind of need to do is we need to make the buttons that we care about connect to this case right here. So the 7, the 6, the 5, the 4, the 3, the 2, and the 1. And the auxiliary will let connect to the 0, because what's going to happen is if that auxiliary is low, or if the auxiliary is high, we're still going to get a high here, all right? And that's no good. So now looking at our design, all right, and this is, and when you first do this, you kind of look at it and you say, oh, that should be okay, but it's not going to be okay. And the reason why is because on the 7, so here's the 7 input. We've got that red, green, yellow, blue, start, last, longest, and the 0 input here is on this AUX. So we don't really care too much about this AUX because it's on the 0 input. So here's that 0 input right here. All right, so there's the 0 input. And that's where we've got that AUX connected to. So it's connected on the 0 input, right? So here it is here. All right, so that means that when you press this AUX button, right, and then we have this case of everything else is high here, we're going to get all highs out. But also, if you don't press it, you're going to also get all highs out. Then the other cases that we care about are if the 7-bit, the 6-bit, the 5, the 4, the 3, the 2, the 1-bit, if those are asserted low, then we will get these different codes out. So now if we look here, going to 7, 6, 5, 4, 3, 2, 1, those are all connected to the very important things, okay? So this right here is kind of redundant, but we're just going to keep it in there anyway. The whole idea is that this is on this case where we can't really differentiate it exactly, so that's why we're leaving it there. But the important buttons are up here. So we take all of those inputs and we put them into 7, 6, 5, 4, 3, 2, 1, and then 0. And then we've got this EI, which we're asserting low, which we want to assert it low to get the truth table action down here. All right, and then this GS and EO, these are outputs so that you can daisy chain these things together and make these things bigger. We don't need these. So now, if you go look inside the data sheet here, and we look at the names, or you can just look at this design here and you can see these are outputs here. So for example, this E0, this tells you when all of these are all 1 or all 0, right? That E0 goes high. And then the GS happens when all of these are high, and then this input here, you'd have to bubble push and figure out, or nor what's actually happening. But this right here is going to end up going someplace, and it goes down here to this EI. So this EI kind of feeds forward into this GS. So again, you could look and see what the functionality of these things are. And you have to look through here. You got to go, and then it's showing here's how you kind of daisy chain these things together. All right, encoded data active low. All right, and let's see here, and that's about it. So you kind of read through here. Yeah, so they're really not giving you a lot of explanation. You kind of have to look at the design here and then look at the circuit design itself and kind of figure it out. So there's not a bunch of English descriptions. So you could just look at this and kind of figure it out. Bottom line is this is how we want to use this thing. We're just going to use this thing just like this, and this is going to get what we want. Now, on these outputs right here, these are going to go directly into the microcontroller, into the Arduino chip. So our firmware is going to have to decode these things, all right? So we know when we see 000 or 010 or whatever pattern, we know what button is being pressed over here, okay? Then the question is the rest of this hooked up right? Yes, V sub CC is hooked up to V sub CC. We got a bypass capacitor, we got our ground there. These are outputs, don't care about those. And this enable input is grounded, so the whole thing is going to be enabled. Again, you go through and make sure that the pins are all correct, never assume they're correct. And now I can't remember if I made this part or if this was already there. I can't remember, but either way, I would imagine it's already in the system. It's a fairly common part. All right, so that gets us all of our buttons. Okay, these are all our momentary buttons for our gameplay. And looking back at the design, here we go. So this button, this button, this button, this button, this button, this, all these buttons are connected to that priority encoder except for the reset button. That button right there, which one is that button? That one is just right here. That's our manual reset for our processor. Just, you always want to reset. All right, let's talk about the difficulty switch. That's the other thing. So all we want to know here is the thing to the left or to the right. Okay, so you can do this in a couple different ways. So what we could have done is use the center as the kind of the switching point, and then we could put this end to ground, and then we could put this end to V sub CC 5, and then you could switch back and forth. It would connect both circuits. Or we can just pull this up all the time, right? And then if you switch it in this position, then you get a 0. If you put it in the upper position, then you get a default 1 because you're already getting pulled up. Either way would work, so that's fine. And that goes to D8, okay? And then if we look at the design, we look at D8. What does D8 connect to? Here it is here, D8, and this is ICP. This is one, I believe this is a compare line on the processor, so it's not too important for a lot of things, so that's why I use that D8, okay? And that's for that difficulty switch on the system here, which is, I'm calling this mode here. All right, and that's the on and off switch right there that just turns the power on. All right, okay, so that's that. So that's all there is to that. So if you hook this up, you read these lines, you connect them to the processor, you will be able to read them. Now, of course, D5, D6, and D7, right? D5, D67, D5, D67, you can't really do anything with this anymore because they're connected up to that output. So here's the problem. So here's these lines right here, right? And this IC is driving these lines. So if you try and drive these lines here, you're going to create a short circuit. So you can read these lines, you can connect these to something to read from them, all right? But you can't drive them from this interface. You could damage things, all right? So they're kind of useless, right? They've been used, but we still put them here to just be consistent, all right, with the I/O interface. Okay, so that's that. Let's go ahead and save that, commit it. Okay, looks good. And you can see, like I said, this is a complicated project, and that's why it would just take hours and hours and hours if we sat here and part by part did all this. And we just don't have the time. We don't need to do it. We don't need to do it. This isn't a microprocessor, microcontroller architecture class. So like I said, I may do something like that in the future. But this one right here, we're just thinking in electronics mode, just connecting things, reading the data sheets, hooking things up, and just trying to get the functionality we want. All right, so what else is left here? So we've got our interface, we've got our power supply, we've got our power good indicator, we've got our USB. Hopefully we got this TX and RX thing squared away, and this is all correct over here. I'm going to have to go in the working copy and modify that. So when you actually are looking at the class, the working copy will be correct. This time I'm actually going to fix the working copy, and I'm going to go back and fix the original too. So when you make, well, my working copy is my working copy, but I'm going to go fix the original so that's actually correct. All right, let's see. What are we missing? We are missing the audio amplifier. Let's talk about that. All right, so at the end of the day, we want this thing to make sound. All right. Now, we talked about making sound, and we made sound on our little organ on the previous project. And in that case, we just took a square wave out and we put it right into a transistor, the base of a transistor, and amplified it, current amplified it, and just drove it into a speaker. Done. That would work fine. And we could surely do that. If we look up the tones, so what we could do is we could go here and we could say, we could go Google, and we could say Simon electronic game tone frequencies, All right, and reverse engineering, I don't know. What do you think? Right here? Let me see. Let me see if the word freak is here anywhere. Nope, freak is not there. Let's go to the reverse engineering. All right, and hopefully there's nothing on here. Let's see. So looking through here, yeah. So this is actually, yeah, this is actually really good. This is I hadn't seen this before. So this is actually nice. So he's got these two. He's got a normal one and he's got a pocket, and he's kind of reverse engineering. So this is a cool little website. So let's go ahead and you know, this website right here, waitingforfriday.com/p equals 586. I'll make sure to put that in the materials. But what I think here, let's see, let's search for the word tone. All right. There they are. So that's what we wanted right here. So on the full size version, here are the frequencies, right? And we actually needed this. Now, website something based on the primary four notes of the bugle. This case being the actual frequencies should be this. On the full size, the lights are in the opposite order. All right. Constraints of the actors producing duty cycle. So we would read through this and we want to mimic these tones. So we would just mimic these tones in a square wave and we could put them out, a single transistor amplifier, be done with it, and that would be that, right? And we can also look at these. I could get a Simon game, and we could read through this, and I believe it's just a square wave. It's not anything complicated. We'd have to look and see if it is a square wave or a sine wave, but I'm pretty sure it's probably a square wave. Anyway, but what I want you to be able to do ultimately is write some more complicated software, and you could play PWM sound or PDM sound, pulse density modulation, or pulse width modulation, and you can still also just put a square wave through here, and then that way have a filter here, so you could actually play music and more. You could play voice, you could play anything you want through here. So what that means is that in our Arduino firmware, we need to get an Arduino sound library that can put out PWM or PDM sound out through a one of the pins, one of the analog pins, all right? Or excuse me, one of the digital pins, because we're going to do this totally digitally, all right? So it's totally digitally. So PWM is a digital using a duty cycle, and the same with PDM is a digital kind of signal. So with a digital kind of signal, 1 bit, we can actually, make music, right? We've talked about PWM and PDM a little bit. So this is what this helps. So this filter right here filters that so that we can get an analog voltage out of it. And then we take that and we amplify it with this amplifier. And this is a nice amplifier, 1.1 watt. And then we connect our speaker. So the whole point is you can just dump out a square wave in here and you would actually hear it. That would be fine. Or you can put out full PWM sound from a sound library and play samples or music for things as well. So I just want to give that flexibility. Okay, so let's look at this thing. Okay, so let's look at this thing and see what this is all about. So there are many audio amplifiers, countless audio amplifiers with all kinds of different properties. There are different classes. Remember, there's Class A, Class B, Class AB, Class D, Class E, Class F. There's all kinds of classes that do different things and are more efficient, less efficient, and so on. Don't want to get into all that. It's a whole conversation. It's a whole book. It's a whole class. But what we do want to do is look this part up. So let's go do it. And where's DigiKey? Right there. We'll look the part up. That's just some notation. That's the actual part. Okay, so so what I did here was I said, hey, I want to spend so much money. I want it to have certain features. I want it to be Class A, B. I want it to be mono, right? Not stereo, just one channel. Have some features like depop and standby. There's no popping. A little tiny package. It's got to be surface mount. It's got to be cheap. And look at this. At 2,500, it's 18 cents. You can't beat that for a watt. So here it is here. And it's by ISSI. This is a cool company. They make really cool analog stuff. Right, here's the part. And I hope, let me see the data sheet here. I believe this is the data sheet. Yeah. All right, so here's the data sheet here. All right, it'll operate from 2.7 to 5.5. That's great. You can read through this data sheet, which I want you to do. And then it talks about things like at 1.1 watts at 5 volts V sub CC. So that'll be its power output with an 8 ohm load. all right, and the frequency is, say, 1 kilohertz is what you're trying to amplify. So there's always, wattage. When you hear wattage with stereo amplifiers and all that, it's under a certain set of conditions, right? And here's the set of conditions: 1.1 watt, 8 ohm load. That's the speaker impedance, and then frequency. The primary frequency is 1 kilohertz that would be going through there. THD is total harmonic distortion. You can look that up and read it in Wikipedia what that means. All right, and that's about it. So you read through here, read through this thing. It's 11 pages, not too long. All right, not too long. Most of it is just these electrical charts, and then here's kind of the how the bypassing, the decoupling capacitors, and all that stuff works, And then we see these filter equations. There's our filter equations, right? F1 over 2 pi RC, right? That looks familiar, right, for a filter. All right. But what we really care about is just kind of this standard application, typical application, and we want a single-ended input, not differential. So here's what we're doing. So we have our capacitor input. Here's R in. Here's this R feedback, right? Here's our bypass capacitor on our power. Here's our battery. Excuse me. Here is our battery. Here's our speaker connected to our outputs right here. All right. And then also this output is connected back to this feedback. That's where this feedback is coming. So it's a kind of an op-amp configuration here. And then in this case, it's got a 20K and a 20K for RF, for R feedback, and R in is 20K. And the gain in this thing, there's a gains equation, which I'll look for in a second. And then there's this bypass, which they recommend 0.47 to ground, and then the shutdown control, which is just a enable. So here's our input right here. Very, very simple. So we want to copy this. We want to copy this. So let's see what we got here. All right. So this SDB, we're going to tie this high. All right. Then we've got ground, ground. We've got bypass. Connected to pin 3, this input, and then through this capacitor to ground. Right, and we've got input plus, here it is here, and then bypass, and then we've got this capacitor to ground. Now, you look here, and I put 10 microfarad here. Why isn't it 0.47? I believe I read in the data sheet that the larger the capacitor for C bypass, and we can look that up, C bypass, it reduces noise if it's larger. And remember, they always are going to give the cheapest, smallest capacitor so they can say, look, our thing works with this cheap little capacitor, but the bigger one would be better. So if we read through here, let's see here. C bypass has the influence on the total harmonic distortion at lower frequencies, but its function is critical to the final result of the, this is the power supply rejection. With input grounded, if C bypass is lower than 0.47, THD increases at lower frequencies. If C bypass is higher, the benefit on the THD plus N in low frequencies is small, but the benefit of the power supply rejection ratio is substantial. So that's why I made it 10 microfarads, because I wanted that. I wanted to not pay attention to the power supply. So we just amped it up there a little bit, made it 10 microfarads, and that's it. That's why you got to read the data sheet, because there might be little tidbits of information to make it perform a little bit better. All right. Okay, and then we've got Vout plus, that goes to the speaker, and then Vout minus goes to the other end of the speaker, and then Vout minus is coming back through this feedback. Let's make sure we did that right. All right, again, always double check things. So here's Vout minus. That is the output, the negative output, and that goes through the feedback, and then that goes back here to the input on pin 4. And does it? Yes, and then that's where our input is. Okay, and again, it doesn't hurt to make this capacitor much larger, right? This is the input capacitor that's going to block DC. It just creates a filter, and making this larger just gives us a little bit filters down a little bit lower, so we can pass very low frequencies. Okay, all right, and anything else exciting here? That's about it. There's one capacitor you see right here. See the CF? This is C feedback. And if you add a feedback capacitor, it gives this thing a little bit better performance, because what happens is higher frequencies are going to jump over this resistor, and then what's going to happen is you're not going to change your gain. So the gain is going to be a little bit more stable over the frequency range if you add this little capacitor here. So if we search CF, and here it is here. In high frequency region, you can limit the bandwidth by adding a capacitor in parallel with RF. It forms a low pass filter with 3 dB cutoff. FCH is in hertz. So again, you can change the performance of this by putting that little capacitor. We don't need it. We're not worried about it. Okay, so here's the design, and this part I believe was also in Circuit Maker, so I didn't have to make it. So hopefully it's correct. I checked it, of course, and I hope it's correct because I checked it, but check it again. And then here's the final design. So that's it. So we're just going to copy this, and then I said, hey, I can put this on any output, so I put it on this D9, and if we look at D9 over here, what's D9 connected to? Again, it's this. This is output compare 1A and output compare 1B. These are for doing timing things with the timers and the counters in the processor. So I can live without that. So D9 is going to drive audio. So in your firmware, you're going to write your firmware, and you're going to get an Arduino library or do it yourself, and you're going to put the sound out as a square wave or PWM or PDM on that D9 pin. All right, then it's going to be coupled into here. It's going to be filtered, capacitively coupled into this amplifier. The gain is set at 10K and 10K. 10 over 10 equals 1. And you can look, the gain here is, the single-ended gain is someplace. Let's just look for the word gain. Gain. Yeah, here it is here. So the gain is RF over RN. So it's basically, that's the ratio right there, okay, RF over RN. That's why we just want to have those resistors be the same, and we'll get that gain, okay? And we don't need voltage gain, we just need current gain here. So that's why we're making them the same. And 10K and 10K is fine, or 20K and 20K. There's a point, if you make them too small or too large, that they're not going to work good. All right, so let's just stick them at 10 and 10. That should be fine. Okay, so that is our amplifier. So that's how I designed it. And of course, I went through and looked at a bunch of others, and I've used, probably, I don't know if I'd say hundreds of amplifiers in 30 years or so, but I've used dozens. Well, I probably used hundreds actually. So I've used many dozens of amplifiers from different companies, all different kind of variations. And so, you just search for it in DigiKey and you kind of find something that you like. Okay. All right. So let me copy that. Let's go over to our final, and let's put it here someplace. All right. We'll put it right here. And yeah, let's just put it right here. Okay. All right. So there's our amplifier. And the design's already done. Again, everything should be surface mount. We can click on here and we can look and see, surface mount. And then of course, since this is a copy of the work copy, we can just go to the work copy here. Where is it here? There's the PCB version, and we can see everything is surface mount. I don't see anything that's not surface mount other than the mechanicals, right? Everything should be surface mount. I don't see any big resistors or capacitors. I could be blind, so always checking, but only the mechanicals should be through hole. So I think we're good. All right. So now we have the entire design here, and we hope that this is correct. So now what we're going to do is we're just going to save this thing. So this is the final. We'll say commit. All right. Now what I'm going to do now is I'm going to go ahead and since we did a copy and paste, sometimes funky things happen. All right. The question is, did we copy and paste everything? All right. Let's just make sure. Let's go here to this original. Let's back out a little bit. All right, and so does it look like we have everything? Here's our switch, we got our difficulty, we got our LEDs, we got our programming port, we got our processor, we got our reset, we have our amplifier, we have our big USB circuit, we got our power good, we got our regulator. Now what's nice, I think you're starting to see this already. Say you do another design and you need a USB to serial UART. Well, guess what? Just grab this and copy it. Done, right? Same thing. You want to use a voltage regulator? Done, right? And that's the whole idea. And you basically create a portfolio of blocks, of these blocks, and then you can reuse them and make changes. You want to make another Arduino, right? Just grab this. There it is. That's an Arduino. Basically, that's it, other than this USB. Okay, so it looks like we have the whole thing here. All right, so I think we have the whole thing here. And so now what I want to do is we are going to compile it, and the compiling is going to check the nets and check for conflicts and things like that. So we're going to go over here, and I believe we can do it here. Can we do it up here too? Yeah, we can do it up here, or we can press F9. So we're going to say compile PCB project. Okay, and then, okay, now we've got some errors. We've got some warnings here, up here. And then it's saying like NetJ18 contains output pins and bidirectional port objects. All right. So what it doesn't like here is this, is these ports right here, all right, these are bidirectional, all right, and then but yet this is connected to an output only. So it's telling me, hey, you probably didn't want to do that, but I do want to do that because I'm using this label just as I don't want to use the signal labels because, like I said, I don't like using it. I like this. It's kind of a, to me, it's like a port, and I don't want to create another wire label just to identify D5. I just want to use the same port that's over here, that's up here, that's here. But since this has an actual direction, there's a conflict. It doesn't like that, but that's okay. All right, so let's go. Well, let's go back. We lost it. Where did that go? Let's go compile it again. All right, so we compile it again, and let's see. So another error here, error here. These are all the same kinds of things. Again, error contains floating input. Okay, so let's take a look at this floating input. So yeah, so C, and again, sometimes it's really hard to see what this thing is talking about. See these inputs right here? This input, this ring indicator, there's nothing connected to it, right? So it doesn't like that, all right? It's just trying to catch everything for us. It doesn't like that. It doesn't like this. It doesn't like this. It doesn't like this. But we're okay with that. We don't have to connect anything to it. You see the point? But this thing just tells you every little problem, and we look at it and make sure it is a problem or it's not a problem. All right. Now we can go and change these things inside of the error error handling document control, which is hidden here someplace. We can say call that a warning, not an error. So if there's a bidirectional port connected to a output or input, just make it a warning. If there's an unconnected input, just make it a warning. You don't have to go so far to make it an error. So these floating inputs, I don't care. All right, part C1 is not linked to Octopart. All these don't care, don't care, don't care, don't care. None of this matters to us. Unconnected pin, again, these are these unconnected pin. So U35, there's U35, U38, U3, all these are unconnected. I agree they're unconnected, but I know they're unconnected, so I'm okay with it. So now we've created this schematic. We've compiled the schematic, and now that we've compiled it, we could import it into the CAD tool into the PCB layout. So that's the next thing that we're going to do. Now, like I said, we are not going to, in this case, it's just too much work. We're not going to go lay out the whole PCB. It's just going to take too long, and we've already done this enough with the other two things. So we're just gonna import it and go through the process, but I'm not gonna sit here and lay all this stuff out because this will take hours and hours and hours. And even if I just show you the results, I might as well just show you this. All right, so you already know how to do this. It's surface mount now, so you know, it's much easier to place things because they're smaller and you have a lot more space. And then it's just really a matter of where you want things, okay? So again, all we're going to do is we're going to come back in another video, and then we are going to just bring the parts in. In the next video, we'll just bring the parts into a PCB layout and just kind of play with it a little bit, just talk about some stuff. And one thing I want to talk about is how I made this circular PCB. That's important. So we'll make the PCB, and then we'll say, here are all the parts, and then now place them, you know, however you want, so that it looks like a Simon game. Put the switches where you want them, put the buttons where you want them, put the USB where you want it, put all this stuff where you want it. Maybe you look at this and say, Andre, this is stupid. Why do you have the USB there? Why don't you have it up here? Why don't you have it over here by this other port? Yeah, maybe you're right. Okay, so but I'm going to talk about some other things once we just look at this all as a whole. So we're going to look at this one as our reference, but we're going to do a little bit on our version as well. So let's go ahead, stop the video here, and I'll meet you in the next video. And we'll copy everything over to a new PCB so we can kind of do a little bit of layout. In the meantime, I'm going to go check a couple things and make sure there's no more errors or bugs, at least that I notice. Okay, so I'll see you in the next video. Bye. All right, welcome back. We're just getting through this material here on the Simonduino design. So let's see, what are we looking at here? So we've got the schematic again. we're looking at the final version. So so we forked a copy and created the work copy. So we have a copy of the design, the circuit board and the schematic. And then of course the final is just a blank copy, which we've actually been designing into. All right, so in the final copy, we've just got a schematic, and we've been more or less copying and pasting from the working copy because we're just not going to design all this. It's too much. It'd take too long. But we've been talking about all the elements. So now we've gone through everything, and then we found a couple problems, which was the TX and the RX. So this is correct here. So this is D0 RX D1 TX. But when I had copy and pasted down here, see this is TX and it goes to TX and RX goes to RX. I had swapped that somehow. Don't know how I did that because I was trying to make a point of not doing it. Maybe who knows. And then anyway, that RX and TX, so this is TX coming out of the processor. TX coming out of the processor goes into RX going into the serial UART, and then TX from the USB to serial UART goes out to RX of the processor. Bottom line, check, 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 check these things. And then we found another bug that we did not look in the data sheet carefully enough for the FT231, which we're replacing. The FT231, we decided to replace the reference design for the Arduino Nano, which uses an FT232. The only reason people use this FT232 is because they're copying. So the Arduino Nano by Gravitech, whatever, they probably copied this from a previous Arduino, and that was copied from a previous Arduino. And every Arduino kind of uses this FT232 more or less. Many of them do. And so you keep copying this, but no one's looking, is there something newer or better? But the one little detail on this was that TX and RX were on CBus 0 and 1, whereas on the 231, which is, where'd we go? On the 231, CBus 1 and 2 are TX and RX, all right? So we had to go look in the data sheet on that, and we found that out. If we can find that FTDI data sheet, which was, let's see, this one's the 232, right? And then here was the 231, and then we went down, and if we search for CBus 0, all right, and then we can see here CBus 1 and 2, this is RX LED and TX LED, whereas CBus 0 is this TXD enable. All right, so and that's when you're using the RS485 mode, so that's not something we care about. But anyway, so they just shifted these a little bit. If we didn't notice, we would have put them on the wrong place. The good news is you can reprogram all these pins. So one thing a lot of people don't know that work with FTDI chips is they're pretty cool because there's a tool from FTDI, and you can find it on their site. I'm not going to find it right now because it's buried someplace. If you look here, drivers, datasheet, hardware, application, eval, someplace here, there's a little tool, a desktop tool that allows you to communicate to the chip and reconfigure speeds, buffers, I/O pins, and all that. Very, very cool. So that's all we would need to do. So we would have been okay, but we want to be perfect. And the whole thing is I'm glad there's a couple mistakes. If you don't make any mistakes, that's spooky for one thing, but you probably did make mistakes and you didn't know. So if you catch a couple, that's a good thing. All right, so anyway, we went through this whole thing. We know how everything works, and everything is surface mount except the mechanicals. All right, so now what we're going to do is we are not going to lay this entire thing out. Again, it's just way too complicated. We're gonna do a few things with the layout tool, and then we're gonna look at the final version and talk about it. All right, so that's what we're gonna do here because we went through this stuff enough with the previous two examples. So this is really at this point just watching me do layout, which maybe you want to do, but it just takes too long. All right, so what we're going to do now is, so this is the schematic, and if you look here over in the document project pane, we've only got the schematic. So now what I want to do is I want to create a PCB, and I'm going to call it Simonduino Color Match Final dot, and then the PCB, which is CMP PCB doc. All right, so we'll go here, right click, and then we'll say add new to project, add a PCB. All right, and then we have to give this the proper name here. I've got this graphics tablet in front of me. It's kind of hard to type. Simonduino color match final. All right, is that right? Looks good. Okay, so that's going to create that. While it's doing that, we'll let that go do that real quick. And go back here. Okay, so now that we have this document, and if you recall, it just kind of puts up a blank PCB, and typically the PCB, I think it's about 4 by 4 inches. Let's see, if we go here to Tools, and then we go to Distance, all right, and we zoom in a little bit and just kind of get it to give us that corner. There we go. So I can compute the distance. I think it's 4 inches, and it's 3937. So instead of being 4 inches, it's, you know, almost 4 inches, right? So I don't know what they were thinking there, but it should be, you know, 4 inches by 4 inches is what I think they were attempting to do. They just didn't do it correctly. Anyway, so this is your starting PCB. Now, you can make this any shape you want. If you recall, we go to, I think, Home, and then we can go to Board Shape, and then we can do Move Board Shape. We can edit board shape, so we can edit the board shape and just start pulling on these handles and then as you do that, see it creates other handles. So you can do all kinds of funky things, right? But we're not going to do that. What we want to do is we want to redefine the board shape, or we want to define from a selected object. All right, so that's why I figured out, you know, how to do that. Because what we want to do is, let's go over to the working copy, which is a complete version of this. Here's our PCB, and what we want here is we want this thing to be circular, right? So we want a circular PCB here. All right, and so ultimately that's what we want to end up with, right? Because it's a circular game. So we want to make a circular PCB. So I'm going to tell you this is 4 inches by 4 inches. So the radius of this is 2 inches. Okay, so that's what we're looking for, a 2-inch radius. So let's see if we can do that. All right, so what I'm going to do is I'm going to come over here. Now, we could, if we were crazy, we could sit here and start doing this, you know, and start bending these things in and try to make a circle, right? That would be kind of cuckoo. All right, so we're not going to do that. So what we're going to do is we're going to go over to these tools here in place, and we're going to do a full circle. And let's see here, I believe now the way that, so there's typically the board shape. Now, so here's a little piece of information that varies tool to tool. So you know how we have all the different layers, right? We have all the different layers, and we can turn them on and off. And there's the layer stack manager, all right, and you know that shows, you know, the various layers that are important to us. But then there's all these other kinds of layers here: 3D top, 3D bottom, dimensions top, all right, for example. And so and then there's outline. All right, so what we want here is we want to put an object here so that the final files all show, you know, a circular shape. So and then there's dimensions top, dimensions bottom. All right, so that's not it. So I believe in this tool, drill drawing, drill guide. What we're going to do is I'm just going to put this thing. See, if we put it on top layer, this is just going to create copper. So we go here, that created copper for us. That's not what we want. We don't want that circle there. Now, if we go outline, oops, if we select the outline layer, I believe, yeah, and that's not what we want either. Okay, so I played around with this for a minute, and it looks like outline is, we can use outline to do this. All right, so what we're going to do is we're going to select the outline layer. And again, you know, you got to read the manual. Well, there's not too much, there's a bunch of documents online for this program. But I believe this will work. So if we select the outline layer, and we might be able to do this with other layers as well, but the whole idea is we just want it to cut all the layers and keep it inside of a shape. Okay, so I'm going to select the outline layer. Then what we're going to do is we are going to draw a circle here. All right, and the next thing that we're going to do is we're going to manually size the circle here. So see its radius, I'm on its radius right there. I want it to be 4 inches in diameter, so it's a 2000 mil radius. All right, so that's the radius right there. Now what we're going to do is we are going to first edit the board shape, and we're going to make sure that this is big enough, and it's acting weird. Okay, there we go. And we're just going to make this bigger, We're going to make this bigger so the circle is within the square. Okay. All right, so now we have that right there. All right, so now we'll click OK. Now I'm going to select this circle that we created. We created the full circle. We just created it with this outline layer, right? All right, and then I'm going to select it if it'll let me. Okay, it's a 2,000 mil or 2,000 mil radius, which is from side to side, the diameter is 4 inches. That's what we want. Now we go to board shape. Now we say define from selected objects. There's only one object selected, which is a circle. We say define, and there we go. So there's this little outline layer. It's still there. We could delete that now if we wanted to. It wouldn't hurt to do that, but we'll just leave it there. And then if we go to 3, and we go to 3D mode, now we have our circuit board, all right, that we can work with. Okay, so now we can actually start placing things on this circuit board. All right, so let's save that. All right, so there's our 4-inch by 4-inch circuit board. So now if you go look here, we have the same kind of thing. We have this 4-inch by 4-inch, and then you're seeing this top copper here, and then of course there's bottom copper. Those are from the fills, right? So now same kind of thing here. We would come here and then say we want to do a polygon pour, all right? And we would say, double click this, all right. And we're gonna call this, as a matter of fact, let's get on the top layer, all right? And then we'll do a polygon pour, all right? And top layer, we would say top layer ground. So this is when the point when we got to when we're putting down our parts and all that, we would do our fills, and that's how you would do it, right? Now, one thing is we don't have all the parts here yet, right? So we need to import all the parts. So remember how to do that. So the parts are over here in the schematic, and we have to compile this. And when we compile this, everything should, anything that's not linked to Octopart, don't really care. All right, and then we have all these warnings and stuff about the bidirectional ports. If you remember all that stuff, don't really care. Okay, so that's good, so we'll save that. Now, we got to make sure we're on the right project, so we're on the Simonduino Color Match Final. And then I believe we can do it here. There's probably a way to do it here, but instead you go to Project, and then we say Update PCB Document in Simonduino. And what this is going to do is it's going to take all the components from the schematic and it's going to bring them in, right? So we say validate changes first. And again, it's cloud connected, and whenever you do something the first time, it does a bunch of work, and then after that it gets a little bit faster. There's a lot of stuff here. It's pretty big. Okay, and close. All right, and now you can see we got all our components, all nicely put out in this ridiculous manner, all to the right here. All right. So again, what I did was I started grabbing components and then I just kind of placed them on top here, at least, so I can kind of work with stuff a little bit easier, so I can see what's going on, right? You got to do that. And I'm sure there's a configuration or something to get this to work better, so we don't have to do this, because this is just ridiculous. And that it puts it out sideways. I can't imagine having 1,000 or 10,000 components in a design. All right, if you had a gigantic motherboard or something like that, and it just stacking them all to the right like that. Okay, so now we have all the components there. And then now remember we've got the rat's nest here, so we can go to connections. We can say hide all. Now we can see what we're doing. Now the next part of the process is what we do is we go subsystem by subsystem. So we say, here's the voltage regulator, and we collect all the parts of the voltage regulator in one little area. Then we collect all the parts of the Arduino or the ATmega core of the Arduino in one place. Collect all the parts of the USB in one place. Collect all the parts of the amplifier in one place, and so on and so forth, right? Get everything all in one place. So we would sit here and grab all these parts, and this would take about, and I could do this with time lapse, but I'm not going to do it. And we get all these parts and we just put them into blocks. Then at that point, then we start, placing these things down. All right. Now, one of the things one of the things in this particular design is we've got this battery, and obviously this battery is not on the top in the design. It's on the bottom. So we have to flip the component here. All right. So let me figure out how to flip this again real quick. And what we want to do is we want to flip it onto the other side. So right now we're looking at the top side. We're looking at the top copper, right? But what we want to do is we want this on the bottom side. So for example, if I go here and we can look at this right now in 3D and see that all the parts are just kind of laid out there, which is kind of cool. But this component, the battery, is on the top side. So I want to flip it on the bottom side, right? So that's what we want to see how to do that right now. Okay, so played with it for a second, and now I remember how to do this. This is in our tips also. So if you remember this page here, we've got this hackaday.io, which is the tips for using Circuit Maker, which is really useful. If you search in this for flip, XY flips in schematic, right? So that's the flip schematic objects, which really have no real orientation because it's a two-dimensional kind of construct. But what we care about is, and thank you for that, what we care about is flipping things in the PCB. So L does that. So L does flipping, all right? So if we go back to our design here, all right, so what I want to do here is I want to put something on the back of the PCB. All right, so now again, if we go to 3, we can see that everything's on the top side. All right, so what we do is we just zoom into the object and we press L. And then when we do that, notice that the text is backwards. And then what I'll do is I'll put it right here. So now if this is on the back side, when we go to 3D, we'll see it occluded by the printed circuit board. And sure enough, it is. So see, it's occluded. So it's behind it now. And that's exactly what we want. So now we can just take this object and we could put it over here and place it and then go back 3. And now we've got it on the back side, which is exactly what I want. So I move this thing around. Whoa. And then it's on the back side. All right. So that's how you put things on the back side. And again, you may put components on the backside too if you wish, right? There's no reason you can't. Many times when you're doing surface mount devices, there's so many pins on some of these surface mount devices, especially if it's a ball grid array, something like that, you actually have to put components right under. So say if we put the processor, here's the processor, right there, there's a processor. If this had, 1,000 pins on it or a couple hundred pins at least, we put the processor on the top side, but it might have so many bypass capacitors, we might say, let's just put those on the bottom side. And to do that, you basically select these components and then flip them to the other side, and then with the copper on that side, you place the objects, okay? So we don't have to worry about that. In this case, we're not going to put much on the back side. We're going to put the battery on the back side, battery holder, and then if you go look here, what I'm going to do is go into 3D. So we've got the batteries clearly on the back side because it's not showing up on the front side. And then if I flip this thing around here, you will notice the other thing is the speaker connector. So that's on the back side. All right. Now, because the speaker connector is just 2 through holes, right? This is really academic. As long as I have the 2 through holes, I could put the thing on either side. I could physically, when I build the board, put it on the top or bottom. But we want to make the model look like what we're building, so we place it on the back side correctly, right? Okay, and let's mess with this wonderful 3D bizarre interface here, which is unlike anything I've seen before. It just is wonky. All right, so this is kind of, what we're going for here, and we only have those 2 parts on the back side and everything else is on the front side. Then it's really a matter of just placing all these things, okay? So let's go back here and let's turn on the text here and go into multi-layer mode. So you can see this is, fairly complicated. There's a lot of components here, and so how I did this was I basically, section by section, I started off and I said, all right, let's build the, the voltage regulator. All right, let's build here's the amplifier, let's build the voltage regulator, let's build the processor area, right? Let's build the USB section and so forth. And then section by section, I built each one of these and kind of cleaned them up, and then no routing yet. And then once I had everything kind of placed where I wanted it, right, then just start moving things around. And here's the in-circuit programming port, and then here's the kind of expansion header, which has our I/O for the Arduino personality. And then it's just, you kind of look. Now imagine maybe I'm going to put some plastic over this, 3D print something. There's the mode switch, our last, our start, our longest, our on and off. And then here's the reset. And now this resets the whole thing. Now, of course, on a real Simon, there's no reset. You can't reset the hardware. You turn it on and off, but we're going to expose that. And then we have this extra little auxiliary switch, which we may or may not need. And then we've got our LEDs, which of course are going to be really different colors. And then it's just, this just personal preference. And then once you get this all done, then of course you hit the auto route and let it auto route this whole thing. Then we go through it after the auto route is done, and we go fix up our power rails, maybe thicken them up, and then clean up everything. All right. So now, so obviously I've done the auto route. Let me take off. So now it's in single layer mode. So there's the top layer. There's the bottom layer, all right, of the board. And just going through all the layer stack. So let's take a look at this routing and let's see what we like and don't like. All right. So here's the top layer and there's the bottom layer. And you can see the little outline is where the actual PCB will end up being, right? Okay, so let's start with the top layer. And like I said, we're not going to, here's ours right here. We're not going to place all these. It's already done, so this is just too much work. So if you want to do this for an experiment, go right ahead. Again, everything is surface mount. You just, obviously just grab the part, put it on the board, there it is. The thing to remember is with through hole, you punch through to both layers, the top layer and the bottom layer and all the inner layers, which it makes routing a little bit easier. So if you want to route this to the bottom layer, you've got to punch a via and then go to the bottom layer. But again, the tool is going to route for you. All right, so let's go back to here. So now let's just talk about, so the auto router ran, and then I very briefly thickened up some of the traces, right? So you can see here's a V sub CC trace right here. If I zoom in, see here's the V sub CC 5 volt, right? And I just went through here and I thickened these traces up to make them all 20 mil so that our power, anything going to power, was like 20 mil, just so our power routing is thicker, right? And I just did that manually. There's not a lot of it, right? And just went through here and did that, and and selected it all, and just followed it through, and that's it. But and all this different shaping and stuff, I didn't change much of it. Okay. All right. So now what I'd like to do is let's just look at this. So now we let the auto router run. I haven't done a lot to it. Let's just look at it and say, what do we like and what do we don't like, right? And again, the whole point is here, this is very low speed. It's going to work fine, but can we improve it just with some things that are glaring, at us that don't look good? Okay, so let's go through that process right now. All right, so again, I'm going to do this in real time with you, and just talk you through it so you can see the process. All right, let's look at this right here. So you might say, well, why don't I just take a straight line here? Okay, well, if we do that, we go like this. See what happens? We get real close there, and we hit that edge. So that's why this thing is stair-stepped. All right, so it's stair-stepped. So let's undo that. Okay, that's why this is going like this, right? So you have to stair-step it because you want to keep away from that edge. All right. Okay, so now looking through here, the router decided to go through the middle here. Now it would have been nicer if the router could find a way to go outside and then it wouldn't have to go through all of these and then we'd get a full ground here. But again, we're not going to mess with it because we'd have to move too much around. All right. Now let's see here. Here we've got kind of a funny thing. We've got this net 15 and then the router went down here and the router went down here like this. Okay. Now maybe a better approach would have just been go from here to here and then not do this double whammy thing here, right? So we could go to route and we could go here and here like that. Give it a second. All right, and then if we undo, let's undo this so we can see. Yeah, so we just need to make sure that this connects here, and then let me redo it. all right? And then I'll go back to route, and then I can go here, here, repour. Okay, so that's a little bit better. And then as I look at this, this is a capacitor, right? Well, what I could have done here is instead, why not do this? And then now look, so now, and we've still got to, whoa, and we've still got to connect this to this. And now we've just got more coverage over here, right? So we just got this trace farther away, and then we could go in here and then grab this and again straighten it out or bend it a little bit. But the point is we got it away from this capacitor, and we got rid of that little funny island, right? That wasn't helping anybody. Okay, so let's zoom out. All right, now this is our processor, and it's kind of tight. And then there's something that you see here. I'm going to talk about these layers. You see me punching. These are vias, and I punch these through here so that I connect the two ground planes together. See, remember we've got the top and the bottom copper, and all of it is ground filled, right? But where is it actually connected to ground, right? Where is it connected to ground? It's only connected to ground in a couple of places, maybe at the battery over here. So take a look here. So here's the battery connection. Here's the ground for the battery. See, 1, 2, 3, 4. That's on both sides. 1, 2, 3, 4. It's on both sides. That's like one place where it's connected to both. So it's connected right here, but then everywhere else it's not connected to ground. So what we do is we punch vias through here, and we ground stitch the two ground planes together, right? And so what this does is it makes sure that we have a really, really good ground. And then you can see I'm punching vias all over the place. And why I'm doing that is this is the power supply. So I want to make sure that this is really grounded top and bottom. So I punch the vias to connect those ground planes together. Because imagine it like this. And this is going to be kind of hard to show you. Let me draw it. Let me see if I can draw it. And we may have talked about this, but I don't think so. So let's talk about this real quick. This is important enough to discuss. So here's our top layer. So here's our top layer. All right. And we'll just draw it as a rectangle, or a horrible attempt at a rectangle. And there's the top, and the bottom we'll draw as this red layer. Okay. All right, and then these are obviously, you know, right on top of each other. Now, so and we did that wrong. Sorry. The top layer is red in our tool. And the bottom layer is blue. All right, let's come down here, just like this. Try and copy it more or less. Okay, and then now, you know, these corners line up, right? Okay, so these are right on top of each other. Now, when something's on the top layer and it gets grounded here, right? If it's a through hole, that will go all the way through and get grounded here. So then you can imagine there's this channel, right? And the channel is obviously just, it's mils thick, but it connects the ground there and there, right? So we've got this ground connection, all right? And we'll just fill that in. So that's that. So anytime there's anything through hole that connects to ground, right, it punches through to both layers, okay? And we get that connection there, okay? So that's kind of what's happening. Now, when we do the ground fill, right, so let's say that the top is all solid. It's solid copper, right? So the top is all solid copper. All right, and we're just going to draw this like this. We could use the flood fill, but I'm not going to even attempt it with this tool because I don't use this tool ever. And I'll probably end up filling up the whole screen. So I just use it to draw. Normally I use Photoshop and stuff to do art with. Okay, so now we imagine both of these are ground filled or filled with metal. And now they're supposed to be connected to ground. Well, how are they going to get connected to ground? Well, on the top, let's say that the power comes in someplace and here's a ground point. Well, that's going to go right through here and connect to that ground point. So now electrically these boards are both grounded, right? So there's a path right here, through here, down here to ground, and now this whole thing is grounded, right? So you could think of, here's this ground and it's connected to all this, right? And here's this ground and it's connected to all this, right? All that's connected. Okay, but what we really want, so there's only one little point, right? One little point. So what starts happening here is this board has resistance, right? And so when something wants to get back to ground, so let's say that we've got a little circuit over here, right? And I want to get back to ground. I got to run all the way through the board, then I got to run up through the ground to here, right? I don't want to do that. So what I want is the entire board grounded. So what we really want is this. So what we do is we via stitch the board. So we put vias in the board all over it, especially around the edges, because that keeps the field. So there's a field, electric field that goes around like this. When we put this via here, it's very tight instead of billowing out like that. All right, so we via stitch this around the edges, and then all these vias, they punch through. So see, now we get all these grounds. Everywhere we got grounds. I'm just get a little messy here. You get the point. Okay, all these grounds punch through. All those grounds punch through. So we got this whole thing grounded. And then in the interior of the board, let's say we've got a power supply or something, we do the same thing. Around the power supply, we put some grounds on there, right? Because we want to make sure everything is really grounded top and bottom, because I want the plane under it to be grounded. See, when there's a field or when there's a signal, so say we got some signals here, so say there's some signals running, there's a signal and there's a signal. All right, now if we look at this cross-sectionally, what does it look like? It looks like here's a signal trace, here's a signal trace, here's the top copper, it ends right there, right? Top copper, maybe there's some more top copper there. Maybe there's a little sliver of it, right? But these traces here, they're as charge moves through here, right? We're going to have an electric field and a magnetic field, but no matter what, we're going to have coupling, and it's got to couple to someplace, right? It's got to couple, so it's going to have a very hard time coupling to this. What we want is under it, we want ground. That's what the other layer is for. So this gives a nice ground here. So now what happens is we got this nice coupling like this. So these greens are the electric field, all right, or the magnetic field. So it's coupling like that. So that's much better. That's what we want. So we want this blue to be totally grounded, and we want the red to be totally grounded. So traces in the blue, that was a horrible color to pick. Traces in the blue, that's equally as horrible. All right, they have an image up top to ground to. So the whole point is this via stitching you'll see will do two things. One, it's thermal, because now heat can progress through the layers much more evenly, so the board stays evenly heated. Two, it doesn't allow EMI, electromagnetic interference, or noise. It doesn't allow field lines to get way out here. They get stuck and they go straight down and straight up. And then next, it creates an image so that traces, these are a cross-section of traces, it creates an image so that under or above there is a ground plane so that these field lines have a place to couple to, right? Because everything is capacitively coupling to everything. So it's very hard to couple next to you, adjacent, because these things are so thin, but you want it above and below. All right, so that is what's kind of going on there, all right? In a very layman's term explanation. Okay, so that's what you see all these little vias for. So all I did was, it's basically you're just taking a pad. You can do it with pads or vias. You just take it and then you just pop it down and say it's connected to ground, right? So for example, what I can do is I can just grab one of these things, I can copy it and then paste it, and then there it is right there. And then I can say repour, and then give this tool in about an hour. And then when I repoured, in this case, for some reason it didn't have, or when I copied it, it's not copying the grounds. So see, if I select the via and I go over here to net, I make sure I can set it to ground, all right? And then now when I hit enter, it should, yeah, so it's the ground. So now we need to do a repour. So if we, let's just grab a trace and see if we can get it to repour. And it should fill the ground in. There. All right, so be careful. You know, this thing, the way it works, you got to make sure it does a repour. All right, so I'm not going to put that there. All right. So that's what these are for. So around the power supply, around anything that's like, for example, if you have some analog sections, you want to make really sure, here's the amplifier. So these are the capacitors and all that. I want to make sure that this is really isolated and really grounded well. So we put all this around it. Another thing you can actually do, which we're not going to talk about any of this, is isolating, creating ground islands, so that right now, ground is everywhere. So what we really want when we're doing analog sections is you'll put the analog section on an island and then kind of put a border around it so that there's only one exit for ground through a certain channel. And that means that all the noise kind of goes through there, all the signal goes through there, and it can't be affected everywhere else. But that's a whole nother class and a whole nother thing. Just for now, when you're building these boards, put some grounds around wherever your power is coming in, put some ground vias to pop through the other side. Then, you know, you can ideally go around the whole thing and pop vias, you know, at an inch or a centimeter, whatever, around the edge to keep it all quiet. And it just helps with the board staying nice and grounded so that as signals are traveling above or below, they have an image above or below for ground. That's what you're trying to get, and you don't want them having to run back over the copper and then up one little ground line to find an image. That is not what you want. Okay. So again, that's talking about more advanced things that we don't really want to discuss, and it's not going to be a big issue with the slow boards. All right, so let's get back in here, and let's look in here. All right, so right here, obviously, right off the bat, you know, there's a lot of congestion in here, and then we've got traces going through the middle here. Why you don't like that is because you're going to put this big through hole component here, right? There's a lot of stress on here. You know, you're going to be, you know, pulling it in, pulling it out, connecting, doing this. And, you know, I don't mind this trace and this trace, but this trace is a bit close for my comfort, and I'd prefer that it was not here. But again, the auto routers kind of decided to do this. We're kind of stuck with it. But ideally, I'd like to push it out, and then what I'd like is I'd like copper fill around every single one of these, like it is over here. See how this is completely filled here, and then I'd like it completely filled here too. I just want these things isolated because these are big mechanical connectors, and I don't want traces running, you know, inside between the connector if I don't need it. Okay, so and again, if I had room, I'd want to spread all these out and put some copper between them, but you know, I'm kind of stuck. Okay, and then I'm always looking for grounds to make sure they have all four little processes off them. Now over here by the processor, so here's the processor. And here's some, these are ground vias I've popped through here. All right, and then here's an actual capacitor, here's a capacitor, here's a capacitor. We want to make sure these capacitors are grounded. A lot of times after the auto router runs, they might be isolated. So take a look at this ground right here. This is very important. I want to make sure you understand this. So look at this ground. So this is all connected, all connected, all connected, all connected, all connected. The only place it actually gets ground is right through here. If I were to close this off, these would say ground, but then there's no actual ground connection. So all you got to do is clip this little piece of copper and you lose the grounds to your two capacitors here. All right, so that's really bad. So that concerns me. So maybe what I want to do is maybe I want to take this trace here a little bit and maybe I pull it back a little bit like this. Pull it back a little bit like that. All right, now this is a little bit thicker here, and what I really want is I just want this a little bit thicker if I could, but see everything's so tight here, these vias, I'd have to move everything up and really mess around with it, but I just don't like that this is all I have right here. And then down on the bottom, there's no ground getting through here. See, the only place I could get through is this one little area here, and there's probably no way I'm going to get that. I'd have to move this and move these vias. So you see, this is the only ground getting to these capacitors. So in this situation, what you might want to do is pop a via right through here, right, and pick up the bottom ground. But see, it's got an island also. This is a completely isolated piece of copper. It's dead copper, right? So it's metal. It's worth it for a heat sink and some shielding. But other than that, it's dead copper. And so if we pop a via through, it doesn't really help us because it's dead, right? Now maybe we can get this to connect to ground. So see this right here? So actually this, we could get this to connect here, but then we lose it here because it's not connected here. So now you can see you got to follow this stuff and make sure that it's all connected, all right? But this is a really common mistake. So you fill your board and then you got your capacitors and you look at it and you're like, oh, it's connected to ground, but it's actually not, because if this was clipped off right here, there would be no ground on these capacitors. They would just not be working. Okay. All right. So be careful. So there is a ground. I'm not happy with it. It's not very big, but it's all we can do without moving things around. Okay. This is grounded good. This is grounded good. So basically you're making sure there's an escape for all these fills so that everything is actually grounded. All right. That all looks good. This right here, there's probably a, so here's, let's see, I'm not sure what this is right here. We'd have to look at it. Let's take a look. What is that? Oh, okay, so this is a ferrite bead right here. So it's going like this and like this. I'm not a big fan of the way this routed right here. I might want to go through the center here and then go up. I might want to try something like that, just go through the center and go up, because this is just it's kind of like going around it. So, that might be, I might go here and if I can get out of this mode, might go here and just, get rid of this. All right, then go back to route. All right, and then so we want to kind of go here, and then we can go here and go up. There we go. Let the flood fill. Okay, so now we have that. Now we got a little issue here, because now that I'm looking at this, so here comes the 5 volts. So here comes the 5 volts right here. And if this is our filter, then it's going through here to these capacitors. So these traces right here, these should be thick. So let's see here. So let's again take a look here. Let's take a look. So here's our ferrite bead. So here comes our power rail, and then it's going through the ferrite bead. And see this is the ferrite bead, which is filtering the noise, but then this needs to be thick also, because this is carrying our power. Okay, so that's carrying our power, right? So we need to go and thicken that up right now and kind of follow it through and see where it goes, all right? So what I'm going to do is I'm going to do this, and we'll just speed this up so you don't have to watch in total slow motion, all right? Okay, so we've resized the first leg of this. All right, we've resized the first leg of it, and we see the tool is complaining a little bit, so we might have to move things away here. All right, and again, we're completely fine with this. We know that it's going to do this, so we're just going to move things away a little bit. Give ourselves some room here. All right, and then we don't want that to happen. See, we lost that ground there. It can't fill through there anymore. And that's another thing you want to be careful as you make traces bigger. And that's still a little bit thin for my taste. Let's just make it one more. And again, it's a slow process. And, I was talking to a friend of mine yesterday who's been designing a board, and, he's just like, yeah, it's taken a year to get it all done, because it's just, you tweak it, you test it, you do this. It's a long process, and we're trying to do it in a matter of minutes here. All right. And so we might want to pull this over here a little bit. Okay. All right. So then if we look here, this is here, and then it's kind of, and again, we are fighting with this tool, always fighting with being able to select things correctly. And so right there, C2, Yep, that's the correct layer, and we need to make that 20. All right, so now we got that 20. And now see this trace here, down here? This is the same trace. That's our power trace. So now we have to continue with this trace and thicken this one up. So we'll make that 20. And then repour. All right, and then that trace jumps. That trace jumps to another layer, and it goes right here. Okay, so this is just going to this pad. All right, so you know, we can surely always thicken up. And again, very hard to select things. We can always make these a little bit bigger, like maybe 15. All right, the pads that actually go into the power. Okay, so all right. Okay, so we got that, and so this is this net C62. C62 is actually the power, and I believe it's coming in. It goes into two different places, if I recall. C62, C62. Yeah. So here's the normal V sub CC right here. This is this V sub CC5, and then this this pad right here. So this is interesting because this is this signal right here, and then it's going into pin 18. Let's see, what is pin 18? So let's go to pin 18, take a look here. All right, so let's go to pin 18 of our design. Pin 18, and looking around, so this is, yeah, this is the analog V sub CC. So this is why this is going through this other filter, right? And you know, sometimes you got to look and remember what you were doing. So it really does only go to one place. It's just this analog filtered signal, and it's got a ferrite bead on it just to keep it clean. So there's really only one place it's going. So so that's okay. So that's good. And now we've got that nice analog signal with a nice fat trace, which is going through this filter, and it's got these capacitors. So we're happy with that. And so now we can back away. And the tool is complaining because we've made it bigger than what's in the rules, right? But that's okay. All right. Okay, so now we fatten that up, so I'm happy about that. Now, one thing, let's see here. Is there anything else? Not really. All right, now here's another problem. So pin 3 is a ground, right? Pin 5 is a ground. So you can see we're getting ground here. We're getting ground here. But they went through here, right? And then it went up into here, and then it's an island. It's an island. So you see why I had to punch these vias through here so I could get ground to the other side. And see, here's the vias on the other side, and now they're on the blue side getting ground. So these grounds would not have had any ground, even though they're connected to the ground plane. The ground plane is not connected to ground unless I punched these vias through here. Now this one via here, this one, I might be able to slide it a little bit, maybe here. All right, slide it that way a little bit, and then see if we can get this to close up a little bit, right? Now, of course, remember every time you move something, we want to get a repour, and sometimes it doesn't do it itself. So you gotta mess with it a little bit. Let's see, go here, let's go here, and okay, that's definitely not what I wanted. Let's try this. Let's just move this down. All right, now we'll get a repour. Okay, and oh, good. And then see, I was able to get that fourth process out of there. And then we still have, and then on the bottom here, we need to get a repour also, which I don't know why it didn't repour. It should have repoured. Let's move this. I guess not. There. Okay, so that's good. So we have a nice 4 process, and by process I mean these 4 little tracks. Ground. So now this is actually grounded. So the chip is actually grounded. So this is a big problem. When you put your surface mount ICs down, now if they're through hole, normally that through hole ground is going to go through both layers, right? Or however many layers you have, it's going to get grounded. But when you're doing surface mount, a lot of times it will fill into the ground plane, but then there's no ground to the ground plane. So that's what these Vias are for also. Ideally, we wished that this would have filled through here and we wouldn't have to mess with these vias, but we have to because it didn't. All right. So again, let's zoom in and see, can we find any other grounds? I think there's only a couple grounds on the chip. So maybe one more, yeah, right here. And you can see here's a ground here. And I popped a couple vias through here anyway, but now is this island isolated? So if we go through here, we can get through here. Here we go, here we go, here we go. Let's zoom out. So you can see probably, yeah. So this is all, so this actually is grounded. It floods out and it gets out there. But, you know, but still, it's got to run quite a bit to get to ground. So we pop these vias right through here, and now we have a good, strong ground by the ground signal itself. Okay, so that's what you're always looking for. All right, another thing also you can do. Right now, you've got this tiny little ground process going here. This is part of the tool when it's connecting things to ground, but no one said we can't make this line thicker. So if we want to thicken this ground up, which I always do, we go here and just pop a trace right on it. All right. Now I've actually put a trace on top of it. Now I can select the trace and I can thicken it up. Let's make that ground good. There. Now the ground is 20 mils, so that's a nice thick ground, right? You don't have to make the pin thin. Same thing over here, right? Let's just do that too. Why use these teeny tiny little pins? So let's go here, pop a ground, and might as well do it here while we got it. Pop a ground, okay, escape. Now you can see the traces there. Now we'll select the trace and then we'll go and make it 20 mil. Get a nice thick ground there. And again, the selection is always a pain. Be careful, take your time. There we go. Now, I don't want to select anything. So now we got the grounds are really grounded on that IC. No need to make them all thin like the 10 mil standard tracking, right? Make them thick, okay? All right. Let's see here. Let's go ahead and let's save this. And this is, remember, we're messing with the work copy right now. So we're actually messing with the work copy. I'm just going to do a save here and I'm going to just commit everything. So the work copy, we've actually modified the work copy from the original, which doesn't have these changes, but that's okay. That's okay. You know, you can access the work copy and the original from my Circuit Maker stuff, so you can do whatever you want to do. Okay, so let's keep working here. All right, so now we got those nice grounds on there, so we zoom in. All right, and we look, is there any other ground? No, no. And of course we're violating things, but we know we're violating it. We did it purposely. All right, so those are some modifications that we made. Okay, now over here, we got this V sub CC line coming in here. Power lines, now typically you'll hear people say use 45-degree turns for signals instead of 90s for a number of different reasons. I say it inside of my book, there's an impedance change and this and that. Only at really ultra high frequencies does that matter too much. It's kind of been proven now and shown that 90s are not bad, but mechanically they're not good. 90 degrees are never good mechanically. There's stress at that corner, so I never do it. I always use 45s unless it's a power line. Power lines are so big and bulky, the signal is very slow, right? So you don't really care. And then if you notice, these things are rounded anyway. So on power lines, you'll see me not bend them all the time at 45, all right? So they're fine if they're just at 90, that's fine. And we could go put a 45 in here if we wanted to, and it'd probably be a little bit prettier. But on power lines, they can be kind of more squarish. All right. So again, we're just looking around. Does anything look really bad? Can we move something to give it a little bit more room? Here, for example, this is kind of messy here. You got this thing Ying off, and I didn't do this, the router did it. You got it Ying off and coming off this right here. You know, maybe there'd be a better way to do this, right? So maybe we could come here and then, you know, move things around. And then this trace is on the right side of this via here, or this post, this pad. So we could put it through the middle here and maybe route it a little bit straighter. You know, let's give that a try. We can drag this around. There we go. We drag that around like that. Okay. And then what we can do is, and that kind of gives this gives this a little bit more, you know, openness. And then what we might do is we might come here and then go like this, and then go like this, and go like that. And then we'll see repour. All right, and you know, maybe that looks a little bit messy. Maybe pull this down here a little bit. Just always trying to give yourself more room, right? Again, it's not changing anything electrically really. It's just this was a little bit cramped. And then up here you see we got this little problem here. Maybe I can move that down there, fix that. You know, and it's a process. It takes time. You know, you got to sit here and you got to do this. And just kind of go through it thing by thing and keep looking around. Can I move this a little? Can I move that a little? Is that in a good place? You know, like this trace right here. It's weaseling around here, you know, and then it's cutting off these pins. They're not being used, you know, thankfully, but if they were, we'd have to route into it, so that would be difficult. And then here's our ground. Here's our ground here. We got two grounds on this thing. So this is going to ground, this is going to ground. So we got a good ground here, so I'm happy. But, you know, I might not like this here and not getting that fourth process out there. So I might want to move this over out here and pop a V and jump over if I had to, because I want that ground. I really want things grounded always. You really want all four of those processes for your grounds, all right? Okay, looking over here, I'm never a fan of this. I don't like anything coming in at an angle because this is creating a, you know, there's this small angle here and this large angle here, and there's lots of reasons mechanically you don't like this because there's going to be a different amount of stress strain on these two things as it heats, right? So what I might do again is I might grab this and see if I can do this. Oh, see if I can get it to come in like that, repour. And then what I'll do is I got to fix it. And then over here, we got all this funny business. So maybe I move this out and then repour. Again, we're letting this auto routing, this kind of magical routing system kind of help us do this. But so maybe what I want now is I'll do this. And I'm just giving myself some room here to work, right? And then unfortunately, every time it does this fill, it's very slow. All right, and now finally we get to where I want, which I think you can see, checkmate. There it is. So now I don't have that coming in at that angle. You want things to hit at 90 degrees ideally, all right, into pads. And so now we've got room, that looks better, I'm happy with that. You want them to come straight into things, ideally, okay? That's what you're kind of looking for. And we got some funny business here, it's a little bit off center, but that's okay. That's okay. We got all our fat lines here and our power rails, our switch, all fat. We've got all of these little through holes. This right here, not too much of a fan of what's going on here. I'd rather center it. Let's just center that, right? Everything's symmetrical. Symmetry is always good. Okay, good. And this this section down here, again, this looks real clean. Again, could I get rid of this? Now, so this is, so you see this 5 is coming right inside of here, right? And it's real tight. So, you know, the question is, could I do that? Whoa, could I? You can't just stop. You got to do the repour, then undo the entire process. Okay, so let's zoom in here. There we go. Can I get this? Yeah, let me do this. You can see where I'm going with this. Watch for a second here. Again, I don't like things tight around pins. Can't escape it. You got to do it. Which I didn't want to do that. Okay, let's see. Can I grab this? There we go. All I'm trying to do is let this fill get around here and just not hug this thing so tightly. All right, because it's a power line, and you know what? I don't want it to short. All right, and let's see if I can grab this, and can I put this a little bit over? I'm still coming in right there. That's okay. And let me just give it one little kiss. There we go. Okay, so that's a little bit better, right? Because now we got a little bit more ground, a little bit more space. I personally prefer that. All right, we can see there's a little step right there. That's fine. We got good ground here, so this all looks good. All right, like I said, I went through this a little bit just to find some of the major glaring problems that the router put in there. This line right here, I might want to just bring it down a little bit. Now remember, as you're doing this, as you're fixing things up, you can see the layer that's under it, right? And be careful. So for example, uh, as you're routing things and you see what's under it, you may not want to put something on top of something, especially if they're parallel. Remember, you're going to get noise, you're going to get crosstalk on things if they're parallel. If they're perpendicular, you won't, all right? So if you have to run signals by each other, run them perpendicularly. Don't run them parallel if possible unless they're buses or whatever. So just kind of, be aware of that. You don't want crosstalk. Usually you're not going to get too much crosstalk through the board, but if you've got some important lines running on top and important lines running on bottom, if you can, put them apart from each other, right? Or put them perpendicular, right? If you can. Okay, so now we're on the bottom layer here, and we're just gonna wrap this up. We're not gonna do much more here. So again, we're just looking at the bottom layer. Is there anything that's just really glaring, sticking out at us? We got an island right here. We got this island. I might be able to pull this line over here and get this to not do an island. So let's see real quick. And again, it's doing this funky thing. Let me grab it. Let me try and grab it here. No. Let me try and grab the whole thing. Let me see if I can grab it here. Yeah, that's not cooperating with me. Anyway, what we might have to do is go and close it off right here. Let's try this. Let's go here. Double click. All right. Just put a new trace in. Now what I'm going to do is I'm going to try and pull this line. I want this ground to come here and grab this island, all right? So what I'm going to do is I'm going to go up like this, move this up here. And again, very slow process. And okay, we just crashed the tool many times just trying to move that stuff around. So again, these tools are very complex and they are prone to crashing. And the whole idea was we're just trying to get this ground fill to fill here without doing what it just did here, which is create this, which is lose this other process. Now, I believe that is just yeah, so this is just a via. So I could, if I want, I can probably just move this over and move it over one, and it's not letting me because, so I got to be careful here. There we go, there we go. This is because the snap grid that it's on, and this is always a problem. So what I'm going to do here is I'm going to put this down to 1 mil, and now I should be able to move this where I want, and it's still not allowing me completely. All right, I'm going to put it right there. I'm going to go back to 5 mil, and sometimes you got to do that to get this stuff to cooperate. So now what I'm going to do is I'm just going to take this trace and I'm going to move it back. That'll let a fill happen. All right, and then I'm going to put it back here again. All right, and then we're going to hope we get that ground. Okay, so we got the ground, so we're happy. On the top layer, we got to also do this. So what I'm going to do is I'm just going to move this trace here to get a repour. And then I'm looking for this ground to stay the same and look good. It does. Okay, so so now what we did was, the goal was we saw that this was an island. I didn't want it to be an island, so now it's connected to all this, and so now it's all connected to ground, and everything over here is okay. And again, this is complicated. It takes a long time. It's a pain in the butt, and you're going to crash this tool potentially. Now see this ground fill right here? I'd like it to be connected to here, so I think I can just pull this out and probably one click, and then look, I got it to ground fill through there. So again, any place you can get that ground to fill through, do it. All right, and so this isn't too bad, other than some of this, these grounding issues. Again, here you can see we've got these grounds, and then if we pull this trace too low, we would lose those. So maybe if you want this ground to go around here, you can move this trace up. But over here, this is very congested in this area here, and now the tool is acting really weird when I'm zooming. So this is really congested. Not much you can do there. All right, so we're okay there. Over here, Okay. Again, any place you got through holes, if you can move stuff away from the through holes, do it. So here, I'm gonna just move this a couple little clicks over, and then now this trace, I'll move it over here, right? Just back it off anything by these through holes, because you know there's always going to be stress and strain through the through holes, and it's a good place for shorts to happen, all right, as you're soldering and so forth, and as parts are being placed. Here, not much else we can do here. Again, we could play with this and try and get a little bit more fill, but for the most part, it's okay, all right? And that's about it. So again, you know, if you were to route this manually, this would take you many, 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 many hours, depending how you know how good you are at it. So we want to use the auto router. Now, when you start getting into high-speed boards and all that, you got to route it yourself, the whole thing. You can route pieces of it with the auto router, and you can surely make rules to teach it and show it how to route high-speed traces or this or that, but it only can do a little bit at a time. And I mean, honestly, I've never seen an auto router that can do a high-speed board properly. It just can't. So you got to do it yourself. All right. So anyway, but for these kind of boards and the stuff you're doing, use the auto router, then go back through it, clean it up, and thicken up any traces. Put these little ground vias in or thermal vias in, and again, you can go around the whole board about every inch or centimeter, and pop vias also, just to make the board completely closed. All right, and I didn't do that. I'll leave that to you. Let's see, is there anything else? I think that is about it. So we got this. So now this is the working copy again. So on the working copy again, we've been messing with. Let's put that back on the top layer here. Put this back on the top layer, and then let's turn everything on. We'll go to 3 here. So basically, that's kind of, so this working copy now has been kind of edited. So this, you could manufacture this. This would work. The original color match game, I think I went into it also. So let's see here real quick. If I go into here, and let's save and close all these documents here. We're very confused. We got so many things open. Let's close that one. Let's close that one. Let's close that one. Okay, now let's get to this one here, which is the schematic. And if we go look at this one, I actually did RX goes to RX, TX goes to TX. So if you were to fork the original, you'll be okay. And then we fix this. And then in the original circuit board, I believe I fixed it also. I'm pretty sure that I did. These signals here. So these are the LED signals. And taking a look here. And the tool is really acting. It's really getting ready to destabilize. So 5, 6, 7, 8, 9. So pin 10. Yeah, I think that's right. I think that's right. All right. Anyway, all right. So let's go back to the working copy. Let's close this up. Let's close this up. Let's close this up. Let's close this up. All right, so the working copy has everything done. Of course, if you want to do this whole thing yourself, you've got kind of your final copy, which in the circuit board, there's nothing. We haven't placed anything because we already have the working copy that has everything done, right? And the next thing now, so now we're done. All right, so now we're done. And we've got the other two projects, the final versions of both, or we can take the original versions of both. And the same thing with this, we can take the original version of this or the work copy, and we can then generate manufacturing files. Okay, so that's what the next video is going to be about, our series of videos. Now that we've figured out how to do PCB schematic design and PCB layout, we know how to pick parts, we know how to do all this stuff, some of the thought process, and you know, you got to design a bunch of boards to get good at it. Design about 10 boards. By then, you will have got the hang of it, I guarantee it. Now we're going to learn how to generate the Gerber files and get everything ready for manufacturing. And we'll do it on the magic wand and generate the Gerber files and generate all these Gerber files from all these things and then get them ready for manufacturing and then go onto a website and upload them and look at the We're not going to build anything or manufacture it, right? But we're going to see the process and see the bidding and the quoting and how we change things, all right? So that'll be fun. So anyway, I will see you in the next video or series of videos and we're going to do that. All right, so I'll see you then. Bye. All right, welcome back everybody, and we are on more or less the last lecture or series of lectures, depending how I break it up, and we're going to be talking about generating the manufacturing files for our circuit boards that we've been so diligently working on for the past lectures and discussions that we've been having. So when we started doing the circuit maker stuff and talking about it, we talked a lot about Gerber files and how a circuit board is made and that kind of thing. So we've already been over that. I'm not going to do it again. You can go back and review the lectures if you skipped around and just went to this part. So what we are going to do is we're going to take a look at all three of our circuit boards that we made, and we're going to go ahead and generate the manufacturing files, the Gerber files, and then we are going to go to 3 or 4 different vendors. We're not going to do this for every single board, but we'll go to 3 or 4 different PCB vendors just so you can kind of see some different pricing and this and that and kind of see the process. All right, so let's just jump right into this. So you should have your circuit maker open, and what we're going to be looking at is the Magic Wand, of course, the 555 timer organ, and then the Simon-Duino. So we're going to be looking at the final design on the Magic Wand, the final design on the 555 timer, but on the Simon-Duino, we're not going to look at the final design because if you remember, we didn't lay it all out because it's just too big and complicated. We just made a forked copy of the primary copy that I developed and called it the work copy. And so we're just going to, so you would have made a work copy that has the whole design, the schematic, and the PCB. And we're going to use that as our model to generate Gerber files. All right, so I'm not going to do a lot of editing on this video, so we're just going to see what happens. And, and I don't, in the first place anyway, do a lot of editing because I want you to see the mistakes and problems because stuff just doesn't go right, and you need to see how to, deal with it. So we'll just see how this goes. All right, so first thing is, let's get the first one we did was the Magic Wand. All right, so let's go ahead, and what I'm going to do here is close these documents so I don't confuse myself. All right, so we're going to get the Magic Wand up. So let's get the schematic up, and we will get the PCB layout up. All right, now, so homework. So before we start doing all this stuff, what I want you to do is you can go to the circuit maker site and you can go to documentation, and there's some videos on generating Gerber files. They're very, very short. I don't want to lose this page because I want you to see this page, but if we go to documentation and we go here to Video Vault, well, you know what, I guess the one that I'm looking at is actually what we're interested in. So let's let Circuit Maker put that page back up. All right, so obviously I'll give you this link in the text file for the lecture, but it's called From Idea to Manufacture, Driving a PCB Design Through Circuit Maker. So it was made a year ago from the time of this video roughly. So I want you to go through this, and this is really long, and it talks about kind of everything we've been talking about with the whole circuit maker coverage in the class. But what we're really interested in here is once we get down to generating the Gerber files. But I still want you to read through this. There's lots of good tips in here, lots of things that I didn't say in class and so forth. So it can't hurt you to read this. It'd probably take a couple hours to read. But anyway, once we get down to, I think it's right around here, and this is just designing everything, still designing, and then viewing your board in 3D. Okay, ready, generating manufacturing output. So it's the last little 10% of this scroll. So here's where it, starts talking about how to generate the Gerber files and how to do that. So there's a few dialogues that we need to set up, and like anything, we can go nuts with this. This is a big tool, right? This is Altium's cut down version of their big tool, and so this really does take years to master, and there's so much to it. So we don't need all that. We're just going to do the bare minimum here. But anyway, I do want you to read this, all right? And then I'm going to do a preview of a couple things. Let's see here. I believe it's here. Yeah, there's a page on OshPark. So this is a fairly popular low-cost PCB manufacturing house. I don't use it because they have delays and their circuit board technology is not that advanced. If you want to do something a little bit more advanced, then the cost is high and so forth. But if you're doing little small things and they have some specials, that it's kind of a low-cost, cheap place to do things. But anyway, what's nice about it, there's a page here, and it talks about some common problems that you might have when submitting a PCB manufacturing file. So we're going to read through this when we get to that point. All right. And then what I've got here is I've got a few different PCB manufacturers. Now there's probably thousands. I exaggerate a lot when I say things to make a point, but there's hundreds of PCB manufacturers at least, but there's probably thousands, honestly. There may be even tens of thousands. Just in China, there must be thousands. So anyway, PCB Fab Express used them many times. Pentalogic used them many times. PCB Cart used them many times. OshPark, like I said, I don't really use that. And then Gold Phoenix is a total absolute Chinese manufacturing website, but I've used them many times also, and many of the American sites actually go through China and they send stuff off to China, obviously, but this is just straight up, you're talking to China, and they're very reliable and very low cost. But the interesting thing is, if you build 5 boards, it might cost, $500. But if you build 1,000 boards, it'll cost $100. So you got to build a lot of boards, and it's actually cheaper. So you want to try that out. But anyway, the point is, and we're going to get to this, you want to try a bunch of different places and quote it out, and then you want to find a place that makes really good boards and consistently sends you good stuff on time, has good customer support. So these are some starting points. We'll get to that. We'll get to those. All right, but let's get back to the tool here. Okay, so we've designed this thing, and now what's nice is we're always in embedded engineer mode, but there's different kinds of work here. There's firmware work, there's schematic work, there's simulation, there's prototyping, and then there's PCB layout, right? There's all these different facets of this thing, and of course we want to be able to do it all, like Tony Stark does. But when you're doing one specific task, you can kind of forget these other things and kind of focus on what you're trying to do. So right now, I don't care what this board is. I'm way beyond that, right? It's a magic wand, whatever it does. We are way beyond caring. All we care about is we have this circuit board right here, and I'll zoom in a little bit. So there's our circuit board, all right? And we want to manufacture this thing. And at this point, we just want to manufacture the circuit board. We're going to personally assemble it. Well, we would, hypothetically, meaning we would buy the parts, stuff them in here, and solder them. All right, so let's press number 3 here. And there's our circuit board here. And let's try and tweak it around a little bit and zoom in, zoom out. There we go. So there's our circuit board. So we would order these printed circuit boards, and maybe we would get 3 of them or 5 of them. That's typically what you do to begin with. You get 3 to 5 of them. One of them you probably just destroy accidentally. Maybe one of them is broken somehow. It's got a bad trace. Something's wrong with it. And then so if you buy 3 to 5, you usually have one that works out and is going to work for you, so you can test it. You always want to test everything. All right, so we need the circuit board, and then we would buy all the parts, and then we would sit and solder it together. Simple as that. Now, you surely can have this manufactured if you want to. All right, but it'd be fairly costly, and again, it depends what your time is worth. If your time is if you're not doing anything, then great, do it yourself. But if you're really, really busy and you're making $250 an hour as a lawyer, or 400 or 500 or 600 like most lawyers make an hour, then it's probably not worth your time to do that. It's probably better just to pay $500 and have a board assembled. Okay, so anyway, you figure that out for yourself. But what you want to do is you want to assemble these yourself so you get the hang of it. Okay, so we've got our circuit board, and so now we want to generate Gerber files. Okay, so we're going to kind of do a couple things to the board first to make sure that it's okay. All right, so before we go generating any Gerber files, we would have already gone here to home and we would have done our design rule check, right? We want to make sure the whole board is correct. So let's do our design rule check. So I'm going to reset error markers, all right? And then I'm going to go ahead and click design rule check. And then remember, we really haven't set up all these design rules, all right? We're just letting them sit and be default. And many of them we're going to get warnings on because we're violating how close something is or whatever. But those we can usually look at and say, oh, that's okay because it's talking about text being on something or something like that. Okay, all right, so we're just going to leave all these checked and we're going to just hit run design rule check. And then sure enough, we get this nice thing here. Error 0, warning 0, rule violations 120. All right, and those rule violations. So we really care about errors. If there's any error, we got to fix that. Warnings, we might care about. Rule violations, we are concerned. Why are we getting these? But they're not going to stop us from manufacturing it. Okay, so we look down here and we see where these things are coming from. So we got 59 of them with constraint. This 10 mil, 12 mil, 12 mil. And remember, we're getting that from we made the power traces thicker manually. So that's understandable. And then this right here, silk to solder screen mask clearance. This is just talking about the text. The overlay text is too close to the solder mask. Don't care. It's just text, just drawn on there, painted on there. Don't care. It's not going to change the functionality. But some people, that might be a bad thing. You don't want that text to be obscured. So that's what that rule is for. But we could have turned it off, but we just leave it on. And then silk to silk clearance, same thing. Two drawn on items on the overlay are too close. But again, it's not functional. It's just an image. It's paint. All right. 120, don't care. Good. What we really care about are those errors and warnings. Don't have any of them, so we can close this. Goodbye. Good night. All right. Now, we are ready to generate the Gerber files. So let's just real quick, little refresh. Gerber files is a format created by a company in the 80s or whatever. We went through all this. We looked on Wikipedia and all that. It was a small company. They came up with a file format called Gerber, and I think the company's name was Gerber. Maybe I'm wrong. But anyway, it was just a file format. It just caught on, and it's a format that describes these printed circuit boards and all the different aspects of them. And there's been a couple different versions of Gerber file up until now, and now we're using kind of the latest Gerber file, and so we need to generate these Gerber files, okay? And it's just like anything. It's like a bitmap file. It's like a MP3 file. It's just a file format, a certain specification, really designed for two-dimensional plotters, okay? And drills and cutting implements, because that's what you kind of use to make circuit boards. All right, so if you remember, let's take a quick here. Let's see here. I think, give this thing a second. Yeah. So remember we talked about, so this is the layer stack manager. This is just showing our board cross-sectionally, right? There's the top overlay, that's the text, the top solder, that's a mask, right? And then there's the top layer, and then this dielectric, which is just this core material, the bottom layer, which is another copper layer, then the bottom solder mask and the bottom overlay. So these boards are two-layer boards, and this is called the stack up, or the layer stack. And the whole idea is we have to generate a Gerber file that describes the two-dimensional image for every one of these layers. All right, and then they're named in a certain way with certain file extensions so that CAD tools and manufacturing tools can read them, right? Now, also, when you send your files to a manufacturer, they're not just going to give these to some computer and it's going to like print out circuit boards. A human being is going to look at them always. Even though you can just give them to a computer, someone will review these, all right? So luckily, if there's errors, they'll usually be caught. Not design errors in your schematic, they don't know about that. But if you made some big mistake or you're missing a file, right, you're missing the top copper or something like that, they'll tell you, right? So there's some modicum of a safety net. But anyway, you want to make sure you got all this stuff right. So we need the two-dimensional images for each one of these layers, right? And these images are in a certain file format, Gerber, all right? And then we also need, the board has a bunch of holes in it, right? And we look at the board and it's got all these holes, and these holes have different diameters. So we've got all these through holes that have to be drilled into the board, and then we have vias, which in this board we may not even have a single via because we were able to route without doing it. So in this board, all the holes are the same size, and I don't even think there's a single via in this whole board. It's so simple, right? But anyway, there could be 10, 20, 30, there could be 100 different hole sizes. So there's another thing called a drill file, and the drill file describes the size of the diameters of these holes and then the positions of all these holes. So there's a drill file also, right? And then finally, there's one last file. Kind of, we're talking about classes of files, and each one of these there might be many, many small files that make up, the drill file that make up the Gerber files. The last file is the pick and place file. And so now, say if you want full automation, you want robots to build these boards. So we have the Gerber file, which also has this drill file, and then we have a pick and place file, which is another file, so that a robot with a little manipulator arm can go grab a part and put it on the board. Okay, and that's the pick and place file. So it's basically a bunch of coordinates that say where to move stuff, where to place these components and their orientation. Okay, and that along with the vision system of the robot, it will grab a part and place it, make sure it's all perfect and all that. All right, we don't need to worry about the pick and place file right now because we're not manufacturing anything. But if you are, you're going to have to generate that. Okay, now, so let's see here. So let's go to, and there's always many ways to do this. So we can go to project here, and let's see which one. Yeah, let's see. I want to go. So if you look here in outputs, you've got NC drill files, you've got Gerber files, you got all this. But if we go to project, we can also click generate outputs here. All right, and it wants me to save the project, I guess because I moved it around. I've moved the board around. So let's save this. Okay, now, so this is the main dialog that allows you to generate output. So we're going to use this one. You can go to that other, if we escape out of here and we go here, we can go and do these separately, but instead we're just going to go to this project and we're going to do generate outputs. All right, and we have to save it again. Redundantly and needlessly. Okay, now let's talk about all these different things here. All right, first thing, bill of materials. Well, we know what this is. So the bill of materials is all the components inside of our design. The problem with this is, and I will rarely use a bill of materials generated from a tool to send to a manufacturer. I may generate it so I can use it as a starting point to make a proper bill of materials. But when you get to professional level manufacturing of products, an ASCII file is not going to cut it. You're going to have to make sure you have every single little thing, pictures of things, directions, instructions, comments, and all that. And sometimes these tools have fields for you to enter that stuff in, but it's just much easier just to get kind of a gross list in a text file, import that into like an Excel file, and then build a proper bill of materials, which I've already shown you, and then show pictures of things. What does this look like? What does that look like? Hey, you can replace this part with this part. These parts are generic. This part needs to be 1%. You gotta explain all this in this bill of material. All right, and then there's also a manufacturing document that describes how do you build this thing. Just talk to the engineers. Talk to them, make a video, and you got to do that stuff, and then you'll never have any failures and never have any problems. The more information, the better. All right, a lot of rookie and newbie engineers, they generate a BOM out of one of these tools. They give them Gerber files, a drill file. They send it off, and they believe these people are like mind readers. They're not. They get thousands of boards to manufacture. They don't have enough information. So send them a big bill of materials. Send them a document that describes what is it we're making. Show them a picture. What does it do? Make them a video. Show them the stuff. Explain it to them, and then they can say, oh, I know what we're doing now. It only takes them a few minutes to read through this or watch the video, and then they have so much more context. They will make less mistakes. And when it's your money, you should be concerned. Okay. So we've got two things here. If we click it over here, it will generate it and create it, put it into this manufacturing package, which is just going to be a zip file. All right, so first let's go to configure here for the bill of materials. Configure. And give it a second. It's got to go to the cloud, and it's got to talk to some fairies and some gremlins. There we go. Okay, so now what it's showing you here is it's showing here's all our parts. And they may be a little bit hard to see, but let me kind of open this up a little bit. There we go. And maybe a little bit more here. A little bit more. Just trying to create some space here. All right, so anyway, you see the point here. So this is what it's saying, it's going to kind of generate for you. And there's the quantity, and I want the part number. All right, so it's going to generate something like this. Now, one problem is, now look here on the left. So these are the part values here. And so we've got kind of comments, we've got the description, right? 100 nanofarad, 100 nanofarad. And so many of these, like these 100 nanofarad, because it's grabbing the actual part, it's not what we wanted. See, we wanted a 0.1 microfarad here. Here, we're not sure what we want. We want a 1 to 10 microfarad, right? But over here, it's grabbing the generic description, which is always the same because we use the same capacitor and just copied it a bunch of times, knowing that we were going to change it. So that's the point that I'm making. This BOM is not correct. It's not accurate because we haven't finished kind of figuring out what parts we want. But it's a good starting point, right? So if you were to print this thing out and get the text file, you could use this, import it into Excel, and then start modifying these things and making them correct so that they're totally accurate. Then you could also, for every one of these, create a link to DigiKey or Mouser or Octopart, whatever. So when the person clicked on it, they'd actually see the part. So they're seeing exactly what you want. But anyway, so this is the bill of materials, right? We're not going to generate it. There's all kinds of settings here. You mess around, do whatever you want. So you can generate that as part of your manufacturing package, right? We're not going to put that in there because we're not manufacturing anything. We're only making the printed circuit board. All right, schematic print. Again, the whole point of this is it shows the schematics. So when they're building this thing, they have an idea of what the circuit is. And the reason why that's important, say on the bill of materials, it has a part, they're not sure what this is. Maybe the part number is wrong, maybe this, maybe that, who knows. But if they can look on the schematic, they can see, oh, it's a transistor. Got it. It's an NPN transistor. For some reason, it just said PN here. The N was left off. And so on and so forth, and they can look at it and they can see what you were trying to do. Then they can either call you or they can just do something and make a decision on their own, but it gives them more information. Some people don't want to send the schematic because they think they're going to steal it. Let me give you some advice. Everyone can steal everything and reverse engineer anything. So I wouldn't worry too much about it because to make profit off your ideas, they have to basically build a business and support it and do all that, and they're not going to do that. So don't worry about, everyone's very worried about IP. Don't be worried about it. Just let the people build the thing and give them the information they need. Again, we're not going to put this in there because we just need Gerber files, all right? And then there's all these different things here. And then fabrication, that's where we're our part that we're really interested in. But let's skip down for a second to assembly. And here's that pick and place. Let me see, can I make this window bigger? No, that would be too convenient. So assembly generates the pick and place of files. So let's hit configure on that. And then in this, there's not much to it. CSV, comma separated file, or just pure text. Do you want it imperial, English, or do you want it metric? Okay. I'll tell you one thing. The whole world kind of sticks with imperial, English system. And that's just the way it is. I hate the English system. I like the metric system. So does anybody that went to school since the 70s up. But somehow this imperial system is just, it's just so, the whole world's so invested in it with their tools and everything that we just are kind of stuck with it. Probably, I hope not till 2050, but probably. All right, so that's a pick and place file. Again, assembly drawings are just you can take a look here showing how something might go together. We're not going to do that. Validation, you want to send them the design rules. Now, this last thing is kind of interesting. Export step. You may not know what step is. This is a 3D file format, so they can actually have the 3D model of the board. And the reason why this is important, let's see here. Go here to configure. And there we go. So, prefer simple bodies, export simple bodies, generic 3D bodies, all these different things here. And you can experiment with this. So what you can do is you can export a step model as part of your manufacturing package. Then they could see a full 3D model. When we put this in 3D, they could see that. But why this is also very useful is now say you have a mechanical engineer or an industrial engineer, and he or she is going to build the plastics or the enclosure that goes around this, make something really pretty that looks nice, right? So you would export the step model for them. because maybe they don't, they don't use this tool. They're not electrical or embedded engineers. They're industrial or mechanical engineers. They don't use this CAD tool. They use a different CAD tool. So we export that file, that step file, which is a 3D file format, very generic. Then they can import it to SolidWorks or whatever their tool is that they like using. And then they can build something around it and build the plastics, and it'll fit perfectly. So that's what that is for. We don't need it. Okay, so that's what all those things are for. Okay, now let's get to what is important. We need the Gerber files. Those are the files that have the actual layers, the artwork for each one of the layers. And the artwork is in a vector file format. It's like in a plotter format, okay, like G-code, right? If you're familiar with CNC machines, very similar. Okay, then we have this NC drill files. What does NC stand for? Numerically controlled. It just means there was a time where somebody was like eyeballing things and drilling holes with a drill press. Now it's numerically controlled. It just means a machine and a robot moves a head around, on an XY plane and drills the holes. Obviously, right? It's 20, whatever it is when you're watching this, 2017, 18, 19, whatever. So that's what that means. We need those. This ODB ++ files, this is just another file format which we're not going to use. Open database format. It's just a way of encapsulating all of this data in a different format. Not going to use it. Report board stack, again, this is just describing what the stack of the boards look like. They don't use this. They could look at it, but again, we don't care about it. So all we care about are the Gerber files and the NC drill files. But we need to configure these things before we shoot this thing off and generate it, right? So let's look and configure. Okay. All right, so let's start with general. All right, so in general here, inches and millimeters, we want this in inches, and then there's a resolution here. So this is talking about how many decimal places of resolution. Now, if it's too low, you won't have enough resolution to resolve your design, meaning you've got something on a thousandth of an inch and you don't have enough resolution. So you increase the resolution. Now you got enough. And then you say, well, why not give it another decimal place of resolution? That would be fine. However, some tools at some manufacturers will get confused if you give it more resolution. So if you have more decimal places of resolution, it shouldn't. Their parser, the text parser that analyzes these files, should be smart enough, but it's not. So you have to look at the manufacturer a lot of times, and it'll say we can take a 2.4, and if you look through here, this is 2.4 is 0.1 mil resolution, or 0.1 of a thousandth of an inch, right, or a 10,000th of an inch. 2.5 is 0.01 or a 100,000th of an inch, right? So they'll tell you what to put it in, and if you put it in the wrong value, it'll mess the board up. Okay, so, but most of them, 2.4 will suffice, and let's look at 2.4. It has a 0.1 mil resolution. If you recall, when we were placing objects, the tool only has a 1 mil resolution, but that's 1 mil for the grid. Sub features can definitely be, they're on, sub mil coordinates, right? So by putting that 0.1 and having that 10 times more resolution, 0.1 instead of 1, that gives us a little bit more, and we're a little bit more sure that everything's going to be okay. So we're going to leave it in 2.4. Okay, so put that in 2.4. And again, you're going to have to look at your manufacturer who you pick and kind of read through their stuff, or just ask them, just say, hey, what resolution should I put it in? And they'll say, yeah, we can take 2.4, 2.5, whatever, fine. Okay, now we go to layers. Now here's the big guy. This is the important thing. So first thing is, one thing is you can learn what these names are here. So here's these names, all these little names here, and they have their little file extensions. And these are kind of cryptic, and if you're not familiar with them, they're kind of hard, and I forget them many times. A lot of tools put the actual layer name in the file name, and then they use .text because they're all ASCII files. So that's one other thing. Everything is in ASCII. There are binary Gerber files, but we're not going to use those. We're going to use ASCII, so they're human readable, because they're not that big, so there's really no overhead, so there's no loss to make it human readable, so someone can just open the thing up and look at it and say, oh, that's what he meant. Anyway, so instead of putting something intelligent for the file name, some of these tools just put an extension and you're supposed to figure out what it is from that. Me personally, I like putting what it is in the file name itself, but the tool has to do that. Or you could go through the Gerber files yourself and edit the file names. You could do that, but we don't want to have to do all that work. All right, so anyway, so G is Gerber, as far as I know, Gerber, and then T0 is top overlay, TP top paste, TS top solder, top layer, bottom solder, bottom paste, bottom overlay. So those are pretty easy. If you see these here and you can remember, that's what those stand for. Now, what do we need? We've got a 2-layer board, so we have top copper and bottom copper. We need the solder mask on the top, solder mask on the bottom, and we need the top overlay, or the top silk it's called, or the bottom overlay and the bottom silk. And remember, it's called silk because it takes from the silk screen process of screen printing. It's called screen printing. And the reason why it's called screen printing has nothing to do with the computer screen. You actually put a screen on this printing table, and then you put ink, and then you put a mechanism, and then you can print on things. You can Google it and watch a video how to make t-shirts with silk screening. All right, you can see where that name came from. Another horrible name. All right, so that's all the layers. Now, there's all this other stuff here we do not need. All right, we do not need all these things unless you need them. Unless you know that you need them, then you need them. Okay, but we don't need them. Okay, so what we're going to do is we are going to add these things. So we're going to click here, and then you notice now we don't need the paste layer, because what the paste layer would be for is for manufacturing. That's where the solder paste goes. So you don't need that. That would only be for manufacturing. So you don't really need the paste layers, and that might just confuse them. But you definitely need the solder. That's the solder mask, and that's poorly named. Solder should be top solder mask. That's the mask that definitely needs to be included. Top overlays the text. Bottom, top solder, top layer, bottom solder, and bottom overlay. All right, and hopefully I got these all correct. Okay, now you can see here these mirror. Something might be backwards, so you can use mirror here if you want to mirror something around. We don't need to do all that. Now, this over here, what this is for is this. The other thing that we need in the file, maybe, is the outline. And the outline is where the router, a drill, or a cutting implement, a saw, laser, is going to cut the board out. So the board looks like what you see on the screen. It's this rectangle, this orange thing, right? So inside of all these files, you can extract or glean what the outline is, but it's nice to just have something that says, here is the outline. So we need an outline layer, and in the outline layer, we need to make sure the outline of the board is there. That's what that is for. So we're actually going to include that outline, okay? Now, mechanical layers to add to all plots. Now, this is confusing also. So what this means is this. So we have the outline layer, but in the other layers, you could overlay the outline, and then it would basically, you'd see this rectangle around everything. So on the top overlay, the top paste, the top solder, all these layers, you could actually put the outline layer. It's not going to hurt anything because that's where the board is cut. So if you say, do this, if you say mechanical layers to add to all plots, it will take the outline layer, and then it will mathematically merge the outline layer with the other layers, each one of them, so it's kind of a copy of itself. So in every single layer you can see the outline, whereas right now there's just going to be one file called the outline that you'd have to look at, render, to see the outline. So it's kind of it's redundant, but it doesn't hurt anything. Okay, so that's what that is for right there. We're not going to do it. We're just going to leave it like this, individual. Now the problem is we could click OK here and click OK, and then we could generate, but we don't know if we generated this outline, so we're going to check that. But let's keep going here before we do stuff. Now, NC drill files, let's go to that. Okay, so now on the NC drill files, first we want everything to match up. If we're in inches and millimeters on the Gerber files, you want to be inches or millimeters on the drill file. Whatever resolution you decided on the Gerber file, you need to make sure is on the same on the drill file. So what did we pick? 2.4, okay? And then there's some funny business down here. All right, so optimize change locations command, leave this right here. These are some other G-code command things. Don't mess with these for now unless someone tells you to or you learn to. You don't need to do any of this, but this right here is important. So C coordinate positions, reference to absolute origin, leave it that that way on everything. So absolute origin, that means the absolute origin in the entire coordinate system. This right here is important. So leading and trailing zeros. So this says keep leading and trailing zeros. So that means if you have a number and it's got so many digits, it might be, say, the number 1, right? So the number 1 might be 00001. So that's got some leading zeros. Now, say if you had 0001.2, right? Now you got leading zeros and you got trailing zeros, right? You don't need those zeros trailing. You don't need those zeros leading, right? What they kind of tell you about is how many digits of accuracy, but a parser might get confused. Now, if you look at some of the manufacturing websites, they will tell you suppress leading zeros or trailing zeros or whatever, right? So it'll say no trailing zeros or no leading zeros. So for example, I remember, and again, I don't use OshPark, but where is their little thing? So here on OshPark, submitting orders, drill issues, there's a lot more than drill issues here. If we go down here and we say, let's just type in 0. Oops. Okay. And hold on a second. I think this is the only, yeah. So this is kind of, so trailing zero suppression. This image shows our system views drill files with trailing zero suppression. All right. Suppressing the zeros causes our system to miscalculate many of the drill holes, causing several types of errors. All right, because the zero suppression doesn't affect all coordinates, it's possible for some drill hits to be shown or expected, others to be affected. Solution: make sure that zero suppression is set to none or disabled. So it's like a double negative. So first you got the word 0, suppression is a negative, right? Then it's set to none or disabled. So suppress, disabled. So in other words, this thing, the 0 suppression, we want it disabled. So we want the zeros. We want the leading zeros, all right? So if we go back to the tool, all right, keep leading and trailing zeros, suppress leading zeros, suppress trailing zeros, so keep leading and trailing zeros, okay? So make sure that zero suppression is set to none or disabled, all right? So we're just going to leave the trailing and leading zeros. And if there's a problem, we'll switch it to these things, okay? So anyway, more things to confuse you with. So again, we got our Gerber files and NC drill files. That's all we need, right? And then we can hit generate. But we're not going to do that. Let's make sure we have an outline. And this is how we're going to do the outline. All right. So we have our board here. And again, it sucks because the board is very, very long and thin. So it's hard to make it big on the screen. So we've got our whole board here. And what we want is the outline. So first, let's go into single layer mode. Remember that? That's what Shift S. And then we're going to shift, we're going to go through the different layers with plus and minus here. All right, and then down here, you can see what's going on. So, and you can see, and it's hard for me to point, but right where my cursor is, as I do this, you can see it's selecting. So it's like scrolling things through and it's showing what it's showing here. All right, so the bottom line is, we want to get to the outline layer. That's the outline layer. So let's go to the top layer. Let's go to top layer, top layer, top layer, top layer, top layer. Okay, so there's the top layer. That's the bottom layer. Okay, that's the outline. All right, so now, yeah, and this is, it's grayed here. It's very hard to see what tab is selected. Now, you can also click like this to get things. You can just click on it. All right. So anyway, we click the outline. Now let's zoom in here. Okay. So now this outline is, some components will have an outline around them, which I'm not sure why they do. But the board has no outline. There's no general outline around the board. So what we want to do is we want to create a outline from the board. Okay. So what we can do to get this to happen is we can go here. So let's go home. We need to create an outline around this, and if we go up to board shape and we say edit board shape, I am not sure how we can select this this region and then create an outline from it. I'm sure there's a way to do this, but that's not working. So what we can do is we can say create primitives from board shape itself. So there's this tool right here, and what we're going to do is we're going to put it in the outline layer and route tool outline. So see how it goes on the outside there? All right, And then if we just put this at 0 mil, I think this is going to get us what we need in this particular case. So we'll put it for 0 mil because we don't need this to be anything. It's dimensionless, really. 1 mil would also probably work just fine. 1,000th shouldn't be a problem. But if we hit OK, then notice we get this line around here. All right. So that line right there should create our board shape that we need, our outline. And then if we go into 3 here, go here, everything still is okay, nothing weird happened, all right? So I think that'll do it. All right, so again, what we do is we go to board shape and we say create primitives from board shape. We just make this width like 0 mil or 1 mil because it's going to be a cut. We want to stuff it in the outline layer and we say route tool outline, and then that creates that layer. So now if we go into single layer mode, now you can see we've got a boundary around the board. Okay, so we've got a boundary around the board. Okay, so now let's go ahead here and so let's go and make sure that we save this. All right, and then we will recommit it. Okay, so now, and you know, this concurrency editing thing apparently needs some work because it's collapsing these different things here. So I'm working on the Magic Wand final design and it's collapsing these things, as you can see, very oddly, but it's okay. Okay, so now we've got our board ready. Let's go back to the view here where we've got everything. And so there's our board. Okay, it all looks good. So now we can go back to project here and we go to generate outputs, and we've configured everything. We've got our Gerber file ready, we've got our NC drill file ready, and we're all ready to click generate. All right, so let's go ahead, let's stop the video here, and then we're gonna, now that we've kind of gone through the, you know, the rigmarole of how to do this, in the next video we'll generate the Gerber files, the NC drill files. We'll take a look at them in a Gerber viewer, and then we will go ahead and take a look at how we would take those to a manufacturer. So let's just stop here, and I'll see you in the next video. Bye. All right, everybody, welcome back. And we were just about to generate our Gerber files and our NC drill files. Basically, we're going to make a whole package. So again, in the project tab here, in the project actions, we're going to use the generate outputs, which gives us this kind of master dialog here where we can select everything. And we aren't going to, you know, put anything other than the Gerber files and the NC drill files into the package. We could put the bill of materials, and we could put the assembly pick and place and the 3D step model and all that. But all we really care about are the Gerber files now and the NC drill files. Now we've already configured this, so if those of you that are maybe jumping to this video, in this configuration, this is a 2-layer board. So the layer stack for this is we've got the top silk layer and the bottom silk. That's the text. Then we've got the solder mask on each side, and then we've got the top and bottom copper. All right. So these are the layers that we're going to include in the layers sub-dialog here. So, you know, top overlay, that's the silk screen. Top paste, we're not going to include. That would be paste for manufacturing. Top solder, top layer, bottom solder. We don't need the bottom paste. We do need the bottom overlay, and we do want the outline, and we talked about that. Go back to the other video. Drill drawing, apertures, and advanced. We're not going to mess with anything. The only thing we are going to mess with is in this advanced thing here. See how it has this suppress leading zeros? Now, depending on where you're doing your manufacturing, they might have some notes about some of these settings. So what we're going to do is we're going to, and we already read that OshPark likes the trailing and leading zeros. So we're going to say keep leading and trailing zeros, all right? And if it messes up, we'll go back and fix it, all right? So that's that, and then we're going to go to the NC drill file. Oh, and then one other thing. Make sure that in general here, so we've got this size, inches is the scale, and now in some dialogues it might call this imperial instead of inches, but it's inches and imperial is the same. and we're going to set it for 2.4. That's the resolution. All right, let's go to the NC drill files. That's 2.4 inches. Keep leading and trailing 0, so this one's okay. And that's all there is to this, and reference to absolute origin. All right, so we already did this, so this should be just a quick review. All right, so we've got our board. We're ready to generate the files, and we're going to go ahead and say generate. Okay, so let's go ahead and I just did it to make sure that it worked. So let's go ahead and generate the files again. So we're going to say generate, and then it's popping open a dialog here for where I want it. So on the other screen. So circuit maker, and then we're just going to put it into, I've got a directory for each one of our projects. So we're going to put it into the magic wand. It just generated this one. We're going to write on top of it. Yes, I want to replace it. Okay, and then that's done. And now let's go ahead, and we've already generated it, so we can close this dialog. And now here is our directory that should have it. So here's this zip file. So now what we're going to do, let's put this into this details list mode. All right, so here it is here. So the first thing I'm going to do is I'm just going to, we can just crack it open and look inside of it. It's got those files, but to look at them, we're going to have to extract it all. So we'll extract it right into the same place with the same name. Okay, so now here are the results. So we have one zip file. So we've got that one zip file that we could send to a manufacturer. And inside of it, we've got Gerber files and we've got this NC drill file. So it's very easy to find things. And then there's status report, right? And the status report is just information. And it just says what it did, all right? So that helps a little bit, and leave that there. Now let's go into the Gerber file, and you can see we've got all these layers that we asked for, and then there's some other things here, all right? And don't worry about those, just leave those inside of there. If they don't need them, then they won't use them. NC drill file, same thing. There's some extra files in here. This text files, the drill file, and these extra files again, and then a status file which just says what went on. Again, leave everything there. Okay, now what we want to do is we want to see, is this correct? So we know what the circuit's supposed to look like, right? So if we go here and we zoom in, for example, and we say, let's just look at single layer, and let's look at the top copper. Let's just click top layer here. So here's what the top layer looks like. Okay, so that looks familiar. That's what the top layer looks like. Now let's go to the bottom layer. That's what the bottom layer should look like, right? And then the top overlay, top overlay, top overlay. It's probably quicker to just scroll through and try and find it like this. Where is it? There it is right there. So there's the top overlay with the text. And now this one, I don't believe we actually put anything on the bottom overlay. So this is, let's talk about this a minute. So here's the bottom overlay, or the bottom silkscreen layer. There's actually nothing there. Now, many manufacturers will charge you extra to print the top and the bottom. So I like to put stuff on the top and the bottom because I can put notes on the bottom or others, other information that doesn't fit. But if you're really trying to go on the cheap, then a lot of times you won't include the bottom layer, bottom overlay or bottom silk layer. And in this case, there is none, so there's no need to pay for it. All right, just keep that in mind. Okay, so we know what everything's supposed to look like. All right, so now what we're going to do is we're going to go to a Gerber viewer, and we are going to, we'll just kind of keep these right here on the screen here. And we're going to get a Gerber viewer. Remember, we talked about this already, and we talked about this ViewMate that you can get from Pentalogic for free, and then you can pay for the full version of it so you can make edits to the Gerber files. But if we just want the free one, we can look at Gerber files, and it's really useful. And let's close this annoying thing. All right, so here it is right here. And this is one of the most powerful and lowest cost Gerber editors I've ever seen. And these things are very hard to find, and they're very expensive. And this one is really, really, really cheap and good. And I think it's like $150. We've talked about this at length when we talked about Gerber file stuff, so I'm not going to go into it again. All right, so now what we're going to do is we're going to take our files, and one by one we're going to drag them in here. So I'm just going to put this on another screen so I can kind of drag across. All right, there we go. Okay, so now I'm going to go inside this directory here, and I'm going to go inside of Gerber. Okay, and then we've got all of these layers here. All right, so then one by one I'm going to drag layers. Okay, so let's look for the top layer. So I'm dragging it in there, and there's the top layer. So if I click in here and I can zoom and drag it around, you see that that is the top layer. And now what you want to do when you're doing your Gerber file review is zoom in and look closely. Make sure there's no shorts, there's no problems, and of course make sure the thing looks like what you output from your tool, right? So where's our tool? Here's our tool here, and what we're looking for is something that looks like this, right? So it should look exactly like this. And then sure enough, and I'm using two different tools that have two different ways to move things, so I'm going to confuse myself certainly. All right, so if you look at this top corner right here, and that right there, it's exactly the same. All right, now you don't see the drill holes here because those are going to be processed after. So after the boards are made, then they're drilled, right? So that's why you don't see the drill holes. Okay, so you go through here, you make sure there's no funny business, make sure everything is exactly what you wanted. And when you see it in this view kind of simplified like this, a lot of times you might see something you don't like. And then you'll go back to your design and fix it and then regenerate your Gerber files. All right, so anyway, this looks good to me. So I'm happy with that. So let's go to the next layer here. So let's go to, that was the top copper. Let's go to the top overlay, the TO layer. So that's that right there. And again, this is just text. All right, and then we're just looking, does the text look okay? Is anything funny, overlaid incorrectly? Is it just incorrect and so forth? But again, that all looks good. All right, spelling, everything's good there. Looks very good. So okay, good. Let's go to the solder mask. Let's see here, and I think this is bottom. Here we go. So this is where these holes, these are not the holes that are going to be drilled in the board, but these are where solder has to go. All right, so this is the solder mask, and this is basically says everywhere where there's a hole, I want solder to be able to get to. Right, so because you're going to solder to it, because these are the through holes of the board. All right, every place else there's going to be a mask where it's going to be filled with the color of the board, whether it's red or green or blue or whatever. So that looks correct right there. All right, and then let's see what else. Let's look at the bottom mask. There's the bottom, and it looks very similar to the top. It should actually almost be identical unless there's anything surface mount. All right, so that's the bottom. And then the other thing that's really important is the outline. There's the outline of the board. That's where the board is going to be cut. All right, so that's correct, right? Now, okay, so now let's go back here. So here's our Gerber and our drill file. Let's go into our drill file and let's grab the drill file. So I'll tell you the drill file is the one named text. So if I drag this into this tool is very advanced actually, and it can interpret drill files also, which is cool. So here is the drill file. Those are the actual holes and the actual size. So if you see here, here's some holes, but here's a bigger hole, right? So this is starting to make sense. We've got different size holes here for different size things, right? And so there's a different size hole, different size hole, different size hole. All right, now if we go into our design, we can see that also. And if we go to the proper layer, which, and again, bear with me here, bottom paste, top paste, bottom, I think we can see it in this tool here, assembly top, and maybe, oh wait, drill drawing. Let me see, drill drawing. So maybe that is the drill drawing. Yeah, I'm not sure. There is a view where you can actually see the drill holes in this tool. I'm not sure where though. All right, so sorry about that. Anyway, so now we've verified that the Gerber files look good. Okay, so the Gerber files look good. So let's go back up here. Now, in the real world, when you're going to go submit this to someone, there's some things that you want to do, all right? So one, I'm not a fan of putting spaces in file names, all right? So that's one thing I don't want to do, all right? Oops. So what I would first do here is, rename this. So get these spaces out of here, all right? And then right inside of the file name, you might want to put the version or put a date. Even though there's a date tagged on that, that date can be changed, right? The computer can change that. It's a file, but it's not going to change the file name. So maybe you want to put a date in here just for you so you know when you generated this. So maybe I'll put 8/2/17. All right, because that's the day it was generated. Or maybe I'll put the version. All right, but anyway, just make this kind of a simpler file name that's going to get parsed correctly and not going to get mangled with funny characters in it. So just straightforward, very simple, not too long. Maybe I'm going to put a date, maybe I'm going to put a version. This is all about keeping things in order. All right, in this way you can tell I generated these on this day, and then as you generate packages, they would be sorted. All right, by an actual name in the file name and not just by the date. because I never trust these dates. You know how it is. You copy some files and all of a sudden the dates are blown up, right? Okay, so here's our zip file. So we've got our manufacturing file, and then now maybe some vendors want us to take the NC drill files and copy them into the Gerber file and just make them all in one directory. Maybe we need to change some names. Maybe we do, maybe we don't. Right now, let's just assume that the system is smart enough or a person is smart enough to take that information. All right, so we got our zip file. All right, so now what we're going to do is let's go ahead and we will, let's just leave this tool. All right, and let's go back to full view here. Okay, now for the fun part. So here we go. Okay, so remember I told you about if you're going to submit your board to different manufacturers, you want to go look through their files and their documents to see about their submission guidelines, their file format, their this and that, you know, little quirks with the system. And OSHPARC, all the different vendors have this buried someplace. You have to find it. It's funny, if you're on the website, it's hard to find, but if you Google for submitting files to OSHPARC, then you can actually find this. So Google is a better search engine than most search engines on websites, which is, you know, obvious. I told you I wanted you to read through this, and then I'll put this inside the text file for the lectures, but it's just OSHPARC submitting orders drill issues, right? So this talks about different problems that you can have, and then if you have that problem, it'll say what it looks like when you have that problem. It kind of shows you, right? Things are off and this and that and so on. So it'll kind of show you what, you know, here something, you know, the mirrored y-axis. So the drill holes are there, but then the board is down here because here's the y-axis. So this needs to be down here, this needs to be up here, you know, things like that. All right, there's a translation problem. Anyway, a zero suppression issues, you know, this happens. All right, so anyway, you want to read through that and kind of know what's going on, all right? And if you have questions, they're there to help you. Well, that's the idea. Customer service on this planet sucks now, but you can at least try to call someone at the company or send an email and ask questions and get someone on the phone that can explain to you your questions. All right, so let's start off. We're going to start off with OSHPARC, and the reason why is because it has a nice system that takes the file immediately and puts it up on the screen. All right, so let's see what happens here. Okay, so I believe I'm already logged in. I've got accounts at all these places. Yeah, CEO at nerve.net. All right, so here we go. So we're going to, and then pricing and specifications. All right, and then it explains to you what the deal is. 2-layer board are $5 per square inch. That doesn't seem like a lot, but it actually is. Right, so if you've got a big board, say you got a board that's 4 by 4 inches, that's 16 square inches. 16 square inches times the 5, that's like 80 bucks plus this plus that. You know, it's $100 a board. That's expensive. So this is actually not cheap. All right, so that's why I don't use this also. Now, one thing we talked about, remember we talked about the different kinds of finishes, Hassel, hot air, surface leveling, and then Enig, which was immersion, something gold. This is the one we want. It's very flat and it's good. So Enig is the one you want. And we can just look that up real quick. Let's just look that up real quick. Enig. And yeah, Electroless nickel immersion gold. Yeah. So, and that's really, really flat. We like that surface. Okay. Okay. So let's go get started. So you've created your account on OSHPARC, for example, and all we're trying to do right now is price things, right? We're not going to say do it, we're just pricing it, right? And we're going to do this on 4, 5, 10 different companies until we find one that we like that's cheap or one that you go with usually. All right, so it's talking about different things here, design submission guidelines. Let's open that up in another tab here real quick. So look at this right here. So it's telling you suggested naming patterns, and look, there's that top layer, bottom layer, all those things, and then common file name related issues, right? Explaining all these things, drill mask, it's talking a little bit about KiCad, a little bit about Eagle, Altium, which is what we're using, Proteus, which is another tool that we used also, Proteus Aries, and then they might have Circuit Maker, no they don't. So Altium and Circuit Maker would kind of follow under the same thing there. Okay, so you might want to read that. Okay, so select a file on your computer. So let's do this. All right, and let me just make this window a little bit smaller. Okay, so what did we just do? We just did this magic wand, all right, and here's the, I hate this, I don't know, I just have never liked this iconic view. I like text. There we go. All right, so here's where we blew the directory up, but here's the zip file. So fingers crossed, right? We should just be able to give it the zip file. It should be able to parse the zip file, find the drill files, and find the Gerber files. So let's see how smart it is. So I've got it selected. I'm going to open it. It's uploading. It's processing, so now it's parsing everything, figuring it out, looking at the files, trying to find everything. All right, give it a second. And when this is done, this is actually quite cool. All right, so your project doesn't contain bottom silk screen. That's true. Remember, we talked about that, so that's okay. All right, and let's see. Enter any project details. Looks good. Enter a short description. Don't really care at this point, right? But we'll just put, magic wand. All right, and we'll say continue. All right, so now it's actually showing us what these things look like. So how cool is that? So now because of the aspect ratio of things, I'm gonna hit plus here a couple times and make the page a little bit bigger. But there's the top, there's the bottom. How cool is that? There's the drill holes. That looks good. All right, everything looks good. There's the bottom solder mask. There's the bottom layer. There's the top silk screen, top solder mask, beautiful. There's the board outline, beautiful. All right, and there's the top layer. Beautiful. All right, now we'll say approve and order. All right, so that we can just get to this right here. All right, and then this is a previous one that I did. Let me remove that so we can just see the price. Okay, so it says, here's what you're building. You want 3 of them. It's going to cost you $60. And then we can do some changes here. We can say 2-ounce copper, all right, if we want, and that I'm not sure why it didn't increase the price. Maybe it slows down the time. Medium run, you can read what that means. Super swift service, you can read what that means. And then they try to upsell you here on some products. Don't ignore that. Now, 2-ounce copper. This is the same as our normal service, but with thicker copper. Remember we talked about copper, right? The ounce of copper, what that means is how thick the copper is. And basically where that came from is you take a square foot of the copper, bang it out flat, right? And that would be the thickness of it. And that would be how much that 1 by 1 square foot chunk of copper weighs, all right? So if it's 2 ounce, it's obviously heavier and thicker, and that's better. And the reason it's better, it's going to allow more current, it's going to allow more heat dissipation. So I prefer, 2-ounce copper usually, but 1-ounce copper will do if it's cheaper. Now, please allow 3 weeks from ordering. So a month? Are you kidding me? I can't wait 3 days to get these things done. So if you use the 2-ounce, they have to send it someplace else. So they explain all the different things to you. And then if you select this option, we'll ship it to you in under 5 business days. Da da da. This only affects manufacturing time. It does not change the shipping method. All right. Now, so we'll ship your order in under 5 business days, and then the shipping method you also have to change. Now let's see what's the cost increase for that. Super Swift Service. Ready? Doubles the price. So it goes up 200% basically if you do that, all right? So anyway, OshPark, what's nice about it, shows you what they're going to do, and then you can make these changes, and that's that. So we're going to use this as one of our services to see how things will go. Now again, we don't know, and I'm not sure here how long this takes. Normally, the medium is much slower and can take 2 to 4 weeks. So Super Swift, if you select, we'll ship your order in under 5. So what do they ship? Place orders will be shipped in 4 business days. So I'm not sure. See this right here? Any day that you order it, I think it's saying that it takes 4 days. Again, I don't use this service, so I think it says if you order it by 11 a.m., it'll take 4 business days. Okay, so that's not bad. All right, and then we go to checkout. We have to figure out what we're going to do for the shipping method. All right, then we put our name, our address, and all that kind of stuff in there, and then shipping USPS, and then priority mail, and then express mail $20. So that's not bad. So you can just put priority mail for $5, and you get it in 4 days. And priority mail takes 2 days in the United States. All right, and then if you go to other places, then of course you're going to use probably first class mail or priority mail. All right, so that's it. And then pay for it, hit order it, done. That's it. So do it. That's how you would build your board. Okay, now, so let's look. This board was $61 for 3. Now, what we're going to do now is we're going to go to some of these other vendors, and we're going to kind of look at some pricing. And we're going to do this process together, all right? Okay, so we're going to go to PC Fab Express, and we're going to do member login here. And I don't have any of these memorized purposely. Okay, so we're here in PC Fab Express. Now, I've used this company for, what year is this? I don't know, 13, 14 years since they started up. And, they're a real solid company. Their prices are pretty competitive. and they're pretty reliable. So anyway, it's just a good solid PCB company locally in the United States that you can use. All right. So Rapid Prototype, they have all kinds of different things. Their website's a little, busy. But anyway, you can kind of figure out where you want to do this. All right, so standard technology, higher technology. So we want like standard technology. So preview by 2-layer, 4-layer, 6-layer. So we're gonna, if we click preview, this tells us what the specifications are. So it says the thickness 0.062 inches. That's the thickness of the board. You can't change it. From 2 to 6 layers. It's saying no gold, no step and repeat. It's saying Gerber files or this format. We need the RS274X. That's what's output by Circuit Maker, so that's okay. Now, copper weight. Outer layers are 1. Finished, we start with 0.5 foil, inner layer is 0.5. So the copper layers are not very thick. They don't allow very thick. Then they talk about hole sizes. This is going to matter if you're doing really fine work, right? So 8 thousandths of an inch finish hole size, maximum is 246, all right? And then, so you just kind of go through here. The maximum board size is 16 inches by half an inch is the big and the small. And then no cutouts and slots, and just you can read through this and all kinds of constraints on you. Okay, all kinds of constraints. Read that so that you understand what you can and cannot do. And that's what's going to go into your design rules or your design as you're designing your board. All right. Most of these companies are roughly the same. And so once you kind of have your rules set up and you design your boards in that way, you're pretty safe on all these companies. If you violate something, they'll let you do it. You'll just have to pay for it. Or you'll have to go to something that's not like a cheap online special. Okay. So let's see here. Let's just back up. All right, so let's see buy, and what we want to do is quote, because we're trying to figure out prices right here. All right, so here we go. So our board is 2 layers. Let's do it in 5 days. That's the sweet spot. If you don't care about how fast this comes in, 3 is too expensive, 10 is too long, 5 is the sweet spot. I'm going to tell you that right now. 3 boards is usually the sweet spot, 3 to 5 boards, we'll keep it there. Now the board dimensions, let's find out what the board dimensions are. So let's go here, all right, and let's zoom out. And let's do our board dimensions with our tool here. And that basically this is how they're going to quote it. And all right, well, this thing's not going to help me too much, so we're just going to eyeball it. And I believe it's 13 inches or something. Yeah, it's about 13 inches. All right, 13 inches by, and we're just trying to be semi-close right now because they're just charging us on square inches. 13 inches by, about an inch, right? Almost an inch. Okay, so we're going to just say it's 13 by 1, all right? We don't have to, this doesn't have to be perfect. All right, so 13 inches by 1 inch. Okay, minimum finished hole size. So see right here, it's asking us how big is the minimum finished hole size. And we could go look at the board. I think they're a lot bigger than 10 mils, right? So we can go to the board and look at our board and what's the smallest little tiny hole on here. And you can probably go look, and it's these kind of holes right here, right? That are all over the place. These are the smallest ones, more or less. So this is the smallest hole right here. If we go to this pad, we can see here. So this is 60 mil. Let me see. 30 mil is the hole size. It's huge. Okay, it's huge. Okay, so we don't have any worries here. So we're just going to leave that at the defaults. This is just saying, and it's not going to charge us anymore unless we go down to the smaller one. So we're just going to leave it at the defaults. Surface finish. Okay, now here is this lead-free hassle. All right, so if you want lead in your solder, great, but otherwise we want lead-free. So let's do lead-free just to keep it clean. All right. Okay, so now we've got its size. We've got 3 boards. We've got 2 layers. All right, that's it. We'll hit continue. All right, now we look at its price. So the price is $77 for 3 of them. $77 per unit. So a total of $231. Now wait a minute. We go back here, quantity 3, this one's $61, all right? So this is much cheaper. Right? So right off the bat, we say, hey, this is the better way to go. Excuse me, not this, but Osh Park is the better way to go. But on this right here, maybe we have some other specifications that we need, right? Or we need it really fast. And so now you can see this matrix down here, and you can start playing around here. So if you go to, so here's what's interesting. If you go to 5 boards, now they're $47 a board. All right, so you go to 5 boards and they're 47. Let's get a calculator. right? So 5 times 47 is 235. So for $4 more, you get 5 boards. Now, watch what else is interesting here. There's a point here where it's like, so cheap, you might as well just get a lot of boards. Look at 10 boards, look at 25 boards. 25 boards, for example, is $18. So 25 boards is 450. So that's not it. So, but there's a point here where you maximize the number of boards and the cost, right? So you can either play around with that and kind of see what you want to do, and then either get a few more boards or not, because you just want to save money. All right. So anyway, this is looking like this is expensive, so we're not going to go here, right? Maybe we want to save money on this one. All right. So now let's go to Pentalogix. All right. So this is another cool company. So let me go ahead and sign in. Okay, so Pentalogix, we're signed in. Remember, this is a company. They have some CAD tools also, and they have the ViewMate, and you can download that for free. Now, they've got a lot of different products here, and so again, I don't want to spend hours on each one of these sites. I just want to spend a few moments showing you quickly. So we want PCB manufacturing. Then they've got US prototypes, they got quick turn prototypes, they got full feature, they got offshore, they got all kinds of stuff, right? And then custom quote, right? So what we can do is, I believe if we do view more, it tells us about each. Yeah. So if we do this one right here, so we can read this. So US quick turn. So these are people that maybe want to do things in the United States, keep it in the United States. You would use US quick turn. 2, 4, 6 layers, 8 layers, up to 100. Lead time as fast as 3, 4, 6, 3 days for 4 and 6 layers. Okay, great. Then you read what these things are all about. These take 2 to 3 weeks because these are full feature. These have custom specs. Okay, high quality, low cost. All right, so these take 2 to 3 weeks because they got to be manufactured in China and sent back. So if you're looking for price, this may be the way to go, and this is assembly. So why don't we try, let's go look at a US quick turn prototype, and we'll compare that to offshore PCB. All right, let's go ahead. Get quote now. All right, it shows all these different features. So trace width spacing, so you can have traces down to 5/1000ths of an inch, and the spacing can be 5,000. Internal cutouts, so that's cool. You can have cutouts. Complex board shape, that means you can make the board a funky shape, which is important, like the circle, right? Green solder mask, top and bottom, boring. And then electrical testing included. That means that after the board is done, they know what the circuitry is supposed to look like with no components, and they can test for electrical continuity. Okay, so this is pretty cool. So we're going to do the US quick turn, and in here someplace there's a description of, how to do this and how to do that for your Gerber files, which you want to read, right? You want to read here someplace. There's some kind of something here somewhere, I'm sure, about contact. I don't know. You'd have to find it and figure it out. But let's go ahead and do this. Okay, so part number, we're just going to call this part numbers. We're going to call this magic wand revision 1. This doesn't really matter. Okay, I want 3, 5, 10, and say 25 quoted. All right, number of layers 2. Remember, the board size is 13 by 1 inches. What kind of finish do we want? So we want hassle or a nig. We want a nig. We want that good finish. It'll be a little bit more expensive, but it's worth it. Silk screen both sides. Remember, we only need it on the top side on this particular board. All right, and that looks like that's it. Let's get a quote. And so, you can see this does not need the Gerber files. They're going to process them manually and look at them. So OshPark, what's nice is you can see what, you know that it's going to build that, which is nice. With this company, someone's going to process this. They're going to put them into their CAD tool. They're going to OK them, and then you're going to get an email that says your files have been processed and reviewed. They're OK, and we're going to start the manufacturing process. All right. With OshPark, or someone else who has an online system that analyzes, you can see that the boards are OK. So probably you're not going to have a hiccup in your manufacturing. Okay, so let's take a look here. So let's see, quantity 3, and we're going to do it. We want 5 days. All right. So now if you look right here, the unit price is $83. So see, quantity 3. So let's go to quantity 5, 73. All right, 366. All right, so 251. So really, this is pretty expensive, right? So it's 251 again. And if we look at that, what was this? This was 231, a little bit more expensive than PCB Fab Express, but still so far, we're getting 3 boards at OshPark for cheap, right? Now, the reason I said that I don't use OshPark because it's expensive and they have limited services compared to what I need, which is true. I go straight to China. In China, these boards would be about $1 a piece, if that. So I'd probably get 10 of them. It'd be 20 bucks. Right? Crazy, huh? But I go directly to China, right? And I don't even want to get into that. We're going to use these vendors that we can use easily from a website. Now, if you're not in the United States, you can still use these, or you can use your local vendors. But of course, I'm going to be talking about things from the United States since I'm from here. All right. Okay, so 251. Compare with offshore PCBs. Let's give that a shot. All right, so here we go. And it's going to push the information into this, which it did. And now we look here and we go, now look at this. So the offshore, it's going to be slower, 2 to 3 weeks lead time to turn it all around, but now it's 148. All right, so that's not bad. It's not bad. Again, it's still expensive. It's still expensive. You know, you could still go to the Oshpark if they're going to do what you need to do with your boards. All right, so okay, so that's that one. And then the final one. Now, actually, there's two of them I want to do. PCB Cart. This is another company that I use. Okay, so let's go ahead and I'll log in. Okay, so we're logged into PCB Cart here. All right, again, notice one thing, these companies look fairly similar, right? If you go back here to Pentalogic, so, well, this one doesn't look too similar, but I believe this one will. Yeah, you go to PC, see it's got this kind of layout right here, and look here, it's got the same kind of layout, right? So in other words, they're kind of grabbing these from the same templates on internet and building their websites. Anyway, same thing, standard PCBs, prototype PCBs, etc. Now, be careful with prototype stuff. A lot of time they won't have silkscreen and this and that, so you got to watch out. So if we look here, let's read more about this. All right, so let's read through this and see what we got. So here's the features. All right, so IPC1, I don't care about that. Number of layers, 1 to 8. Order quantity, build time, material, FR4. Board size, 6 by 6 millimeters, 500 by 500. Board tolerance, don't care about that. Copper weight is 1 to 2 ounce. Inner copper is 0.5 to 1. Copper thickness, okay. Minimum tray space is 5. All right. Solder mask on both sides, yes. Solder mask color, all these different colors. Solder silkscreen sides as per the file, silkscreen color. So this is pretty good. So this quick turn, this PCB prototype is actually not bad. So let's give this a try. All right, so here we go. Part number, all right? So magic wand, all right? And it's 2 layers, board size in millimeters. Can we switch this for millimeters? No. All right. So what is it? 13 inches times 24.5 millimeters per inch is 31. So we'll just call it 32 millimeters. And, oh, I'm sorry. 13 times 24.5, that should be 318. Yeah, so 320 millimeters. And then this will be 24.5. I'll just call this 25. Quantity 5. All right. And I think, is that the minimum? Looks like it. 2 layers, a single board. I don't want to panelize anything. Lead time is 5 days. That's fine with me. Surface finish, let's just leave this one as lead-free hassle again. I don't want lead on things. Copper weight, we could put the 2, but again, we only need 1. It's not a high power thing. All right, thickness, finished board. You can change the thickness of your board here, but again, we're going to leave it as their default. Solder mask, as in the design. Now, this is nice. So solder mask color. Finally, we got some color. So what do you guys want to do? Red? I always like red. Red, red looks nice. Let's make the legend white. All right, so that's the silk screen. Okay, so $43 and quantity 5, unit, so unit price 8. So check this out. So let's go to cart here. All right, go to checkout. And do I have something in here? I don't know what this thing is. Oh, previous quote. So look at this. So now we got 5 boards. We got them colored. We got them cool. We got with lead-free solder. And these are only $8 each. So our total is $43. We got 5 boards. And what was our best so far? Our best was, where was our best? From Oshpark, 3 boards for $60, right? So each of these boards is about, what, $20? But over here, each one of our boards, right, let's do our little divide here, 43 divided by 5, is $860. So we have done really well. Now, what if we were lazy and we said, oh, let's just stop, you know, Oshpark is the best. Well, look, we just found PCB Cart rocks them, completely rocks them, and you get colored boards, right, which is super cool. All right, so anyway, so now proceed to checkout. I'm not going to buy these. All right, and then we can do our payment here or whatever, and then we can select which method we want to ship them with, okay? And then that's it. You got your boards manufactured, all right? So, so that is that. So that is the process of generating Gerber files taking them to the manufacturer and doing all that. All right, so let's, we're not going to do all three. I don't think we need to belabor the point. I think you guys know how to do this, but let's go ahead and let's do another one. Why don't we do the, well, let's see, maybe we can do them pretty quick. Let's see. All right, so here we go. So let's close this, and let's close this. All right, so that was the magic wand. Let's go to the 555 timer organ. Let's open up the document so I can see what I'm doing here. All right, so here's our 555 timer guy. So here's our organ. So again, we need this outline. So let's go look at the outline layer and let's turn this on single. Notice we don't have an outline here again, right? Again, it'll probably be okay and the system will be able to figure it out. There's some little funkiness right there. Look at that. Look at that little thing right there. So that's kind of interesting. Let's see if we can fix that. So if we go to home and we go to board shape and we say edit board shape, I believe it's edit board shape, yeah. Let's see if we can grab this. Of course not. And so this might, you know, what this actually might be is the copper. Let me see. Yeah, you know what? This might be the copper. This might be the copper pour. It would be cut by the outline, so it doesn't really matter. It's not going to hurt anything. Okay, so again, we really do want to put an outline on here just in case, even though the vendor would be able to figure this out because there is an outline here. But we're going to put it separately inside of this outline layer. Okay, so let me go ahead and do that. All right, so remember we're going to use that create primitives from board shape, and we're going to just make this 1 mil thick. We're going to call it the outline, route tool outline. All right, and now if we do control or shift S and go to single layer mode, notice now we have this outline around the board. Okay, so now I'm going to save that, and then I'm going to recommit the final design here. All right, and we just want to make sure we've got that outline. That's all. All right, and let's go back, say Shift S, get all the layers, go to 3D mode. Our board looks good. We're all happy. Okay, so we'll go back to 2D mode, and let's go ahead and let's generate our files. So we go to Project, we go to Generate Outputs. Now, I don't believe this maintains this from project to project, so we're going to have to go reconfigure. All we want are Gerber files and NC files. We're going to go to Configure. We want it 2.4. Layers, let's get our layers we want. So all these layers, and then we're going to undo the paste layer. We don't need that, and we don't need that, right? Drilling, drill drawing, don't care about that, nothing there. In advanced, we do care. In advanced, we have to say keep leading and trailing 0. So we're going to keep those there. Everything else we're just going to leave the same unless we've been told to change it. Okay, that looks good. Go to configure the NC drill files again, set the resolution correctly, and then get rid of the suppress, keep leading and trailing 0s. We're going to hit OK, and then we're ready to go. All right, so then we're going to hit generate. Okay, and it pops up the directory here, and we want to stuff this into the timer organ. So here it is right here. We're going to save it. Okay, close. Now let me get that window wherever it's hidden. So here it is here. All right, so timer organ, there it is. There's our zip file. Let's explode it. All right, so now we've got our Gerber files. Looks good. We've got our NC drill file. Looks good. All right, so now let's go into our Gerber viewer. I'm just going to move this off the screen so I can work with it. I got too many things here open. All right, what am I doing? We're looking for the Gerber viewer, so we're looking for this view mate. All right, so we're going to go to the Gerber files, and I'm just going to, let's start off with the top copper. There's the top copper. All right, and if we were to go look at the design, right, we would go back to the design here, and we go to single layer mode, and we go to top layer. So we're looking for something that looks like this. So sure enough, it does look like that, right? There's that little section there, that little section there, section there, section there. All right, so again, what we do is we just want to look around here. All right, we want to zoom in, zoom out, make sure there's no funny business, right? Because we're going to manufacture this thing. Are there any shorts? Is there anything you don't like? Is there anything, you know, that could be a little bit better? Could you move this? Could you, you know, whatever, right? You know, I'm not happy about that, right? But it'll be okay. All right, let's zoom out. Looks good. Remember, we only spent a little bit of time cleaning this up, right? So we could have made a better version in the tool itself, but at some point you have to just give up and say it's done, or nothing ever gets finished, right? Okay, so that looks good. All right, let's look at top overlay. That's our top overlay. Text all looks good. I'm happy with that. All right, let's see. Bottom layer. There's the bottom copper, right? Again, zoom in, check things out. Make sure there's nothing going wrong. Okay, looks good. What else we got? We got the solder mask. That's the bottom solder mask. That looks good. There's the top solder mask, almost identical. And then let's see, where's the bottom overlay? Bottom overlay. And so there's nothing on the bottom on this one, right? So there's nothing on the bottom, which I don't remember if we had something on the bottom, but we surely have space to put something on the bottom. If we go to 3D view, right, and we rotate this thing around, yeah, we could put something real cool on the back, right? We could put some text there, right? But anyway, so that's that. Good. So now, again, let's just save this thing again, and let's make sure we commit it. Okay. All right, so now we've looked at it, looks good, and what's another thing we can look at? Let's go to the NC drill file. So we'll open that up and we'll get the text out of it. Drop that into the tool, and that's where the drill holes go. And that looks correct, right? There's the four corners of the board, there's the battery holder, and there's all the other stuff, right? So this looks like what we built, all right? So I'm pretty happy, all right? So now we can go, and now the Osh Park tool is pretty cool because it shows you the board. So we're going to start there. So we're going to go here, we'll go back home, we'll say get started now. Select a file on your computer. We're going to go to the, what are we going to? The timer. And again, I don't like this view. All right, there we go. All right. All right, it's from programming in DOS so many years and 8-bit computers. I just want some text. All right, so we want this right here. We're going to open that up. Let it process. This one might take a little bit longer, huh? It's a little bit more complicated. I can't find a board outline file. All right, so the board outline file, that's something that is a problem. So let's see what happened there. All right, so here's this, and we go to board outline. All right, and it's definitely there, and I'm looking in the Gerber file. I don't see the outline in the Gerber file. All right, so here's the Gerber file. Do you see the outline? No. All right, so we made a mistake. All right, I purposely did that, and to show you what would happen. And this is exactly what happens. Okay, so let's go generate the outputs again. So what I'm going to do is I'm going to go delete. I don't even need to delete it. So go generate outputs. So let's go back to configure here. Go back to the layers. And what are we missing? The outline, right? Right there. Okay. Now, let's go ahead and regenerate. And we're going to save it right into the same place here. Yes. Okay. Obliterate the previous file. All right. We're going to come up here. And then we're going to blow this directory away we exploded it in. All right, and now we're going to re-explode this. Okay, good. Now here's the new Gerber and drill file. So now if we go to the Gerber file, and there's the outline we're looking for. So let's make sure. Let me move this over here. It's complicated, guys. It's complicated. There's a lot to do, So here's the outline. I'm going to drag it in here. There's our outline. All right, so Osh Park now should be happy. So let's go back to Osh Park. All right, let's start over. Select a file from your computer, and we want the zip file. All right, this time it should work. So this is a lot of fun, and when your board is done, this is what you do for a couple days. You sit here and you go back and forth. You try and find a vendor that you like, and you're like, hey, I want the boards to be colored. I got some cool cutouts in them. I want them to have silk screen on both sides. I want 2-ounce copper, but I don't want to spend $1 zillion, right? So you got to look around, and then don't do anything. Just let it simmer a day or something. Think about it, check some other things, and then pull the trigger on it, because usually you did make one little mistake, and sometimes kind of good to go back and look at it. So don't rush. You get real excited, and I know I do. I've got a board, and I want to build it, and then I ship it away, and I'm like, oh no, there's a mistake. I forgot something, and then I just wasted the money. So take your time when you're doing this. All right, take your time. All right, so it looks like it worked that time, and it's 9 by 4 inches, so it's 228 by 101. Let's try and remember that. 9 by 4, 228 by 101, $180 for 3. So this one's a little bit expensive, so even Osh Park is getting expensive here. So we're going to do continue because we want to see it. All right, so ooh, look how cool that looks. So let's make it big. All right, so we got the 4 holes. This looks good. Beautiful, beautiful. There's the back, the drills. Bottom solder mask, bottom layer, top silk, sick. Top solder mask, board outline, good. There's the top layer copper. Look, good. All right, so approve and order. All right, let's get our magic wand out of here. All right, so we got 3 for 180. All right, so we're not going to go to all these companies because we already know they're pretty expensive, but we're going to go to the PCB cart. Let's do that one. So let's close this window here. All right, we're going to go to PCB cart. Here we go. And what do we want? We want prototype PCBs. Quote now. I don't know what you're talking about, Chrome. All right, so part number, we're just going to call this, what are we going to call this? We'll just call this 555 organ. All right, and then the board size was 228 by 101. Was that about right? Let's just make sure of that. As a matter of fact, can we go back to PCB cart and see it? Can we go back here someplace? Does it say? Does it say no? Can I press back? Will that blow up the website? Can I press back again? Here we go. And no, can I press back again? And there it is. Yeah, 228 by 101. Okay. 228 by 101, quantity 5. All right. Okay, so we're going to do, this time let's do an ENIG on this one. And we'll check both prices. Let's leave it at 1 ounce copper. We'll leave the board normal thick. Solder mask, this one has it as in file. Solder mask color. Okay, so let's do this. We did last one red. Let's do this one blue, and we'll use white. All right, and is there something we are missing here? So display no longer. I don't know what this is. Solder mask. Okay, solder legend. Okay, thank you. All right, and single board. There we go. Okay, so for 5 boards, it's $86 and tooling is free. So total cost for 5 boards is $86. I mean, how can you beat that? And you come here, and what was our? Oh, we already skipped past it. It was $180, right? 180 right there. All right, now that's 86, and we picked ENIG. Now let's look if we do lead free. So $10 savings there if we just do plain hassle. Yeah, so and this is fine. Hassle's fine. For this board. This is all through-hole stuff. Don't worry about it. Look at that, $66. Boom, I'm adding to cart, and we're done with that. All right, so that is really, 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 really cheap. All right, that's great. All right, and then of course you can have the cool color, and then the color doesn't change the price in most cases. So if we go red, yeah, it's still the same. Sometimes if you do a funky thing, like if you do white, and then we do black, yeah, see that? So the white with the black is a little bit more expensive. So sometimes the color can have an effect. So, if you want to pimp it out, do I have any white boards here? No, but white does look very cool, and the black text on it is very easy to read. Okay, so that's that one. Let's do our last one. All right, let's do our last one. What time is it? Okay, where are we? Let's go here. Okay, so we're done with this. Just let me recommit this. Recommit this, just so if we did anything weird to it. All right, and let's close both of these and close this. Now, our last design was surface mount, right? And that was the Simonduino. Now, remember, we're not going to do the final because the final isn't the final. We're going to do the work copy because that is a copy of the original, and this is the one that we kind of have the whole thing. All right, so this one already does have an outline. So let's go in this view right here. So this is the whole board with everything in it. Looks good. This is the entire product. All right, so we are going to build this right here. And this has got a 4-inch diameter, right? 4-inch diameter. So this board is going to be pi r squared, so 3. So let's figure that out. So pi times r squared, which is 4. So it's about 12.5, 13 square inches of material. So that'll be interesting to see how that what that costs. All right, so let's get to the tool. So we want to generate outputs. All right, and schematic prints, we're going to turn that off. So configure, Gerber files, and NC drill files. All right, so here's all the layers. We don't need the top paste. Again, even though it's surface mount and you're going to need to put paste on it, they aren't going to do it, right? They're just building the board. So you can get rid of that. You don't need to include it in here. Sometimes it even confuses them. This time, make sure outline's in there. I tricked you last time. All right, and we got 2:4 resolution on inches mode. Okay, so we got our layers. We got our drill drawing, apertures advanced. Okay, suppress, keep leading and trailing zeros. Everything else the same. Good. Go to the NC drill files. Again, we're going to go on 2:4, reference absolute origin, and don't want to suppress. We want to keep those leading and trailing zeros. Hit OK. OK, and we're ready to go. Let's hit it. Generate. All right, and where are we going to put this? We're going to put this in the Simonduino directory. There it is. All right, and the cursor is magically doing stuff. Okay, so now we're going to back this out here. Back this out. Okay, so here's the directory. There's Simonduino. There it is right there. And remember, when I go really uploading this to the company and all that, I'm going to, simplify this name. I don't need this paragraph description, right? I'm going to put a date on it or something, right? Just keep it simple. Think like DOS, right? 8.3. Keep it simple. All right, so we're going to blow this up. There are our files. We got our Gerbers. We got our outline this time. We got our NC drill file. The drill is actually in the text. Okay. Now let's go to Gerber. All right. So again, I'm going to go to my Gerber viewer. You see in the process. This is a process. Over and over and over. This is what it is. Here's the top layer. All right. So we're going to zoom in on that, and we're going to get close and personal. There's the processor. Right. There's our nice grounds and stuff. We're just looking at it, inspecting it, comparing it to the original. It should look exactly the same as the tool, right? If we pop back into the tool and we get just the top copper, right? It should look just like that. And we're just running around in here. Is there any funny business? Is there anything we don't like? Sometimes you can see it better here because it's a more simplified view, right? I'm not happy about that. This little, right? I'm not happy about these little things here, right? I'd like those to be closed, okay? So, but again, you can just keep messing with this stuff forever. At some point, you got to pull the trigger. All right. This right here, maybe I would have pulled that out a little bit more and maybe try to get that fill to come around there. Anyway, so that looks good. So let's see. Here's the bottom. That's the bottom resist. There's the bottom overlay, right? It's backwards, right? There's the top overlay with all our text on it. Looks cool. Where's the bottom layer? There's the bottom copper, right? And remember, this thing's going to get cut out, so it doesn't matter that it's square. Here's the outline, right? And then let's go and get the drill file. So I'm in the NC drill subdirectory. There it is. There's the battery holder. There's the header for the Arduino interface. There's the programming interface. There's our speaker, right? Speaker holder. All right, the speaker sits behind it, so we can hear it. So we're good to go. So I'm happy. So let's go ahead and let's quote this up. All right, so here's the file right here. I'm just going to move it over here, and we're going to go to OshPark first. This is kind of our testing platform. It helps us test things. So let's do a start over. All right, select a computer file. All right, what are we doing, everyone? We are doing this, and we're doing the Simonduino, and we're doing this one right here. This one's complicated, so it's going to take it a couple minutes. Okay, so it's 4.01 by 4.01 inches, 101 by 101. All right, $80 for 3. So $80 for 3. Okay, so the 25 bucks and some change for each. All right, so let's continue. Let's see what it's looking like. All right, so I'm going to zoom in a couple times. So look at that. Gorgeous. Just perfect. Looks nice. And what's nice is this is it's a photorealistic rendering, right? Even though it's a pretty simple rendering, it is photorealistic, so it looks exactly like what the thing is going to look like. All right, it looks very, very, very similar to what you're going to see. All right, there's the board outline, and there's that, and there's that. Yeah, looks good. All right, so we could approve an order. We already know how much that costs. All right, so let's go back up top there and let's back out. So that was 80 bucks for three. 80 bucks for three. Okay, let's go to our other guys here and let's we'll type in, what is this thing? It is the Simonduino. All right, and what's the board size? 101 by 101, 2 layers, 555, da 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 da. And we already know that this is a little bit cheaper, so we're just going to start with the hassle. For the color of it, let's make it, let's make this one fun. We'll make it yellow. All right, and look at that, just ridiculous. 5 boards, circle, right? 40 bucks. What more do you want? That is crazy. Now, because it's surface mount, we really do want this Enig surface. All right. When you go to the Enig, it goes up by 50%. It went from 40 to 60, right? But it's worth it to make your soldering a little bit easier. Now, in this case, the solder, the size. Let's go to the next page here. Now, in this case, we used size 805 parts. They're all pretty easy to solder, right? So we could live without the Enig if we want to save that money. If you're really on a budget, hey, go without the Enig. You'll be able to do it. You'll be able to do it. All right. But the Enig will make it a little bit easier. All right. And again, we can take a look here. If we make it green, does it make it cheaper? No. So again, we make it yellow. It's 40 bucks. And then if we decided we wanted to make it white. Now, I'll tell you one thing. When you're doing projects that are lighting projects and that have LEDs on them, it's important that you reflect the LED, right? So you've got a lighting source, you want to reflect it. So actually, you don't want colored boards. You want a white board, all right? You want a good diffuser. You want something, you know, that's white colored, right? That's going to reflect light. So you make the PCB white. So we do that, and look at that. It goes to 5540. Then if we add Enig, then it goes up to 75. So anyway, it gets up pretty pricey. But if we just drop it down to hassle and leave it at white, then it's $55. So do what you will. So that's it. So we have gone through the process of designing the PCBs, laying them out, the schematics, generating the Gerber files, sending the Gerber files to manufacturers, looking at exactly what would have to be done, and then you just order them, right? Order them, you get them back, you buy the parts from DigiKey or Mouser, Octopart, whoever, and Newark, Element 14, whatever your favorite vendor is, and you solder the things together, and you cross your fingers, and you test them. All right, and when you're doing that, one last little piece of advice: build it up slowly. Like this complicated board, do not solder this whole thing at once, right? Solder things piece by piece. Start with the power supply, then turn the thing on. Does the power supply work? Yes. Then try the next section, the next section, the next section, slowly, because if you keep going, you're not going to know where you made a mistake. So you do things in sections. So like, for example, let's go to the Magic Wand, and we'll go to the circuit board here, get it up, and there we go. All right, so there's a circuit board, and if we look at the schematic, all right, so what do we have? We've got the power supply. So I would start off, I would just solder the battery connectors on, right? The battery holders and the switch, right? I would just get that going. And then I would just, switch it on and put a probe on V sub CC, and do I get, the voltage I should get, the 4.5 volts, right? The next thing I would solder is just the clock circuit, just the 555 timer, the potentiometers, the capacitors, and then I would turn the thing on, and then I would put a probe right here on this pin 3 and ground, and I would see if I'm getting a clock signal. Then I would hook the 4-bit counter. Again, see if that's counting. I'd put a probe on A0, 1, and 2, right? An oscilloscope or a probe, whatever. Then I'd hook up this next part. Then I'd hook up all these LEDs. Do it in pieces. So if you make a mistake, you can backtrack. Because remember, you're only ordering 3 or 5 PCBs, and you don't want to use all your parts and destroy everything. All right. So anyway, that is more or less the end of the class, and we may have some extra bonus videos and things like that down the line. But anyway, I hope you've enjoyed the course, and we've really went. If you think about all the material that we've covered, it's kind of overwhelming. We started off with what an electron was, right? We literally started off with charges, right? And we went all the way through all these different things, and we just built a circuit board and sent it to manufacturing. That's pretty cool. So anyway, Go back through the material as much as you need to. Send any questions you have to me, and I'll answer them. And I hope you enjoyed the course. Bye bye. Welcome everybody. So this is a bonus lecture and one of many bonus lectures that we're going to have. This is the first bonus lecture. So I'm going to kind of explain what's going on here. So if you've already taken the class and gone through all of the lectures, then you're going to have a really good idea of how to design electronics, build printed circuit boards, etc. So the bonus lectures are going to be kind of a potpourri, just random things. It might be something that one of you suggested that you wanted to learn about in a single lecture. It might be something cool that I want to show you in a single lecture. And it might be something not completely related to electronics. It may be something more compute related or microcontroller related, something higher, maybe retro computing or gaming, something like that. And then we'll learn about something, tear something apart, do something, build something, but we'll try and keep these in one lecture. So anyway, I've got many, many, many ideas, a big long list, and there's no real order how I'm going to do this. But the first one, what I thought, I was just sitting here and I just finished a medical product a while ago. And one of the things that we need to do in this medical product was sense force. And there's lots of different kinds of force sensors, but many of them are very expensive and many of them are very large. So we had to kind of find something that was very small, and there are a number of manufacturers that make what are called force sensing resistors. And if you take a look on the screen here, one of these companies is called Interlink Electronics, and you can see some of their products here. And so what these things are, basically they are a laminated series of materials that when you press on it, it changes its resistance. And so there's a certain construction to these, and we're going to take a look at them in a second. But you can see there's these different sizes, and this one right here is maybe the size of a dime. This one right here is maybe the size of a quarter. And then it's really simple. It's basically a resistor that as you squeeze and press on it and apply a force, the resistance changes. And then we can take that value of resistance and put it into a circuit, an analog to digital converter, or an op amp, something like that, and control something directly. Who knows? The whole thing is they're super cool, they're relatively cheap, and it's a fun sensor to be able to play with. Now, so what I'm thinking is let's take one of these sensors, which I have over here on the bench. Let's build a basic circuit with the sensor with an op amp. And in the course, we didn't really talk about op amps, so I'm going to briefly talk about it. But op amps are a massive subject. In fact, in college, if you get an EE degree, op amps are usually 1 semester, sometimes they're 2 semesters. So when I took EE, it was actually 2 semesters, beginning and advanced op amp design. So a whole year just to learn op amps and everything that they do. So obviously we can't learn op amps in a 30 to 60-minute lecture. But I'm going to kind of give you a quick and dirty overview of what they do, and then we're going to use it in the circuit. All right, so we're going to need a force sensing resistor sensor, which I have many of them. We're going to need an op amp, and we're going to just build up a little circuit. We're going to basically convert force into a voltage, and then we're going to plot it on an oscilloscope, and then we're going to maybe we could use it to control an LED, and then maybe talk about some other things we could do with it. Maybe use a comparator, an analog comparator, and compare the voltage of something, and when the force exceeds something, it could turn something on, something like that. So we'll talk about that, and we'll see what we're going to build. So before we get into all that, let's do our homework. All right, so the first thing is I wanted to show you this website, Interlink Electronics. And like I said, there are a couple companies that make these sensors. So let's take a look here. Here's another company. This one's called TechScan, and this company makes some of the smallest sensors I've ever seen. And again, you can see here 3.81 millimeters, 9 millimeters, 9 millimeters. So this diameter of this little sensor is, about 4 millimeters. That's pretty small, all right? And then they have these kind of mechanical little protrusions or contacts that you have to mechanically connect to. Usually you don't want to solder to these because you'll melt the plastic here. All right, so TechScan and then the other company, Interlink Electronics. the technologies are very similar, so we're just going to kind of look at these. The TechScan parts are very expensive actually. So unless you need something really, really small and Interlink doesn't have it, I would just avoid the TechScan at first because they are expensive. Unless you can probably find them on eBay. Someone's bought 1,000 of them or something. All right, so let's go ahead and let's take a look here. So depending on what you're doing, you might need something the size of a quarter, and then you might need long leads or short leads, long leads or something the size of a dime. So they have these variations of it so that you can kind of use what you need for whatever it is you're building, and you don't have to fabricate too much, all right? Now what I have, I believe, over here is I have the FSR 400, and I have the FSR I believe I have the short also. So the FSR 400's what I have over here, which kind of has this smaller sensing pad. All right, so let's just click on that. All right, and then you can kind of read about it. And now they make these sensors with different sensing capabilities. So their range is different. So some of them can sense a larger range or a higher amount of force, and some of them are for a lower amount of force. So you kind of have to read and figure out what you want and order what you want exactly. All right, now the other thing is when we're talking about, so let's back up here. So if it's been a while since you've done, high school physics or whatever, so these are measured in newtons. How much force you can apply is measured in newtons, right? And you apply this force over the surface area of this little sensor. So 0.1 newton, so forces as low as 0.1 newton and a sensitivity range of 20 newtons. Now, for example, if you're in the United States, most people don't know what a newton is. They've heard it before, but unless you're an engineering student or something, you're not going to be familiar with these. So the one thing is just being able to convert these to get an idea. So I think I have, let's see, a Google, yeah. So we look at a newton here. So 1 newton is about 0.22 pounds of force, right? Or another way, if we say 1 pound of force is about 4.44 newtons. So that kind of gives you an idea. So 1 pound is about 4.44 newtons, all right? And again, 1 newton is about 0.22 pounds. So that kind of gives you an idea. So in the case of that other sensor, it just said that it can measure from 0.1 newtons and a sensitivity up to 20 newtons. So 0.1 to 20. So let's take a look at that. So 0.1, all right, so that's, 0.02 pounds, right, and up to 20 newtons, right? That's 4.4 pounds, about 4.5 pounds. So that's a good amount of force. Now, you're going to be applying this force with your typically maybe it's a sensor you're going to press on it with a finger or something like that, or it could be you could have a mechanism, a mechanical mechanism, where you have maybe an actuator and the actuator is pushing down on the sensor, something like that, right? So anyway, if it's something you're going to press with your hands, believe me, 2 or 3 pounds of force is quite a bit for your fingers to be pushing down, or 5 pounds is quite a bit, so that'll suffice. But if you need something that can measure a higher amount of force, you can still use these, but you can adjust the electronics and the sensing so that you can kind of get a larger scale, all right? So anyway, so that's that. Now, on the Interlink page itself, there's a datasheet, integration guide, and a bunch of other things here. Unfortunately, they make you kind of fill things out. So if you want the integration guide, you got to fill this out and, put your name and all that just to get the information. However, on a couple different websites, I was able to find this SparkFun for one of them. So SparkFun has the same product and it's for sale here, and this is exactly what we're looking for. And you can see here there's kind of a size, and so like I said, this one's very small. It's like the size of a dime, and then the bigger one's about the size of a quarter. All right, now if we go ahead and crack open a couple of things, we can get the data sheet here. So again, showing the diameter. So this one's 5 millimeters, and this one's 13, and so on, depending on what you want. So this would, for example, this large 38 millimeter square one, maybe you want to sense when a vehicle drives over something, a bicycle, a car, whatever. You could put an array of these, or you could put one, and you could put a pressure plate, and then you could sense what's going on there. All right, and then it shows various different parameters and so forth, and then application information. So this is kind of this is one of the things I wanted to show you. In addition, there's what's called a, if we go here, there's what's called an integration guide. And I want you to read that as well. You're going to download that and read that if I can find it. Yeah. So here's a force sensing integration guide. And what this is, it's 26 pages. This is kind of a, quick and dirty explanation of how this technology works, right? So, I've read it. You should read it. Read it cover to cover so you know. And then it kind of talks how this thing works. So it's got kind of this flexible substrate here, which is this, kind of plastic polymer material. And then it's got this little spacer here. Now the spacer is just mils thick, so there's open air here. Then there's this resistor here, and then the whole idea is as you press down on this, you start making contact and shorting these little resistive elements together. And as you do that, the resistance changes, and then the signal is sensed with these two conductors here. It's as simple as that. Except it's made very, very, the construction is very, very accurate and precise and repeatable, so these sensors work very well. So these sensors actually work very, very well. Now, one of the problems with them, let me see if there's a chart here, is, yeah, so you can see here the chart. So we've got this conductance here, right? And conductance is the opposite of resistance. So here's resistance here. And you can see clearly this is nonlinear, right? So this is a curved chart here. And now it's linear in small pieces, right? So if you want to sense from here to here, it's linear, here to here, it's linear, here to here, it's linear. But if you want to go all the way from here to here, it's nonlinear. But this is no big deal. So what you do is you simply build your sensor, and then you basically apply a force, a known force, 1 Newton, 2 Newton, 3 Newton, 4 Newton, 5 Newton, etc., up to 20 Newtons or 100 Newtons. You measure the final voltage out of your system, right? We put that in a table, and then we use a curve fitting algorithms, or like a least squared algorithm, and then we could figure out what the force is very accurately, because we can basically, this is clearly a second order curve, third order at most, but a second order curve would fit through here nicely. It's clearly parabolic. And and that way we could use a lookup table to figure out what the force is very, very accurately. All right, so don't worry about the nonlinearity. If it's too non-linear for you, then you're just going to use a microcontroller. You'll, through experimentation, run the system, put a Newton of force, 2, 3, 4, 5, etc. Then you will measure with a third-party measuring device. So you're going to need something to measure force, so you know what force you're actually applying. You're going to correlate that with the voltage, create a table, or the resistance, create a table, and then you can use that lookup table to figure out, so I've applied, so I'm reading whatever the voltage is. Now, of course, this is conductance and resistance, which is going to result in a voltage, because we're going to basically create an amplifier, and we'll have a voltage, and then we'll know what the force is to each one of these things, right? Whatever the gram force is or the Newton force is, right? Okay, so that is that. And let me see, is there anything else here I wanted to show you? Yeah, and this is just, so again, do's and don'ts, how to mess with this stuff, be careful of it. And when we go on the bench, I'm going to show you how I fabricated some of these things to connect to them. They're mechanical, so you can't be soldering to them, you'll melt them. So you've got to kind of use mechanical connectors, right? And then it's got some suggested interfaces for basic sensing. So we see this symbol right here, and this is an op-amp, or operational amplifier. And I've probably mentioned this in the course if you've already been through the entire course, or you've probably heard this word before. An operational amplifier is a kind of an idealized amplifier. And inside of this little triangle are many dozens, if not hundreds, of components to try and create this perfect amplifier. Now, of course, nothing is perfect, but it's perfect within reason. So basically what an op-amp allows us to do is things like amplification, filtering, mathematical operations, addition, subtraction, multiplication, logarithms, all crazy, crazy stuff. Op-amps are crazy. And like I said, it's basically a semester or good year course to dig into op-amps. Now, there are hundreds, if not thousands, of books on op-amps. I'm going to show you a couple. But an op-amp is an amplifier. And in this case right here, what's going on is the force sensing resistor is here. It's being used as a variable resistor. Then we've got a fixed resistor here. So we've got a voltage divider going on here. Then this op amp is just being used as a simple non-inverting buffer. That's all it's doing. It's buffering it. So basically, we want to sense the voltage at the node, but we don't want any current to be drawn out of here, because as we draw current out of here, we would change the resistance, and the system would change and be inaccurate. So that's another property of op amps, ideally, no current flows into these or flows out of these two terminals called the non-inverting and inverting terminal. And we're going to take a look at this just real quick. I'm going to kind of give you a crash course in op amps just for a few minutes to kind of get your feet wet in it. But anyway, we can use the properties of op amps to create this, basically it's a buffer, and it's an analog buffer. So whatever voltage is here, we're going to see here, but when we sense this voltage, the system basically will draw no current from it magically. But on the output here, we can actually drive a lot of current. So for example, this output is going to follow this input here. So we're going to be able to track what this force sensing resistor is doing. And then say the voltage is 1 volt, 2 volt, 3 volts, and I want to pull like 30, 40, 50 milliamps out of here, depending on the op amp, I can do that. And it will have zero effect on the circuit. Because it has zero effect on this, it won't change the voltage and thus change the reading. So remember, when you're doing sensing, ideally when you're talking to your sensors, you don't want to modify or disrupt the sensor itself as you're sensing from it, right? You want to basically look at it without it knowing you're looking at it. Okay, so this is one possible configuration here. And then it's showing you that V out equals V plus, whatever this V plus is here, divided by 1 plus, RFSR, which is this right here, and divided by RM. So that's the equation that you would get. So that would tell you what the V out would be. All right. And it's just saying some op amps that you can use to try out. All right, and then here's another one, so adjustable buffers. So again, it's going to show you a bunch of different designs, all based on op amps here, and this gives you different offsets and different things. So you can read through all this to kind of figure this out. What we're going to start with is just this one right here. We're just going to basically use this as a voltage divider. We're going to basically get an output of it. And we're going to use that output to drive an oscilloscope and maybe something else so you can kind of see this thing working. All right, but again, I'd like you to read all this so you can kind of get an idea here. And then, of course, you're going to be, and then showing some other, cool ideas here. Like driving a relay, for example. So when this thing, so here, threshold relay switch. So when this op amp, when the output hits a certain voltage, it's basically going to turn this thing on, and this relay is going to turn on. That was just what I was saying, using a certain force to turn something on, right? So anyway, read some of this, and then there are these kind of samples here. So if you have a 1.5K or 4.7 or 7.5K, it's going to kind of give you an idea of the different forces you could apply, right? And remember, 1 kilogram is 1 Newton. And these different forces you could apply, and then what these curves are looking like with these circuits. So if you use this feedback resistor of 7.5, 4.7, or 1.5 in a simple circuit, these are the kind of curves you're going to get. So for example, you see here, if you use this 1.5K resistor, we get this initial nonlinearity, and then this thing settles into this nice line, right? And then we can basically read from 200 to 1,000, but the voltage doesn't change much. Now, if we go ahead and we use like this red resistor, which is a 4.7K, now what happens is, again, we get this nonlinearity, and it happens a little bit longer maybe, right? A little bit longer. Then it's linear, but now we get kind of from 1.5 to 5 volts. We get more of a dynamic range. So it's a give and a take, right? So it's either you get more dynamic range, you get more nonlinearity, or you get linearity, less dynamic range, etc. So you play with this stuff and just figure out what you want to do, okay? All right, so that's that. So that's the force sensing resistor. We're going to use one from Interlink, and let's see here. I believe, yeah. So this is basically what we're using, and let's make this a little bit bigger for you guys. So this is a DigiKey right here, and I've kind of looked this up, the FSR 400 series, right? And the FSR 400, if we back up here, is this series of the small one and the big one, right? And let's go back here. So you can just order these right now. And again, these things are not cheap. $7, $8. These things are not at 1,000. They're $385. This is not a cheap little device. So, but if you want to sense force accurately, this is a way to do it. Now, other force sensors, really complicated, advanced ones, could be 100, 200, 300. They're $1,000, $10,000 force sensors actually. So if you want absolute accuracy, but these are usually good enough for the kind of applications we're going to be doing in sensing if something's coming, going, robotics, etc. All right. So you can order a few of these. Now, they are expensive, so what I do suggest is maybe look on Amazon.com or maybe look on eBay, whatever, and see if you can, Alibaba, Banggood, see if you can find some of these things cheaper, maybe a bundle of 10 or something on eBay for $5 if you want to play with them, because they break pretty easily. And let me go back to that SparkFun. So you see right here this connection. So these things are basically crimped. These are little crimps here, and they're just crimped. Can I make this bigger? Just crimped on here. And uh, if you apply any force, it just snaps off. So the first thing that I do when I want to play with one of these is I put a couple little connectors on here, and we've seen that stuff before, and I fabricate a little cable, and then I put some heat shrinking around this to protect it and give it some strain relief, so as I bend it around and stuff, it doesn't break. All right, so that's kind of how you have to work with these things, and you will break them as you play with them. All right, so we've seen the data sheet here. So here's the FS400 data sheet. So you're going to download that from Interlink Electronics, which if we go back to the website here, is just interlinkelectronics.com. And then the other thing that we are interested in is this guy right here, which is this integration guide, force sensing resistor integration guide and evaluation parts catalog. So you can get this from Interlink, or you can just get it on SparkFun very easily. All right. And then, okay, now let's go and let's talk about, so what we're going to do is we're going to build a circuit. What circuit are we going to build? We're going to basically build this circuit right here. And let me find that again. It should be right about here. Down a little bit. And here we go. So we're just going to build, something like this. Very simple circuit right here. And as a matter of fact, I think if I go, there's even a simpler one. Here's one here. And yeah, there might have been another one. Let me see here. Let me scroll through here. There's kind of a couple good ones to start with. All right, so here we go. And basically just a variable resistor. And we're just going to put it through an op amp, and we're going to use an op amp as an amplifier, which we haven't learned in the course how op amps work, but I'm going to show you real briefly. And let me see if there's, no, not really. There's another circuit that I like. Another circuit that I like here, but it's not in here, I don't think. Yeah, and these are current to voltage converters. That's why there's this feedback resistor and there's no more voltage divider. That would be hard for you to even to see though if you're not familiar with op amps. All right, so anyway, we're going to build the first simple circuit, which will go back to any of these, and it just looks like this. We're basically just an op amp, resistor, and our force sensing resistor, and that's it. Okay, now let's switch gears to op amps. All right, so let's talk about op amps. So operational amplifiers. So where do we even begin with that? All right, so the first thing is there are about 1 billion operational amplifiers. Inside of each operational amplifier is many dozens of components that create kind of this virtual amplifier. Now, what I'd like you to do is, again, always lots of homework with me. You know that if you've taken the class already. All right, so there's a couple books that are easily available online. One of them is called the Handbook of Operational Amplifier Applications, and it's written by Texas Instruments, which of course make operational amplifiers. So I want you just to search for this, and then just, it's SBOAO092B.pdf. If you just search for that, you can probably find it. But anyway, Handbook of Operational Amplifier Applications. It's 100 pages. I would just like you to read it. All right. And it's going to start to show you how these things work, what they look like, what their models are, and so forth. So this is one example, one good book. There's another book, and let me see if I can find it here. I think I already downloaded it as well. And let me see. This one. Again, another Texas Instruments book for free. Op Amps for Everyone by Ron Mancini is the editor-in-chief. So I believe this is like and there's different versions of this. Yeah, 2002. So this is very new. So as far as op amps go, this is brand new, right? It's like transistors. This stuff changes, but what we're going to be using, this is, as far as we're concerned, state of the art. Okay, so I want to kind of use op amps for everyone as our reference. Now, let's go through here. And what I want to do is I want to show you kind of the model of an op amp and just a couple circuits. All right, and then again, you're going to have to read this because this subject is very, very large, And then this is kind of circuit review, which you would have already learned in the class. But what we want is section 3 or chapter 3, I believe. Yeah, is the development of the ideal op-amp equations. All right, so you read this right here, and it's what it's going to talk about is an op-amp is this ideal amplifier, and it was designed and architected to have certain properties. Now, nothing is ever ideal, so it's close to ideal as long as you use it in a certain domain and you don't exceed that domain, right? As long as you play by the rules, it will act like this ideal amplifier for all intent purposes. It'll be perfect. If you break the rules, it will not work anymore. All right. So what I want you to look at here is kind of this model of an ideal operational amplifier. And so let's look at what's going on here. So it says things like we've got IB equals 0. We've got IB equals 0. So this current going in this direction and this current going in this direction are both 0. Then it's saying the voltage across these two terminals, VE, is also 0. Okay. Then it's saying its input impedance, ZI, is infinity. It says infinite input impedance. All right, great. And now what's going on here is basically this is an amplifier, right? And it's going to amplify. And so now we see this output, this A, so it can actually source infinite current. All right, so it's infinite current supply. And here's another, I wish this was true. The output impedance is 0. So it has 0 output impedance, it can source infinite current, it has infinite input impedance, and it draws no current. So basically this thing is completely ideal. So if you look up here, it kind of talks about all these things, right? Now in reality, these things aren't going to be true. So maybe it can output an amp or 100 milliamps. Maybe its output impedance is 10 ohms or 50 ohms. Maybe its input impedance is 100K or a megohm or 10 megohms. Maybe the input currents, these input currents that come in here are maybe microamps or picoamps. And maybe this voltage difference between the minus, which is called the inverting, and the positive non-inverting terminals, maybe the differential voltage is millivolts or nanovolts, maybe picovolts. I think there's some picovolt ones, operational amplifiers. Okay, so anyway, that's what we're looking for. And here's the rule. The more ideal the device, the more expensive it costs. So if you're building, for example, military grade, medical grade hardware that's dealing with very small signals, and noise is very important, where basically you're going to deal with very tiny little voltages, and you have to have these things operate so that there's no noise and all that. You're going to be using very expensive op amps, and by very expensive I mean you could spend a transistor's a penny, 2 pennies, 5 pennies. An op amp could be 20 bucks, 50 bucks. I never like to say never, but I've never seen an op amp that's $1,000, but I bet you there is one. But there's op amps that are tens of dollars easily. So we're going to use op amps that are $1, $2, $3, 50 cents, right? With certain properties, okay? So that's what we're going to pick. Now, picking op amps is like picking transistors and field effect transistors. There are just too many of them. So what you do is you have to pick a company that you like, a TI, a Fairchild, a this, or that, whatever, and kind of, get the part from them, whatever the company is that you like. And otherwise, you'll just be overwhelmed. So I'm going to just pick one for you, and then we're going to build something with it. All right. Now, all right, so that's kind of the model of the op amp. And then what happens here is it's going to start showing these different circuits. All right, so let's go ahead and let's take a look at some of these circuits. All right, so when you start off with op amps, you're going to probably be building 2 circuits a lot. One is called the non-inverting amplifier, and one's called the inverting amplifier. The non-inverting amplifier is nice because it doesn't invert anything. In other words, if you put a voltage in, say V, you get something times that voltage V out. The inverting version, you get minus V out, right? So it inverts the signal somehow times some gain or some other transfer function. All right, so let's just take a look at this. And now, again, you're going to have to read through this because it's going to derive the equations. All right, it's going to derive what's going on here. All right, but in a nutshell, and here's another thing. So now, when you want to derive the equation of an op amp, you can actually do it, and it's actually kind of fun. It's a fun exercise, and of course, if you take an EE course in this, you'll derive all of these yourself. You're not going to be given them, you're going to have to derive them and figure it out. But how do we derive it? Well, we derive it based on the laws of the op amp. So we assume that the guy who made the op amp, or girl, created this idealized version of it. So we know that the gain is infinite. We know that the output impedance is 0. We know that the input impedance is infinite. We know that the current into the inverting and non-inverting terminals is 0, and so on and so forth. We have all these rules. So then what we can do is we basically can put components on the op amp, and then using nodal analysis or mesh analysis, whatever you want to do, circuit analysis, we can constrain the circuit such that we can start to write formulas or a set of equations, and out of those sets of equations will emerge or pop out the transfer function for the op amp. And if you put capacitors and inductors and you have the proper formulas for them, you can get very complex filters and all kinds of cool things. Anyway, in this case, he's just starting off very simply, and he's saying, all right, we've got two resistors here. One's I'm going to call RF for feedback, and the other one I'm going to call RG, I assume, for it's going to ground. So the idea is we're going to have a voltage here, and the voltage is just going to be on this single input, Vin. All right, and that's all we know. We got V in, we got V out, we got these two resistors. My question to you, his question to us, and all that is, what is V out? What's V out? Well, he goes through this explanation here, kind of explaining why it's like that. And then he comes down, and he says, hey, here's the deal. V out over Vn equals 1 plus Rf over Rg. So 1 plus Rf over Rg. That means that V out, so if we take V in and move it over here, V out equals the input times this. So that's the transfer function right there. So basically, it's going to have a gain of at least 1 plus the ratio of these two resistors. So for example, say if you wanted to have a gain of 1, then we would make this feedback resistor 0. So if we make this feedback resistor 0, right, then basically it's going to have a gain of 1. Then if we make this RG infinite, we could make it infinite, right? It wouldn't notice it. Then we would still have this gain of 1. So basically, if you just tie the output to the input, you create this non-inverting amplifier that just the input follows the output because the gain is 1. All right. If you leave these resistors in here, then the gain is whatever this is. So for example, say we put RF as 100K. Then say we put RG as 1K. So 100 over 1 is 100, plus 1 is 101. So the amplification would be 101 times the input voltage. Now wait a minute, you say, wait a minute, what if I put 5 volts in here? So you're telling me I'm going to get 505 volts out of here? No, of course not, because that would break all the laws of physics. You can't get something you don't have. But within the, so say that the op amp is powered. Now we have to power these things. It's an active device, all right? We're going to power it, which is not shown here, with a positive and a negative supply. So say the positive supply was 10 volts and the negative supply was minus 10 volts. So when we try to do this amplification, so we said the amplifier is going to amplify 101 times. Let's call it 100, all right? 100 times. So if we put in a little voltage, say 0.1 volts, right? 0.1 volts times 100, right, would be 10 volts. So it would take the 0.1 and we would get 10 out. But the moment we put 0.2 volts in, right, that would be 20 volts out. It's still going to stay at 10 volts. It's not going to generate some miraculous voltage. So again, the op amp will only operate within, the realms of reality, but it will attempt to be ideal. It will attempt to do these things, all right? So it's never going to generate more voltage than you give it for the rails, for the power supply rails, which we're going to see where you hook that up. And again, it's never going to give you more current than the data sheet says that it can give. So even though you try to pull more current out of it, it's just not going to give it. If its op amp is rated for 100 milliamps and you put a load on it of 1 ohm, right? And so we put, say for example, we put out 10 volts and we put 1 ohm, right? So we got 10 volts, we got 1 ohm, so that's 10 amps. No, 10 amps is not going to come out of the, is not going to be sourced by the op amp unless it can source 10 amps. It's probably going to put out 50, 100, 20 milliamperes, whatever it's designed to do. So you can't break the rules, but as long as you stay within the rules and usually stay away from the barriers, away from the envelope. So you don't want to use this thing all the way to the envelope because then it's going to start to act nonlinear. So in other words, if you know that the op amp has a and we're going to talk about some other things. Say we know that the op amp it can source 500 milliamps. I'm probably not going to push more than 300 or 400 out of it. I'm surely not going to take it all the way to 500 because it's probably going to start acting weird, right? So if I want 500, I'm going to get an op amp that puts out an amp, right? Remember, always over design everything so that when things go sideways or things happen that you don't anticipate, nothing breaks. Okay, so this is the non-inverting amplifier. And we see the equation right here. It's V out over Vin equals 1 plus R feedback over RG. And these resistors will typically be called R1 and R2 in a lot of other books, R2, R1, all right? And then what I just said when I was just kind of saying, if RG becomes very, very large, right, and or RF becomes very, very small, right, then this whole thing reduces to V out equals 1, right? All right, times Vn if Vn is 1. Okay. Okay, so let's keep looking here. Now, the inverting op amp. So this is kind of what you're going to see more often. And the reason why is because this is a little bit more, having the 1 plus term is kind of a little unsettling as an electrical engineer. I don't like the 1 plus because it's 1 plus something. And that something is never ever really going to be 0. It's 1 plus it. So we kind of like no 1 plus. We just like input voltage times something, done. This is what this does. Now take a look here. So V out over V in equals minus RF over RG. Now look at the architecture of this one. This one has the feedback resistor going back from the output back to the input. And here's another little comment is op amps they operate with feedback. If they didn't, they would just be open loop and they would just they would saturate, they would go crazy. So we take some of the output and we feed it back to the input and create this feedback loop, and that makes them well behaved, all right? Anyway, so we take this output, we feed it back here through the feedback resistor, then again we have this G, which is not our ground, it's just RG, which I'm sure it says what he likes to call RG. But anyway, typically this would be R2 and R1, right? R or RF and R1 or RN, right? Anyway, either way, he goes through the rules of the op amp, and then he drives what this equation has to be. It just has to be. And then it's V out equals V in times minus RF over RG. So what is this thing doing? It's inverting the minus sign. And what's the amplification factor? It's RF over RG. Super simple. So let's say we wanted to make an amplifier that multiplied the input voltage by -1. That's all I wanted to do, by -1. All right, that's it. So I'm going to make RF and RG the same. Now, also there are rules for RFs and RGs. You don't want to make them too big or too small. So make them usually in K, right? So don't make them 1 ohm and 2 ohm. Make them in K. Don't make them in hundreds of K usually. Make them in tens of K. Make them in K. So I'm going to probably make RF and RG both 10K. All right, 10K over 10K is 1. So V out over Vn equals -1. Boom. So my output voltage will be my input voltage inverted. Now, wait a minute. This is cool. So I can put in a positive voltage and get out of negative voltage, but my power supply is only positive. No, you can't, unless you have a negative power supply. So to get the inverting op amp to work, when we power this thing, we're going to put a plus V and a minus V on it, a plus 5 volts and a minus 5 volts, a plus 12 volts and a minus 12 volts. So whatever we force it to do, it will do if it can do it. So if you don't have a negative power supply on here, you're not going to get a negative voltage out of it. You'll get the closest to negative that you can, which is 0. So again, you can't violate the laws of the op amp, and you can't violate whatever you have in your circuit. It's not going to work. But if you don't violate it, it will work. So for example, if we had a plus and a minus 12 volt supply, and we put in 1 volt, we'd get out -1 volt. If we put in 5 volts, we get out -5 volts, et cetera, et cetera. So we just basically did mathematical inversion, right? And if you wanted to gain it a little bit, say we wanted to multiply, so say we wanted to multiply the input by the output by -2. Then I would make RF 20K and I'd make RG 10K. So now my gain is 2, and with the minus sign is -2.